Hi everyone. So we are going to start with a new topic called as recursion. Okay. So it's one of the most trickiest topics in programming, and lot of students also find it difficult to master this topic in the beginning. So it takes little time. So if we talk about the difficulty level in the course, okay, so suppose the course is going like this, then at recursion the difficulty level will shoot up. Okay. So it's a difficult topic for beginners to understand, and it will take little bit time. As you go through more examples, as you do more problems, you will be able to understand this topic in a very better manner as compared to whatever you have done earlier. Okay, so recursion is one of the most difficult or trickiest topics to master in, and it will take certain time. Okay, maybe 1 or 2 months, so that you are able to visualize recursion for each and every problem. Okay, and other topics that are little bit tricky, and they are like dp. So dp is also related with recursion. You need to formulate the same kind of recurrence relations that we will see. And another one more topic that we cover in this course is graphs. So people generally find these topics difficult. Okay, so if you were doing a course till this point, and in this section you can expect a raise in the difficulty level. Okay, but you do not need to worry. You need to cross this global maxima. Okay, once you do this, you will find lot of other topics as easy. Okay, and also recursion will be used in other topics as well, such as trees, graphs, some of the problems of linked list. So as you go through more and more problems of these sections also, you will find it easier to work with recursion. Okay, so let's start. What is recursion? So it's a method in computer science, okay, where solution to a problem depends upon solutions to smaller instances of the same problem. Okay, so here two words are very important: smaller instances of the same problem. That means you're given a bigger problem. Okay, so what is the meaning of a big problem? So big problem means the value of input is big, the value of n is big. Okay, for example, you have a, let's say, problem of size n, and you want to break it into smaller problems. Maybe you break it into two problems of size n by 2. Okay, maybe let's say you are given an array, and you want to find out, let's say, sum of array. So what you can do is, you can say, okay, no, I will first find out sum of first n by 2 elements of the array, and then I will find out the sum of next n by 2 elements of the array. So I can combine them, and I will get the sum of the array. Okay, so what you're doing is, it's a way in which you are able to break a bigger problem into smaller sub problems, and you combine the solutions from the smaller sub problems to get the solution for a bigger problem. Okay, for the sum question, it's not actually required to use recursion, but still we can use it if we want. Okay, so the whole idea is, the idea is to divide the bigger problem into smaller sub problems. We will solve those smaller sub problems recursively, and we will combine the solution of smaller sub problems to get the solution for a bigger problem. Okay, and that breaking of problems can be in any manner. You can reduce the problem from n to n minus 1. You can say, okay, this is a sub problem. If I can solve this problem, I can also solve this problem. You can further reduce it into n minus 2, and so on. Okay, so we will recursively break down the problem into smaller sub problems, and we will try to figure out a solution for this problem. Okay, so let me show you one image. You can see this, there is a bigger image, it has smaller images of the same type. So that is what is the meaning of smaller instances of the same problem. So if you're computing the sum for a bigger array, and you're breaking this into, let's say, two small arrays, and you're computing the sum function here also. Okay, so that means you are doing the same thing on the smaller array. Okay, the function should remain same. So that is what it means, smaller instances of the same problem. So the problem is still sum, but the array for which we want to compute the sum is now smaller. Okay, so this actually helps us to simplify a lot of questions where we cannot easily write an iterative solution. Okay, so you know, you can easily compute the sum by using an iterative method also, but there would be certain problems where you can you can simplify the code using recursion. Okay, you can simplify the code using recursion for many complex problems. So that is why we are going to learn the recursive technique. simplify the code using recursion for complex problems. Okay, so one such problem that we will do in this section is Tower of Hanoi. Okay, so iterative solution is quite difficult for it to, but we can easily write the code using recursion for complex problems. Okay, so let us see what is recursion with the help of one example. So we will discuss parts of recursive algorithm. So a recursive algorithm is going to have two parts. One is called a base case and one is called a recursive case. So let's see. So let me take one example of the simplest possible problem in which you need to compute n factorial. Okay, let us say you want to compute 5 factorial, and also you know 5 factorial can be done easily using iteration. You need to multiply all the numbers in the range 1 to 5, and this answer is 120. But let us see how we can do it uh, using recursion. Okay, so n factorial is now a bigger problem. We need to break this into a smaller problem. Okay, so let us assume there is a function f of n which gives us the value of n factorial, and also we can express this function as n multiplied by f of n minus 1. Okay, so what is f of n minus 1? It gives us the value of n minus 1 factorial. Okay, because it solves a smaller instance, because it's n minus 1 of the same type, because the function is f. So f means a factorial function. So we can easily say that for any given problem, n factorial can be written as n multiplied by n minus 1 factorial. Okay, so this is what is called as a recursive case. This is called as a recursive case. Okay, so any recursive algorithm will have a recursive case and it will have a base case. So let us discuss what is a base case. So let us assume we want to compute 5 factorial using recursion. So what we will do, we have 5 factorial, that is the problem we want to solve. We will say this is nothing but 5 into 4 factorial. Okay, now 4 factorial is another problem that we need to solve. So we can say, okay, 4 factorial can be written as 4 multiplied by 3 factorial, and 3 factorial is another problem that we need to solve. So it can be written as 3 into 2 factorial, and here we have 2 factorial, that is a problem. So it can be written as 2 into 1 factorial, and this can be written as 1 into 0 factorial. Okay, now at this point we have the problem that we need to solve is 0 factorial. So we cannot further reduce 0 problem to minus 1 factorial or minus 2 factorial. So we have to basically stop at this point. Okay, so we need to stop at this particular point. We can also stop at 1 factorial because we know the answer for 1 factorial is 1, but let us assume we are stopping at 0 factorial. So we can say this answer is going to be 1. So what we will do is we will substitute this answer. Okay, we will substitute this answer in the previous cases. So 0 factorial is 1, so this becomes 1. Okay, and 1 into 1 is 1, so we put a 1 here, so it becomes 2. We put a 2 here, it becomes 6. We put a 6 here, it becomes 24, and we put 24 here, so this becomes 120. Now you can see what we did is we actually did two steps. We reduced our problem to the smallest possible case, and then we built the solution from the bottom to top direction. So there are two directions. So this direction of is called as, let's say, top to down direction. Okay, and this is nothing but we are going towards the base case, going towards the base case. Okay, so this case, the value of f of 0, that is equal to 1. So this case will be called as a base case, and the value of f of n, that is written as n into f of n minus 1, this will be called as recursive case. Okay, so what we do, in each step we reduce the problem to a smaller sub problem until we hit a base case, and from the base case we start coming back and build our solution. Okay, so you can see 1 factorial is 1, so this goes here, so this goes here, this goes here, and this goes here, and we get the final answer as 120. Now let us see how do we implement this in the form of a code. Okay, so let us first write the code, and then we will also understand the magical rule of recursion. Okay, so let's see, the code is factorial.cpp. Okay, so we need to write a function called factorial. In 10 we have a function called main. So now in this function we need to write two things. One is our base case and another is our recursive case. So what we do in the base case, we first check. Suppose you are computing some answer for a value of n. So you need to check if this answer is equal to base case, then you need to stop at this point. So if n is 0, so 0 factorial is 1. So I will just return the answer as 1. And second is recursive case. In the recursive case, what you need to do? So let us see what is the magical rule to approach recursion. So it's nothing but it's the principle of mathematical induction. Okay, so you will follow this rule to write code for any recursive problem. It is based upon principle of mathematical induction, or it is called as PMI. So it says figure out the base case. So in the factorial problem, we have figured out the base case that f of 0 is equal to 1. This is our base case. Okay. Second, while writing code, you need to assume the sub problems can be solved by recursion. So that means if we are computing the value of f of n, we can assume that f of n minus 1 can be computed using recursion. So we have to assume this thing. Okay, so if you do not assume this thing while writing code in the beginning, you will get confused. So let us assume that we already know the smaller sub problem. Using the sub problems, we will need to write the answer for the current problem. So this is our current problem. Okay, so how do we use this sub problem to write the answer for the current problem? So it can be written as n multiplied by f of n minus 1. So this is what is called as a recursive case. So in this, out of all three steps, the second step is most important while writing the code. If you do not assume you have the answer for the sub problem, you will find it very difficult to write the code for the recursion. Okay, so now let us say in the recursive case, the answer for the sub problem, let's call it as a small answer or sub problem answer, whatever you want to call it as. So small answer is going to be nothing but fact of n minus 1. And once you know the small answer, okay, so in this line you can assume that this code executes perfectly and this gives you the small answer, and you can build your answer for the current problem, that is f of n. So that is going to be nothing but n into small answer, and you can say return answer. Okay, so this is one way of writing the code. If you do not want to create variables, you can directly write return n multiplied by fact of n minus 1. So that is also fine if you do not want to write all the case. Okay, so now let us test our code. Okay, so let me give 5. You can see I'm getting 120. Let me give 6. I'm getting 720. So that means this is probably correct. And now let us verify how this is working. Okay, so let us see at what happens at the memory level when you do a recursive call. Okay, so now you can see we are calling the same function that we have here to compute the answer for the sub problem, but let us see how does this function call proceed. Okay, so let me just break it down into something called small answer. So small answer is fact of n minus 1, and let us say return n into small answer. So that is also fine. Okay, now let us see what happens. So you know function calls happen via call stack. Okay, so that's something that is known to everyone. So let's assume we have a call stack. Okay, and in this call stack we have the function called main. Okay, so every function call that we make goes inside the stack, and all the variables that we have in that particular function are stored in the particular stack memory. Okay, so we have in the main the value of n that is equal to 5. From here we make a call to the fact function. Okay, so fact function gets the value of n as 5, and it also creates a variable called small answer, and let's say the small answer variable is created in this memory, and that value is not known. So that value is not known, so it initiates another function call. Okay, so if I talk about this particular function, this function gets paused at line number 12. From here another function is called that goes into the stack, and it says okay, the value of n is now 4. So you create a copy of n. Okay, so we are passing it by value, so that means every time the function is called, a new value, a new variable n is created in the stack memory of that particular function, and it is a local variable in that particular memory. So here you, what you do here, you check if it is a base case or not. So this is skipped, so you come to line number 12. So it is also paused at line number 12, and it also initiates another function call 2 factorial with the value of n equal to 3. So here you do not know what is the value of small answer, and here also you do not know what is small answer. So you make another call with n equals to 2, and here also you do not know what is small answer. Okay, so line number 12, line number 12. So you can treat the call stack as copies of the same function. Okay, so the same function is getting executed for different values of n, and in the call stack you have the state of the variables for different values of n. Okay, so we have n equal to 1 in this call. So this function is again paused at line number 12, and we do not know what is small answer, so it makes a call to f of 0. Okay, so here we are at n equal to 0. Okay, so finally when we are at this particular function, okay, so we say if n is equal to 0, so it says yes, it is 0. So what we do, we say return. So basically return means remove that function from the call stack and return that value where it was required. Okay, so where it was required at this particular point from the previous function call. So previous function call knows the answer for 0 factorial is now 1. So 0 factorial says my answer is going to be 1, and from this function you return n into small answer. So what is n? N is 1 and small answer is 1. So you basically return from this function. Okay, so line number 12 is executed, line number 13 is also executed, and once line number 13 is executed, you return 1 to small answer to the previous function. So the previous function is n equals to 2. So here you again know the value of small answer. So once you know the value of small answer, you know line number 12, you execute line number 13. So it says 2 into 1. So this gets removed from the stack. 2 into 1 is 2, so it comes here. And similarly you execute this function call now from where it was paused. It was paused at line number 12. So the answer becomes 3 into 2, that is 6. So it goes off from the call stack. So 6 comes here. So it becomes 4 into 6. This function goes off. It returns the value 24 here. So it becomes n into small answer, that is 120. It gets popped off. And finally in the main you get an answer that is equal to 120 at this particular line. So once this is over, main also goes off from the stack, and finally you will have a empty stack. Okay, so if you now carefully analyze the memory requirements of this function, so you can see the memory, initially the stack was getting filled, it shot up, and then it started decreasing. So in the worst case we were using order of n memory, and this is the time of execution of the program. Okay, how the memory requirements changed during the recursive program. So if someone asks you what is the space complexity of this program, so it will be order of n, because you are using a implicit recursive stack, and that is going to store n number of variables. Okay, so you can see it's going to take order n memory because you have n number of stack frames, and each stack frames contains a constant number of variables. Okay, one is value of n, one is small answer. So you can see also the time complexity is also going to be order of n, because we made n calls, and in each call we are doing a constant operation, that is multiplying two numbers, another constant operation that is checking for the base case. So I hope you got an idea how to visualize recursion using call stack. But as a beginner, you should first follow these steps. You should find out a way to write the code, and this golden rule or this magical rule will help you to write the code for the recursion. Once you have written the code, you can verify that your code is correct by drawing the call stack, and you can also draw a recursion tree. Okay, so we will see more problems in the upcoming videos. Hi everyone, so now we will discuss how do we compute nth Fibonacci term using recursion. So let's say given the Fibonacci series, you want to compute what is f of n, okay, and for a given value of n. For example, if n is 5, you want to compute the fifth term of the series, that is 5 in this case. And property of Fibonacci that we already know is that the nth term depends upon the previous two terms, okay. So it is sum of previous two terms. So f of n can be written as f of n minus 1 plus f of n minus 2. From this very recurrence, we know how to compute f of n, okay. So what we need to do is to implement the code, figure out the base case. Okay, so let us see what happens at small values of n. For example, you want to compute at n equals to 2, so you will make a call on n equals to 1. You will also make a call on n equals to 0, and n equals to 0 will be our base case. And let us see what happens if we do not make n equals to 1 as a base case. So we will make a call on n equals to 0, and we'll make a call on n equals to minus 1. So this is something that we cannot do or we should not do, so we do not make this call. So what we do, we also make n equals to 1 as a base case. So we will have two base cases here. So we will have f of 0 that is equal to 0, we will have f of 1 that is equal to 1. So we know what is the base case. Second step is you need to assume the sub problems can be solved using recursion. So you do not need to worry about how do we compute f of n minus 1 and f of n minus 2 while writing the code. Once you have written the code, you can actually verify, you can visualize how this program works, and you can be certain why your code is working, okay. So third is we need to combine the sub problems to write the answer for the current problem. So that is clearly we have done. So we need to add the sub problems to compute f of n. So we know all the three steps now. So firstly we will write the code, and then we will try to visualize it, okay. So let's go into the code. Okay, so I had already written, so I will still write it again. So first is you need to find out the base case. So base case would be if n is 0 or n is 1, we need to return the value of n, okay. So that means if n is 0, we are returning 0. If n is 1, we are returning 1 in this case. Or you can make two conditions as well, okay. In the recursive case, we need to compute two sub problems. So we can simply say return f of n minus 1 plus return f of n minus 2. But to make your visualization easier, we will do it in two steps, okay. So we will say, okay, let's compute the first sub problem, that is f of n minus 1. Then we will compute the next sub problem, that is f of n minus 2, and then we will return the concatenation of both, okay. So we will return f of 1 plus f of 2. And now let us test our code, okay. So let's say for 5 we are getting, so we are getting correct answer for every value, okay. So you can see the code is correct, and now let us try to visualize our code. What happens in the memory, what happens in the call stack, how does a recursion tree look like, we will draw everything now, okay. So let's assume your code starts from n equal to 1, okay. So let's say you have this main, okay. So this is your main, and from here you make a call to the Fibonacci function with the value of n equals, let's say 4. So let us say you want to compute for the Fibonacci function for the value n equals to 4. So in this function you check for the base case, so that is not true. So you come to line number 13. So we are executing line number 13. So from this line you make another function call. So you another function call that goes in the memory, and a copy of n is created. So that n is now going to have a value 3. So from 4 we are making a call on the sub problem, that is 3. Okay, that's what we have done. And in 3 you again check for the base case. You come to line number 13, and line number 14 is not executed, so you are computing f1 first. Line number 14 is not executed, so we are at line number 13. So here also you compute f of 1. So that leads to another function call. You make another function call with value of n equals to 2, and that says okay, base case is not true, let's go to line number 13, and it says okay, I want to compute the value of f of 1. So it makes a function call on f of n equals to 1. From 3 we make a call on 2, and from 2 we make a call on 1. Okay. And it says okay, what is f of 1? So at this particular point you see the value of n is 1, so that enters inside the base case, and it says return 1. So here we do not compute f of 1, but we say okay, return 1. So this value of 1 is returned at this particular point. So 1 returns a 1 here, and as you hit a return statement, that function call goes off from the memory. And what will happen is you are now in this function. So the function that is at the top of the stack is currently executing. So this is the function that is executing. So here you will move to line number 14, and you will try to compute f of 2. So what is f of 2? It is another function call. You're making a function call on n equals to 0. So from here you make another function call, that is n equals to 0. Okay. And as you hit this function, you see n is 0, so it returns n, so it returns a value 0. Okay. And this function also goes off from the memory. So carefully note how is the space increasing in the code. Okay, so we are making function calls. The space utilization is maximum at n equal to 1, then it dips because of the n equal to 1 function gets popped, then it increases again because we make a function call on n equals to 0, and this function will again get over, so the space utilization will decrease at this particular point. So what happens now is we are at line number 15 in this particular function. The function at the top is currently executing, and this value is now known as 0. So what it will do, it will add these two values 1 plus 0, and it will return a 1 to the previous case. So that's what we do here. So we return these values, and we came to know that the value of f1 for n equals to 3 is 1. So what will happen now? So we are now executing the function that is at the top of the stack, and that function is f of n equals to 3, and that has already executed line number 13. We will now execute line number 14. So it will say okay, I want to compute f of 2. So it will make a call. It will make a call on n equals to 1. So you can see the space utilization has dipped, and it will increase again at n equal to 1. Okay. So again, so we are making a call on n equal to 1. It is a base case. It will say okay, return 1. So this value is now 1. So this function again goes off from the memory. So 3 made a call on 1. 1 says my answer is 1. So f of 3 will return 2. So you can see these two terms, when get added, they will return true. Okay. So this is how f of n equals to 3 goes off from the memory, and f of 4 knows the answer for f of 3. That answer is going to be 2. Okay. And what happens is now is you have fewer frames in the call stack. Okay, you just have 2 frames. Okay. And now the function that is currently executing is f of 4, and that has already executed line number 13. So what it will do, it will execute this line. So it will make a call on n equal to 2, and since we have not stored the value of n equal to 2, we will redo some work again. So that will say, okay, to compute n equal to 2, you need to compute f of 1, so it makes a call on 2. Okay, and from here we say, okay, make a call on f of n equal to 1, so there will be some increase in the space as well. Okay, and from here it will say, okay, my answer is 1, so it says answer is 1. So it will say, okay, let's compute f of 2, that is n equal to 0, so it says my answer is 0, so it makes a call on 0, it says it's 0, and you return the sum of these two values. Okay, so that is going to be 1 plus 0, that is 1. So f of 2 for 4 is now this thing. This goes off, and from here we return the answer as 1 plus 0, that is 1, and at 4 we know the answer is 2 plus 1, that is 3. So in the main we get the answer as 3, and finally n equal to 4 is removed from the call stack, and finally main is also removed from the call stack. Okay, so this is what happens in recursion. Okay, so you can see the space graph would look something like this. I've not drawn the exact graph, but it would be something like this. Okay, so when you go deeper into the call stack, the space utilization is maximum, and at these two calls the maximum space is being utilized. So the space complexity would be order of n, because you have n number of stack frames in the call stack. Okay, so this is how this code actually works, and this is how you get the value of f of n equals to 1. Okay, and another thing to note is the recursion is executing in a left to right order. Okay, so if you want to build this kind of a tree, okay, you first, this branch is executed, after that this branch is executed, after that this branch is executed, after that this branch is executed, and finally this is executed. Okay, so this is how recursion proceeds. But suppose if you want to make a tree for your own understanding, or for just for the visualization purpose, you can also draw it parallelly. Okay, for example, if you want to make a tree for n equal to 5, so you know that 5 will make a call on 4, it will make a call on 3. From 4, you know, you can make a call on 3, you can make a call on 2. From 3 you can make a call on 2, you can make a call on 1. From 2 you can make a call on 1, you can make a call on 0. From here the answer will be 1, it will be 0, it will be 1, it will be 1, it will be 2. From 2 you need to make a call on 1 and 0, it will be 1, it will be 0, it will be 1, so it will be 3. And from 5 you're making a call on 3, so it will make a call on 2 and 1, 1 and 0, 1, 0, 1, 1, 2, so it will be 3 plus 2, that is 5. So this is how you can quickly build a recursive tree without actually going into the details of the call stack, what happens at each call stack. Okay, so in order to make your work simpler, you can just directly build the recursive tree to visualize what happens in each case. Okay, so I hope you got an idea how recursion works, how call stack works, and we will see some more problems in the coming videos. Hi everyone. So to make your recursion concepts more clear, we are going to write a very simple two functions. One will print the first n numbers in the increasing order. That means if n is 5, you just need to print 1, 2, 3, 4, 5. And another function of the same type, but it will print the numbers in the reverse order. Okay, so that means you need to print 5, 4, 3, 2, 1. So now let us see what is the problem here, and how we can break this into smaller problem. Okay, so for example, n is 5, and let us assume printing, we can print one number and we can ask recursion to print all other numbers. Okay, so let's say if we are starting with n equal to 5, let us first discuss the decreasing order one case. Okay, so we'll first write the code for the decreasing order. What we can do is, okay, if you want to do some work for n equals to 5, what you can do is you can simply say, okay, print 5. Okay, and you can make a call, or you can say print n, you can make a call on the function for n minus 1. Okay, something like this. So if you have a function n that prints the numbers from n to 1, So what you can do, you first print the small number you currently have, and you make a recursive call on the smaller number. So if you make a recursive call on 4, it will basically print all the numbers from 4 to 1. So this is done by recursion, and this is done by you. Okay, so it's pretty easy. So what we will do is, we will first write the code and then we will see. Okay, so let us say int decrease, or let's say void decreasing is the function where we get the value of n, and we have main here, and we call this function decreasing of n. So what you need to do, you need to first figure out the base case. Okay, so base case means you are reducing the value of n. So if you reach, let's say 0, you will stop. You do not need to do anything for n equals to 0. You should return. Okay, or you can do something like this: if n equals to 1, you print 1 and then you return. So that is also fine. So but let me make this case: if n is 0, we will stop. Okay, and according to the rule, what we need to do, we just need to do two things. We need to write the current case and the base case. So base case is already written. We need to find out what happens in the current case. What you need to do for this value of n, so you need to print this value of n followed by all other values of n which are smaller. So you need all other values from n minus 1 to 1, so that you can assume it will be done by this function decreasing of n minus 1. That's it. And now let us try to run this code and visualize it, how it works. So let's say n is 5, so I get the answer from 5 to 1, so that is 5 4 3 2 1. So let us see what happens in the call stack. Okay, so we have this function main. It makes a call to the decreasing function with n equals to 5. Here what we do, we say okay, we will print 5 and we will reduce our function call to n equal to 4. In this function call, what we do, we print 4. Okay, so we are actually printing in this direction. Okay, and we make a call on n equals to 3. So here we print 3 and we make a call on n equals to 2. Here we print 2, we make a call on n equals to 1. So we make a call on n equals to 1. And from here we print 1 and we make a call on n equals to 0, that says return. Okay, so once we come back in this function, we see okay, we don't have anything, so we just jump to this line, so that is nothing but a return statement here. Okay, so it's a void function. In the recursive case, writing a return statement is optional if it is a void function. So this function gets over, so we do not do anything, we just come back here. We do not do anything, we come back here, we pop it, we come back here, we pop it, we come back here, we pop it, we come back here, and that's the output that stays on the screen. But now, can you exploit this same function, the same recursive behavior, to get those numbers in the increasing order? Okay, so we have seen that currently we have printed these numbers while going from top to bottom. Okay, so this direction is top to bottom. Starting from a larger value that is on the top, we are going towards the bottom. Okay, from 5 we are going to 4 3 2 1 0. Okay, we do not print 0, so we get these numbers. Another thing that we can do is, we can also print the numbers while coming from bottom to top. Okay, so that is something we can do. So that means we can first reduce our subproblem and then we can print the numbers in the increasing order. Okay, so first make a recursive call and then you start printing those numbers. Okay, so if we do the work in this direction, we can actually get 1 2 3 4 5. We can get those numbers in the increasing order. So that is our another direction, bottom to top. So we can exploit this to build our increasing function. So let me show you if we want to assume how this function will work. Okay, so let us say there is a decreasing function. So decreasing of n will do two things. It will first print n followed by decreasing of n minus 1. But if we want to write increasing of n, what it will do, it will say first print all the numbers. Okay, so it says first print 5 and then you print 4 3 2 1. But in increasing of n, we will do something opposite. We will say okay, first print all the numbers in the increasing order from 1 2 3 4. So you can assume that this function will do the work for you, increasing of n minus 1, and then you can print the value of n, so that is 5. So you will get the output as 1 2 3 4 5. So this is what we are going to do in the recursive case. So let us see here, void increasing of int of n. So again, base case will be same. If we hit 0, we will return, okay, but here the order of statements will change, okay. So line number 14 and 15 will be swapped. So first print all the numbers in the increasing order up to n minus 1, and then you print the number n. So that will actually change the way output is going to be present on the screen. So let me show you, increasing of n and cout handle. Okay, let's say n is 5. So you can see we are getting the decreasing numbers, we are getting the numbers in the increasing order as well. So let me just dry run this one with the help of call stack. So we have main, we make a call on increasing function with n equals to 5, we make a call on n equals to 4. So we are at line number 23 in every function, okay. From here we make a call on n equal to 3, n equal to 2, n equal to 1, and n equal to 0. At here we hit the base case, we pop this function and we come back here, okay. So in every call we are at line number 23. So once you come back to this function call, what will execute? Line number 24. So the first output that you will see on the screen is the value of n, so that will be 1. Then you come back here, it will be n equals to 2. Then you come back here, it will be n equals to 3. Then you come back here, it will be 4. You come back here, it will be 5. And this is how the output is being written, okay. So anything that is written after the function call is actually a bottom up direction, okay. That is from the base case towards the top, okay, or bottom to top, you can say. Or anything that you write before the function call, okay. So before the function call, this is executed in the direction when you go from top to bottom, that is you go from top to base case, okay. So these two things you should be knowing, that the code that is written before the recursive call executes in this direction, and the code that is written after the recursive call executes in this direction. So that will really help you to solve some of the problems in a very simplified and easy manner without getting confused what happens, okay. So that's all for this video, and see you guys in the next part. Hi everyone, so now we will discuss one example. We have to check if a given array is sorted or not, okay. For example, given this array, you have to print this array is sorted, but suppose if this element was 14, then you have to print false, this array is not sorted, and we have to do it using a recursive function. So now let us see how we can break a array problem using recursion. So suppose you have a very large array, there can be multiple ways to break that array. For example, this array contains n minus 1 elements. You can say, okay, I will keep the first element here, and I will make a recursive call on the other n minus 1 elements. So this could be one method. Or what you can do is you can break it into two parts. You can say, okay, this is my first method, okay. You can say I will break it into two parts of size n by 2, and I will check, okay, if this array is sorted and this array is sorted. Let's say these elements are 1 2 3, and let's say these elements are 4 5. So if I can check if this array is sorted, and if this array is sorted, I can check if 3 is less than 4, then this entire array is sorted. That is something that I can also do. But for this problem, we are just going to follow the first method, where we are going to break this array into two parts, one as an array of size 1, okay. So and remaining elements will remaining array will contain n minus 1 elements, okay. So now you have reduced this into a sub problem of size n minus 1. So what you can do, you need to check if a given array of size n is sorted or not. So for that, what you need to do, let's say this array is named as a, okay. So firstly, you need to know from the recursive function that f of n minus 1 is sorted. Okay, so we need to know f of n minus 1 is sorted. So if this is true, okay, if this is true, then we must compare the first element of this array, that is a of 0, with the first element of this array. Okay, so that is nothing but a of 1. So if a of 0 is less than a of 1, then we can say this array is sorted if the remaining n minus 1 elements are also sorted. So in this case we will return true, otherwise we will return false. If any one of these conditions is uh, not true, we will return false. Now we need to figure out what is the base case. Okay, we can say if an array contains 0 or 1 elements, then it will be always sorted, so we can return true in this case. Okay, and we can assume sub problems can be solved using recursion, so that means we do not need to worry about f of n minus 1. We can just make a recursive call and ask, okay, recursion, tell me whether the smaller subarray is sorted or not. Using the sub problems, we need to write the answer for the current problem. So this is how we write the answer for the current problem. So for the current problem, we need to check if a of 0, that is 1, is less than the next element, that is 2, and all other elements in this array are either greater or equal to 2, and they are in the sorted order. So that will be told by recursion to us. So let us first write the code, and then we will try to visualize how this recursion actually works in the sorted array. Okay, so this time I will make the return type of the function as bool, and I can say is sorted. I have this array a, okay, and I also have the number of elements in the array n. So now we need to think about the base case. Okay, so in the base case I can say if n is 0 or n is 1, that means my answer will be true. So array with 0 or 1 element will be a sorted array. And let's think about the recursive case. So in the recursive case, what we can do is we can check if a of 0 is less than a of 1, and we can check is sorted what? The remaining array. Okay, so the remaining array starts from a plus 1, so that is the base address of the remaining array, and also the number of elements in the remaining array will be n minus 1. So that basically means the array which starts from the index a plus 1, so this index is a plus 1, okay, and it contains n minus 1 elements. Okay, if this array is also sorted, then we can say we will return true, otherwise we can say we will return false. That's it. That's the whole code. Okay, so there can be multiple ways to write the code for the same problem. You can take a variable I to denote the index of the next element instead of doing a plus 1. That you can do, but this is also fine. Okay, this is the simplest possible code I could think of from the logic we had discussed. Okay, so let us first run this code and then we will visualize it. Okay, so is sorted, we can give array and n. So this should be arr and n. Okay, and let's try to run this code. So we are getting 1, that means it's true, and if I make this element as 14, so we will get 0, that means it is false. So 0 means this array is not sorted. Now let us try to visualize what happens in the recursive call. Okay, and also you are passing an array. So arrays are passed by reference, they are not passed by value, but you are also passing the base address of the next array. So this address actually gets copied in a pointer variable. So we have, so array is passed by reference, but the address of the array is passed by value. Okay, so there is a common array that is there in the memory, but we are actually changing the address of the array in each function call. So this is nothing but it is equivalent to a pointer variable. So that means in every call stack you're making a copy of the pointer variable. Okay, so let me tell you what happens in this case. Okay, so let us say we have this particular array. So this array is 1 2 3 14 and 5. So what you do, you say okay, uh, in this case this is what the a variable points to. So ARR is in the memory. Okay, so ARR is there in the memory 1 2 3 14 5, and ARR stores the base address. Let's say this address is 100, so A also stores 100. Okay, the starting address of the array. Let's say next address is 104 108 and so on. Okay, so you enter the base case, n is not 0, so n is here 5, it contains 5 elements, so you skip it, you come here, you see okay 1 is less than 2 and is sorted a plus 1, so 1 is less than 2, this is true, so we execute this function call. So we say okay is sorted a plus 1 and n minus 1, so we make a function call on the smaller part of the array. Okay, in which we do not pass the entire array, we just pass the base address of this array. So the base address is a plus 1. So this, the new function knows okay the base address of the array a is 104. Okay, so this is array a for the new function call, and we have a 5 here. So now you again compare a0 is less than a1. So what is a0 in this case? This is 2. So we compare 2 is less than 3, and you make a call on the remaining part of the array. So that is 3 14 and 5. So n is 4 at this point. Okay, and n is 3 at this particular point. At here you, what you do, you compare if 3 is less than 14, and I will make a call on the remaining part. So that call will not be made, that call will be made, yes. So the remaining part of the array is 14 comma 5. So n is 2 at this particular point. So as you are going down, as you are making more number of calls, what happens is at this point you check 14 is less than 5, and you will make a call on 5. Okay, but this call will not be executing due to short circuit. Short circuit basically means if there is a AND condition in the if statement and the first condition is false, then the second call is not executed, or the second expression is not evaluated. Okay, so if this is false, so we do not actually make up this call, so we actually return false from this point without hitting the base case. Okay, so we return false from this particular point. So now what happens in the previous function call is, in the previous function call you needed an answer at this particular point, so this answer comes out to be false, so it also returns a false here. So this answer is false, so this also returns a false, and this false is now propagated back to the main. So that's how we get a 0. Okay, so false is stored as 0 and true is stored as 1. So okay, so let me give you another case where we have a sorted array. Let's say we have 1 2 3 and 4. So what do, you compare 1 and 2, you make a call on 2 3 4, you compare 2 less than 3, true, and you make a call on 3 4. You see 3 is less than 4 and you make a call on 4. So in this case you see you have actually one element in the array, so it actually returns true. So we might not be hitting this case, so we will be only hitting this case when we have one element in the array, it returns a true. So this true goes back, this true goes back, this true goes back, and this true goes back. Okay, so this is how the true is propagated back from the base case to the main via each recursive call that is stored in the stack. Okay, so it's just a game of this if else statement. So as soon as you find out okay there is a comparison which is not correct, you return a false at that particular point. So I hope you will be able to understand this problem, and I've not drawn the call stack, but you can do it on your own now. Hi everyone, so now I'm going to give you some few problems to try by yourself. Okay, you need to first write a recursive function that performs binary search. Okay, so binary search means you're given a sorted array and you're given, let's say, a key. You need to find out the index of that element in this array by using the binary search algorithm. Okay, so you will divide this array about the midpoint, and then you will see if the key is greater than midpoint, then you will discard this array and you will do a recursive search in the smaller part of the array. Okay, so that you will do for every step. So you have to use a recursive binary function that you have to build in this problem. So it's easy problem, I think you should be able to build. So that's the first question that you need to try. Second is you need to write a recursive function to perform a raised to the power n. Okay, so you need to compute, let's say, 5 raised to the power 6 or 2 raised to the power 8, something like that. So clearly you need to think how we can break this into smaller sub problems and whatever. Okay, so here also you need to see. So if I give you a hint, you can clearly say that a raised to the power n can be written as a multiplied by a raised to the power n minus 1. So you can use this trick to break this into a recurrence, and you need to figure out the base case and you need to write the code for it as well. Okay, so the third problem is you need to write a recursive function to multiply two numbers without using star operator. That means you're given, let's say, 5 into 3. That's what you need to do. So it should be 15. So recursively you will write something that will add 5 3 number of times. Okay, so that answer should be 15. So you need to write a function called multiply that recursively adds the number a b number of times. Okay, so if you add a b number of times, you will get the answer. Okay, and you need to think of how it can be further broken down into sub problems. So a hint would be, you can simply say multiply of a comma b can be written as a plus multiply of a comma b minus 1. Okay, so if you have multiplied a b minus 1 times and you add a to it, that will actually help you to get the recurrence. So think about the base case and implement all these three functions, and happy coding. Hi everyone, so we will now discuss a problem in which you are given an array and you need to find out the first occurrence of the key present in that array. Okay, so let's say key is 7. So you need to find out, okay, what is the index of the first 7 that is there inside this particular array. So obviously we can use linear search, but let's see how we can build this linear search function using recursion. So this function will return me the index of the first occurrence of the key present in the array. So there can be multiple ways to write the code for this problem, but let us discuss one of the ways. Okay, so let us assume that you are breaking this problem into two subproblems, or one subproblem of size n minus 1, and let's say this element is some x. So what you need to do, you need to check at array of 0 if that element is 7, so you return this index that is equal to 0. Okay, otherwise you ask your subarray, you make a recursive call and you ask your subarray to give you the index of 7. Let's say this index is I. Okay, so from the subarray you come to know here that the 7 is present at ith index. So what this should return, this should return to the main that the 7 is present at I plus 1th index, because of this element you are adding 1 to the index. Okay, for example, let's say this is 3 and here you have 4 7 2 6. Okay, so in this smaller array the 7 is present at the first index. Okay, so this returns a 1 here, so this should return 2 to the main. Okay, so that's the whole idea. This is how we can recursively break down our problem. So, and it is also possible, suppose this element is 17, then this will return minus 1. Minus 1 means, okay, this 7 element is not present, then this should also return minus 1 to the previous function call. Okay, so basically what we can do is we can break our array into a subproblem of size n minus 1, and we can make a recursive call on this array to check where is 7 present in this array. Okay, assuming that subproblem will be solved, so we get this index I, and this index I can get two values. If the 7 is not present, it will get a value minus 1. If 7 is present, okay, then that value will be I. But if we want to compute index with respect to this starting point, that index will be I plus 1. That's what we are going to do. So let us see what we can do is, So we can check if n is 0, that means we have checked all elements of the array and we could not find any element that was equal to 7. We will say okay, we will return -1. Okay. Otherwise, we are in the recursive case where we will make a sub problem. Okay, so we can first check on the current index. We can check if a of 0, that is my current element, that is equal to key, then I can simply say return 0, my work is done. I do not need to call on the further array because I'm looking for the first occurrence, and that occurrence is present on the 0th index in the current array only. Okay. Otherwise, if this is not the case, it is possible that 7 is present in the remaining part of the array. So we can make a sub problem. Okay, so we can find the index in the remaining part. So int I, that will be equal to first occurrence of that particular key or 7 in the remaining part of the array. So remaining part of the array starts from the index a plus 1 and it contains n minus 1 elements and the key remains unchanged. And if the remaining part returns -1, okay, so if I is equal to -1, that means the remaining part does not contain a 7. We can also return -1. Okay. Otherwise, the remaining part contains 7. So the index of the 7 with respect to the current part would be I plus 1. So we can return I plus 1 in this particular case. Okay. So this should be size of ARR upon size of int. So let me run this code, and in this array we have this 0, 1, 2, 3. So we should get an answer as 3. So see out first occurrence, array and key. So it's called linear search. Okay, so we are implementing a linear search function, and you can see we are getting 3 as the index of the first occurrence in this particular case. Okay, so now if you're slightly confused, I will just give you an idea of what we have done. So we have 1 2 7 3 7. Let's say this is my array. Okay, so in the first occurrence function, I check n is not 0 because n is 5. So I come here, I check a of 0 equals to key, it's not. So I skip this. I make a recursive call on the smaller part. So smaller part is 2 7 3 7. Okay, and as I make this particular call, this returns me something. This will return me something. So it will return me some value of I that is currently not known to me. Okay, so I just start with this recursive call. What happens here? So we see n is 4 here. That's not the recursive case. In this case, this is the array and a0 is not 7. Okay, so we skip this part and we make another recursive call. We are in line number 13 here. So we come to this 737. So in this case, this is array and n is not 0 and a of 0 equals to key. So a of 0 is actually equal to key. So this is a of 0 and this is equal to 7. So what I do, I return 0. So I tell this bigger array that 7 is present on the 0th index in my smaller array. We do not make any further recursive calls. So what happens here is this array comes to know that in the smaller part of the array it is present at 0th index. So this array actually says I will return 0 plus 1 to my parent. So basically this bigger array comes to know that in this smaller part of the array the 7 is present on the first index. Okay, so this array returns 1 plus 1, that is 2, to the parent. Parent is main. Okay, so parent is main. So what actually happens is, so here you will get the answer as 2. Okay, and you can see this occurrence is nothing but 2. And suppose in the worst case, if the 7 is not present, so let's say the elements are 1 2 3. Okay, so 1 says okay, I'm not 7, I make a call on 2 3. 2 says I'm not 7, I make a call on 3. 3 says I'm not 7, I make a further call on an array in which no elements are present. So n becomes 0 here. Okay, so as n becomes 0, we say return -1. Okay, so 3 knows that if the next function returns -1, I have to return -1. So 2 3 knows if the next function returns -1, I have to return -1, and 1 2 3 knows if the next function returns -1, I have to return -1. Okay, so this case is really very important to see. If the 7 is not present, then we will just skip it. Okay, so some of you might not think this way, some of you might think it the other way. Let's also write one more function to do the same work but in a different style. Okay, so let us write linear search function in a different style as well. Okay, so let's say we have int linear search, we are getting this array A, and suppose you do not want to worry about, okay, what value should be returned, so you just want to take an index I and you want to check if the element is present at index I have to do the work. Okay. Okay, so basically I'm going to convert the iterative linear search code into a recursive code here. Okay, so in iterative linear search you do something like this: you go from I equals to 0, you go till I less than n, I plus plus, and here you put a check. If this array of I equals to key, you return this index. Otherwise, you see, if I equals to n, you say the element is not present and you return -1. So same thing we can actually do recursively. So let us first think of the base case. Okay, so in the base case you can say if I is equal to n, so I is the index of the current element, so we are taking another variable explicitly to denote at what index we are currently working at in the array. Okay, so if I equals to n, if I crosses the last element, that means it's not present. Okay, so let me tell you what we are doing. Okay, so recursively I say, okay, check at this particular value of I. If it is not true, I go to the next, I make a recursive call on the smaller part with the increased value of I. If this is not true, I make a recursive call on the smaller part. If this is not true, that means 7 is not present, I make a recursive call. And if I becomes equal to n, that means we have to propagate -1 to the parent. So that's my base case. Okay, otherwise in my current case, okay, recursive case would be you first check at the current position. If array of I equals to the key that you're looking for, that will be equal. In that case you can simply return I. Okay, so now you are going to increment the value of I. So this I will store the exact index of the 7 with respect to the original array. Okay, otherwise we can say return linear search. We will not change the base address of the array, but we will just increment the value of I plus 1. Okay, and we will not change n, we will just change the value of I. Okay, so this code is more like a for loop. We have converted a for loop into a recursive code. Okay, so generally for loop is a better way. It's more efficient because it does not take up stack memory, but I'm just telling you how you can convert a loop into a recursive code. Okay, so this is your basically update part of the loop. This is basically your stopping criteria of the loop, and this is basically the if condition that you put inside the loop, that if array of I equals to key, you return I. So if your array is 1 2 7 and 3, in the first call you check I is 0, you just make a call on the next part, so you give this entire array and you see if array of I equals to 7, I is 1, it's not, you make a call on the next part, you say okay, this is 7, I equals to 2 is 7, so you return I. Okay, so I equals to 2 is returned here, from here you return I equals to 2, from here you also return I equals to 2. So that is what is the meaning of this statement. Okay, so if you do not find the element in the current index of the array, go and look for the element in the remaining part of the array. If that element is present in the remaining part, you will return some value of I. If that is not present, you will return -1 from the base case. Okay, so -1 will be propagated back from the base case. For example, if it is 1 3 4, you look in at this index, you're looking at this index, you're looking at this index, you're looking at beyond the array, it's not present, you return -1, so it goes back to the main via stack of recursive function calls. So this is another way of writing the same code and with the same time complexity. Okay, So I hope this is clear, and that's it. Hi everyone. So now we will discuss how we can find last occurrence of an element inside an array. Okay, and that is not sorted, so we have to do some kind of a linear search only, but we will build a recursive function. Okay, so some of you will obviously treat it as a very easy problem, and it is actually an easy problem. So let me give you one example. So let's say this is the array and you want to find out the last occurrence. For example, this index of the array is the last index of 7 present in this array. So one way is you start from this direction, you find out the first occurrence of the 7 from the right. But the way we are going to write the code is we are just going to again do a pass from left to right, and we are going to see how we can recursively find out what is the last occurrence of the 7. So the code is going to be similar to this function, but it will help you understand recursion better. That's why I'm going to take up this problem and discuss this particular approach while going from left to right. Okay, so let us give quickly revise what we did in the first occurrence. In the first occurrence, we actually checked if a of 0 contains key. We do not check for the next part. Okay, for example, if this is the array 1 2 7 3 something something something, we just make recursive call up to this particular point and we return 0 from here, we return 1 from here, and we return 2 from here. So we do not go into the remaining part of the array, but here we need to actually find the last occurrence of the array. So that means we need to go deep inside the array up to the maximum depth we can. So that maximum depth will be the entire array. Okay, so let us see. Let's break down this problem so into sub problem. So we make a call on the smaller sub problem. Okay, and at every point I'm not going to check whether the current index contains 7 or not. So first I will make a recursive call, go and find a 7 in the remaining part of the array before looking at the current index. So we make a call on 7376. From here we make a call on 376. From here we make a call on 76. From here we make a call on 6. From here we make a call on a null array. Okay, so this array says number of element is 0, 7 is not present, it says -1. Now you check at the current index. So is 6 equal to 7? It's not, so you return -1. Here you check at the current index. Is 7 equal to 7? Yes, so you return 0 because this 7 is present at the 0th index of this array, so you return a 0. Now this array comes to know the value that is returned by the sub array is not equal to -1. That means we found a 7 in the smaller part of the array. Okay, and so this will actually return index plus 1, so it will return 0 plus 1, that is 1. And similarly this comes to know that in the smaller part of the array 7 is present at the first index, so I should return a 2. So with respect to this as a base, so this index is 2. And similarly this function, this array comes to know that it's present in the second index in the smaller array, so let's return 2 plus 1 3. And similarly this returns an index 4, so you can see this index is actually 4. So this is how we are going to proceed with the code. So what you need to do, do not look at the current index, first make a call on the remaining part. Okay, first you will make a call on remaining part. So we are going to do opposite of this thing. So here we were first looking at the current index, then we made a call. So in this case we'll first make a call and then we will make a check at the current index, and if the call says 7 is not present and the check says 7 is not present, then we will return -1 in that case. Okay, so let us quickly write the code. So there would be base case. The smallest possible case would be if there are 0 elements in the array. Okay, so that means if n is 0, we can return -1. Okay, so otherwise in the recursive case, what we need to do, first make a call. Okay, so we can say last occurrence or index that is going to be given by the last occurrence function in the remaining part of the array. So remaining part is start from a plus 1, contains n minus 1 elements, and the key is key. Okay, now you can check if this I is equal to -1. Remaining part says I could not find an occurrence of 7. So what you will do, you will check for the current part. So if a of 0 is equal to key, that means you got a 7 at the 0th index, that means you will return 0 from the current sub problem. Okay, but if this is not the case, if the remaining part says element is not present, the current part says the element is not present, you will return -1. Otherwise, here here you will come, if I returned by sub problem is not -1. Okay, so in that case you will return I plus 1, because in the smaller sub problem, if the index of 7 is I, then in the current problem the index of 7 will be I plus 1. So that's what you do at this particular point. Okay, so this is the complete code for the last occurrence, and we can also test our code. Okay, so we have this 7 which is present at the 7th index, and the first 7 is present at the 3rd index. So let me just run this code. You can see we are getting this answer as 3 and 7. And also what we can do is we can just remove all the 7s and we can test our code again. So you can see we are getting both first and the last occurrences -1. That means 7 is not present. Okay, so there can be multiple ways to write this function, but I showed you a recursive way of thinking through this problem, and you can write code any way you like. Okay, so you can also use this kind of a notation, this kind of a function if you want to build, but this was taken up to make you understand recursion in a more better way. Hi everyone, so now we are interested in writing a function that finds and prints all occurrences of the key in the given array. Okay, so now you want to find out, okay, print all index of 7 present in the current array. So these are the indexes that you want to print. So I am making it a void function because we are just going to print the occurrences. So we will also take another variable I that denotes the current index that which we are currently standing, and we will just do some kind of a linear search that we have written in the earlier case also. Okay, so what we will do, so we will have a base case. So we say, okay, if we have reached till the end of the array, we will just return. So if I equals to n, we do not need to do anything, we will say return. Otherwise we can check if the current index contains 7. So if a of I equals to key, then we can just print it. We can say cout I. So this is one occurrence. Otherwise you simply skip it and go to the next index. Okay, so regardless of current index contains 7 or not, you just need to make a call on the remaining part of the array. So the remaining part of the array is A. It starts from the index I plus 1, it ends at index n, and the key is key. That's it. Okay, so if I now just call this function all occurrence of array starting from index 0, array contains n elements and the key is key. Okay, so you can easily visualize what is going to happen. Okay, so it is -1 in this case, but let me make it as 7 and 7. Okay, so you can see 3 and 7 both can be extracted from a same function as well. Okay, so this code I think you must be able to understand. It's a very easy, we just converted a loop into a recursive call. Okay, and now we will write one more function which instead of printing, it will store all occurrences of the array in the another array. Okay, so we can say void, or let me say int, let's take it as yeah. Okay, so let me write another function as int store occurrences. Okay, so what this function will do, it will count the occurrences of that particular key in the array, and it will also store them in a different array. Okay, so let me take another array. Let's call this array as output, and let's take another index as j. So what I actually want is, suppose your input array is like this, 1737. So I want to create an output array in which you are storing the occurrences of the 7. So one index is this and one index is this. So I want to store 1 and 3 in this particular array. So I will use the variable I to iterate over this array, and I will use a variable j to iterate over the output array. Okay, so this is my input A and this is my output A. So we will make this array outside the recursive function, and we will also return the size of the output array from this particular function. Okay, so this is sometimes these type of questions, these type of concepts are used in some more problems like subsequences and all. So that's why we are discussing this problem here. Okay, so what we can do, we can take another array that's called as output. We make it as, let's say, of size 100, and we can say the size of the output array, the number of occurrences of 7 that are stored, that is given by store occurrence. And here you pass in the array, input index I is 0, n is n, key is key, output array is output, and j is also 0. So initially you start filling this array from the 0th index. So initial value of j is also 0. Now can you think of a base case? Okay. So in the base case, it would be if I equals n, that means you have reached till the end of the array, you can return the size of the occurrences, that is going to be 0. Okay, this should not be 0. Let me tell you what it would be. It would be j plus 1. Okay, so let's see what we are going to do. Okay, so suppose this is your input array which contains 1 7 3 7 6. Let's say these are the elements, and this is your output array. Okay, so j is 0. So you traverse this array from this index. At ith index you do not find the 7, so you do not do anything in the output array. You make a call on this part. At this index you see there is a 7. Oh, there is a 7, so you put the ith index in this array. So I is 1, so you put I1 here and you increment the value of j, and you make a call on the smaller part of the array. So you see a 3 here, you do not do anything, you make a call on the other part of the array. So at this part of the array you see there is a 7 here, you put the index, that is 0 1 2 3 3 here, and you make a call on the smaller part of the array. At 6 you see there is no 7 here, you make a call on the smaller part of the array. This is the case when I is equal to n. So at this point you need to return the value of j. Okay, so j is let's say, yeah, so j is initially 0. So when you put the first index, j comes here. When you add the next 7, j comes at this particular index. So you need to return the j. So j is going to have value 2. So from here you will return the value of j. So j basically denotes the count of elements that are stored in the output array. Okay, so it should be return j. Otherwise what you need to do is you need to make a call. Okay, so let's see, if array of I, if this contains what, if this contains key, then what you will do, you will say output of j will store the index I. Okay, and or let's say out of j will store the index I, and you will make a recursive call on this further part of the array. So that will be store occurrences, and from here you can say it will be I plus 1, n, key, output, and j will be incremented as j plus 1 because you are storing some count here. Okay, so you can simply return this. Okay, otherwise what you can do, you can simply return store occurrences if this is not equal. Okay, so if array of I is not equal to key, so in that case you do not need to do this step. So you just make a call on the remaining part of the array without changing the value of j. Okay, so here j remains unchanged. Okay, and here you increment the value of j, increment j to accommodate current occurrence. Okay, so from here we will get the count, and what we can do for int k equal to 0, k less than count, k plus plus, we can simply say cout output of k. And here we can print the count as well. So this should be ARR. Okay. So we can see count is 2 and we are getting 3 and 7 in the output. So let me tell you what we have done here is, so let's just dry run this code for a small example. Okay. So let's say we have 1, 7, 3, 7 and 6. Let's say we have 5 elements. So we take a variable I that is initially 0. We also take another output array and we take a variable j that is also 0. So we see, okay, if I is equal to n, this is not the case. We come here, we say if a of I is equal to key, it's not the case. So we make a call on the remaining part of the array from I plus 1 to n. Okay, from I plus 1th index to nth index. And we say, okay, whatever is the occurrences of 7 in this part of the array will be returned this part. So that is true. So in this part there are 2 7, so the final answer will be 2. That's for sure. But what happens? How do we compute the answer is 2? So we say, okay, we come to this index and we see if this is 7. So yes, it is 7. So what we say, output of j equal to I. So we put I here. We put this index. So this index is what? This index is 1. So we put a 1 here. Okay, and we make a call on the smaller part of the array. And we also say, okay, whatever is returned. Okay, so we make a call on the smaller part of array. We see there is a 3. We do not do anything. We say, okay, the value of j is returned by this part of the array. Okay, so we will understand each and every step, so don't worry. So when we come to 7, we say, okay, this is 7. So what we do, we store 7 here. Okay, and we make a call on the next part of the array. So j is now 1 and j will be now 2. Okay, so when you put this value, j becomes 1, and when you put 7, j becomes 2, and you make a call on 6, nothing happens. You make a call on null, nothing happens. From there you return the value of j. Okay, so once you finish this entire input array, you actually return a value of 2. Okay, so that 2 is propagated back. Okay, so 6 says I have filled 2 arrays in the output. So 7 says there are 2 j, there are 2 occurrences of 7. So this 2 is propagated back from the every call to the main, and when the main sees the output array, you get the occurrences. Okay, so this occurrence is 0, 1, 2, 3. So this should be actually 3. Okay, so this is how we build this particular code. Okay, so I hope it is clear, and you can try running it yourself also. It's not very difficult, but it's just another way of writing this function. Okay, so we are just writing this function where we are storing the occurrences as well. Okay, so more or less it is same. Hi everyone, so in this video we will discuss how do you compute power function. Okay, you want to compute a raised to the power n using a recursive function. So we will discuss two approaches. One is the basic approach and second is the optimized approach that I call as fast power. Okay, so let us first discuss the basic approach. In the basic approach, we can break down this recurrence into a multiplied by a raised to the power n minus 1. So if you want to compute f of a comma n, that can be written as a multiplied by f of a comma n minus 1. So this will be our recursive case, and we can say if n is 0, we can say return 1, because whatever is the value of a, if a raised to the power 0 is, if this is what we do, then the answer should be 1. Okay, so that's what all we have to do here. So we can simply say return, uh, we can say if n is 0, we can say return 1, and in the recursive case we can say return a multiplied by power of a comma n minus 1. So that's pretty easy. I think you will be able to try in this code. And also you can see, if we talk about call stack, the depth of the call stack, it would be equal to n. For example, if you do a raised to the power 5, so in here you start with the value of a and n is 5, then you make a call on n equals 4, make a call on n equals 3, you make a call on n equals 2, you make a call on n equals 1, you make a call on n equals 0. So this returns 1. So here it is multiplied with a, here it is multiplied with a to get a square, here it is multiplied with a to get a cube, here it becomes a cube into a4 here, and here it becomes a4 into a, that is a5. Okay, so this is what happens in the call stack, and you can obviously see the maximum depth in the worst case is order of n, and also the time complexity of this method will be order of n. But we can do it in a better manner by choosing a sub problem that is basically in terms of n by 2. Okay, for example, if I want to compute a raised to the power n, I can say this can be written as a raised to the power n by 2 and square of this term if n is even. Okay, and if n is odd, then again I just have to multiply this answer with a if n is odd. For example, if let's say you want to compute a raised to the power 9, then this can be written as a multiplied by a raised to the power 4 and square of this term. Okay, so a raised to the power 4 is a smaller sub problem. If this is of the size n, this is of the size n by 2. And similarly, we can break this into a square and square of this term, and we can break this into a raised to the power 1 into square of this term. We can break this into a multiplied by a raised to the power 0 and square of this term. Okay, so this term is going to be 1, so this will return a, so this will give me a square, and once I know the value of a square, I can get a4. Once I know a4, I can get a8, and I multiply it with a to get a raised to the power 9. So if you see the depth of call stack in this case, so you're reducing your problem from n to n by 2, then to n by 4, and finally up to the value of n will become 1. So if you just count the number of steps needed to convert n into 1, so you will find that these steps will be log of n to the base 2. So we can drastically improve our solution that runs in order n time to order of log n time. Okay, so if you're not familiar with these terms, space and time complexity, you can watch out my section on space and time complexity as well, but it is just related with the number of operations, number of memory frames we are using to execute this code. Okay, so let us optimize this function to make it faster. So we can say if n is 0, we can say return 1, that will remain same, and here the recursive case will now we will change. Okay, so we will check if n is odd, so we can use bitwise operators to see if the last bit is 1, that means n is odd, and we can first compute the answer for the smaller problem. So I can say the sub problem or the smaller answer, that will be nothing but fast power of a comma n by 2. Okay, or you can say n right shift 1, that is also fine, and you need to square this answer up. So I can say smaller answer should be multiplied with itself, so I get the square. And if n is odd, then what we need to do, we need to multiply this smaller answer with a itself. If it is not, then the smaller answer is the bigger answer itself. Okay, so let me show you what I have done. A raised to the power n is a multiplied by a raised to the power n by 2 square if n is odd, and it is a raised to the power n by 2 square if n is even. Okay, so this is what I have done. I compute smaller answer. Smaller answer is nothing but a raised to the power n by 2. That is done using recursion. I square this answer up. Now some of you will code it like this. Some of you will do something like this. Smaller answer is faster power of a raised to the power n by 2 into fast power of a n by 2. This is how you will square it up, but this is an inefficient way of doing it because you are making two recursive calls. Okay, from, let's say, if you want to compute a raised to the power 8, you are saying, okay, go and compute a raised to the power 4, go and compute a raised to the power 4 again, and from here you make a call, go and compute a raised to the power 2, 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 and this will further make a tree like this. So this is going to take more time, it's going to be more inefficient. So what you can do is, from a raised to the power 8, you can say, okay, compute a raised to the power 4, whatever is the answer, store it in small answer and multiply this answer with itself. Okay, so you do SA into SA into SA. So this gets multiplied by a raised to the power 4 to give you a raised to the power 8. Okay, so this is not the way you should write this code. You should write it like this. So you square it up. If it is odd, you multiply it with a. If it is even, you just return this particular answer, and this is how you will compute the answer. Okay, so let's take few examples. Let's say a n, you do scene a and you do scene n, and here you can say C out fast power of a comma n and l, and here you can do C out power of a comma n and l, and let's try to run our code. Let's say 5 raised to the power 4, 625, 2 raised to the power 10, 1024, running perfect. So you can see answer is same for both, but this code is much more efficient, okay, in executing, both in terms of time, both in terms of memory as well. Okay, so now if you want, I can do a small dry run on this call stack as well. For example, let's say you want to compute 2 raised to the power 10, a is 2, and let us say n is 8. Okay, so you make a call in which n is 4. From here you make a call on n equal to 2. From here you make a call on n equals 1. From here you make a call on a to n equals 0. So firstly, this frame will get evaluated, because you can see all of this code is written after the function call. So first we will go towards the base case. So this hits the base case, the value of n is 0, it says return 1. So we get the answer for a raised to the power 0 as 1. And when the answer is 1, we square this up. So 1 square is 1. We multiply this with a. So a is a, whatever is it is 2. So we get this answer as 2. Okay, so a raised to the power 1 is 2. So we get this answer here. And what we do, so once we come in this function call, we see that answer for a raised to the power 1 is going to be 2, and we just square this answer up. So we square this answer up, we get 4 here. And what we do, we see if n is odd, we multiply it with it, but if it is even, we return the small answer. We return this answer 4 here. Okay, so once this answer comes here, we first square it up. So this answer becomes 16. N is even, we just return this answer. We come here and you can see what we do. We see n is even, we just first we square this answer up using instruction number line number 19. We say it becomes 16 into 16, that is 256, and we see n is even, so we do not multiply it with a, we just return this answer. So 2 raised to the power 8 is actually 256. Okay, so this is how we get this particular answer, and I hope this one is now clear to you. Hi everyone, so in this video we will discuss how to implement bubble sort recursively. Okay, so let me give you a quick recap of bubble sort. For example, if your array contains these elements 5 4 3 1, what do you need to do? So in the very first step, your idea is to take the largest element to the end of the array. Okay, so you start doing pairwise comparisons. So current element gets compared with the next element, so it becomes 4 5 3 1. Then you compare 5 with 3, it becomes 4 3 5 1. Then you compare 5 with 1, it becomes 4 3 1 5. So this is what happens in first pass of the entire array. In the second pass, you again start from the beginning of the array, and in this pass you again do pairwise comparisons. And what happens is the second largest element of the array goes to the second last position. So you compare 4 and 3, it becomes 3 4 1 5. You compare 4 and 1, it becomes 3 4 3 1 4 5. Okay, and you can see now two elements are sorted from the end. In the third pass, what you do, the third last element or third biggest element moves to the third last position of the array. Okay, so you have 3 4 3 1 4 5. So you compare 3 and 1, it becomes 1 3 4 and 5, and this part of the array becomes sorted. So basically, to sort the entire array you need to do n minus 1 passes, and in each pass what you do pairwise comparison of the elements from starting. Okay, that's what you do. And if the current element is bigger than the next element, then you swap the two adjacent elements. Okay, so firstly we will write this logic using recursion plus iteration, and in the next step we will convert this entire code into a recursive code. Okay, so let us say void bubble sort is a function, and here we get the array, and we also get the number of elements in the array. Okay, or you can just write it like this. So we will discuss what is the base case and what is the recursive case, and before that let's build the main as well. So let's say you have this array which contains some elements, let's say 5 4 3 1 2, and you have n equals to 5. And okay, let's think about base case and let's think about recursive case. So in the base case you can say that if the array contains only one element, then it is always a sorted array. Okay, that what you can say. Okay. So if you have something like this 5 4 3 2 1, so after the first pass 5 goes to the end, 5 4 3, sorry, this becomes 4 3 1 5. Okay, so 5 goes to the end, so you have an array of n equal to 4 elements. Here you can say you have an array of n equal to 3 elements that you need to sort. And then what you need to do, you can further reduce it to a case where 4 goes to the second last position and you are left with 3 1, and you can say 4 and 5 are already sorted. So the length of the unsorted array becomes 2, and you further reduce it to the case where it is like this 1 3 4 5. Okay, by doing a pairwise swapping across the array. So here the length of the element is 1, so the length of the unsorted part is actually 1. So something similar I'm going to do. I'm going to say n equal to 4. We will pick the bigger element and put it to the last, and then we will pick the next bigger element, put it to the last, and so on. And in each call we will reduce the size of the array. Okay, so we will make a call on this unsorted part of the array to sort it using recursion. So that's the whole idea that we are going to implement. So in the base case we can say if we are left with only one element in the array or in the unsorted part, so we can simply return. Otherwise, in the recursive case, I can say I will take a variable j. J goes from 0. J goes till before the last element. So last element is n minus 1. J plus plus. You compare the current element with the next element. So if a of j is greater than a of j plus 1, then what you do? You just do the swapping. So you do swap a of j and you swap a of j plus 1, and you can recursively call bubble sort on the smaller part of the array. Okay, so smaller part of the array is a comma n minus 1. So that's it. So you can see generally when we implemented using iteration, we use two loops. So here we had the inner loop from the iteration, and the outer loop we converted into a recursive call, and this loop will run n minus 1 times. Okay, from starting from n till the 1. So let us dry run this code if you want. So let's see if we have 5 4 1. So what we do, in the first step we start from j equal to 0, we go till this point, and let's say 1 and 0, we go till this point and we do a pairwise comparison. Okay, so it becomes 4 5 1 0, then we compare 5 and 1, it becomes 4 1 5 0. We compare 5 and 0, it becomes 4 1 0 5. So this is what happens after the for loop. And in the recursive call, what we do, we say okay, sort this array A whose length is n minus 1. So we send this array for sorting. Okay, 5 is already there, so we do the same thing. It becomes 140, it becomes 104, and we stop at this particular point. So n is here 0 1 2, so we just go till this point. Okay, we just take the value of j till this point, and j plus 1 is 0. So we now make a call on this problem. So this problem is 1 0. We just run the loop till this index only, so it becomes 0 1, and we already had 4 and 5 in the correct positions. So this is how our array gets sorted. So in each recursive call, you are reducing the size of the array by a factor of 1. Okay, so this is basically to sort the first n minus 1 elements after you have moved the largest element in the current part to the end of the array by pairwise swapping. Okay. Now our next step is to even reduce this for loop. We don't even want to use this particular for loop. We want to convert this into again a recursive code. Okay, so we would be writing another function, bubble sort, let's say completely recursive without using any for loop. Okay, so just for practice, so that you are able to understand recursion in a more better manner. So firstly, we need to think what variables we need to take. Okay, but let's see what happened here. So here, generally when you write an iterative version, you use two loops. One loop controls the number of times the inner loop should execute. Okay, so the inner loop is same as this one, and the outer loop is basically controlled by the recursive call in this case. Now what we want to convert this loop into recursive call. Okay, and when this loop is running, we keep a variable j to denote at what index we are doing the swap operation and how many times we should do it. So here if we do not use a loop, we need to keep this variable j in the function call itself, so that we know at what index we are currently working at. Okay, and in order to use this variable I'm using this variable n. Okay, here, so n basically controls how many times the internal swapping logic should execute. Okay, or how many passes we should do for the complete array. That's what is the role of n in this case. Okay, so we will have the array, we will have the variable j, and we will have the variable n. Okay, so n controls the outer loop and j controls the inner loop, and we are not going to put any loop here. So firstly, we need to think of base cases. So both n and j are doing different work, and we will have two different base cases for both of them. So firstly is the same base case. If n becomes 1, we will return. That means our number of passes have been done and our work is over. So that means array has been sorted. Okay, and there would be a corner case for j as well. So what we will do now is, let's say initial value of j is, let's say 0, and you have something like this 5 4 3 1. So what you will do in the first call, you will just swap 5 and 4, that is j and j plus 1. So you will make a call on this part of the array. So j is at this index, it becomes 4 5 3 and 1, and j comes to j plus 1. Okay, so j becomes j plus 1, and you say okay, do the swapping in the remaining part of the array. Okay, and then you again make a call, you say okay, do the swapping in the remaining part of the array. So it becomes something like this 4 3 5 1, j comes here, and you say okay, do the swapping in the remaining part of the array. So it becomes 4 3 1 5, and at this point j becomes equal to n minus 1, and you do not have any other element in the front of 5 with which you will compare this thing. Okay, so we are not going to put a for loop, but in every call we are going to update the position of j to the next index. Okay, so what we will do, we will say if j points to the last element, okay, That means you have done single pass of the current array, and in that case you will perform bubble sort on the array starting from the index 0. Okay, starting from the index 0, but the number of passes will be n minus 1. So this is what we are doing here. That means the internal for loop has ended. So this means this for loop has ended. So that is the condition. If j becomes equal to n minus 1, you have to make this call. So in this call, when you make this call, the new value of j will be 0. It will start from the beginning of the array again. Okay, has been done. Otherwise, if the pass has not been done in the recursive case, what you need to do? You need to check if aj is greater than aj plus 1. Then you do the swapping and make a next recursive call. Okay, so that means you do the swapping with aj and aj plus 1. So those elements get swapped, and you make a call on bubble sort recursive. So here it should be bubble sort recursive, and here it should be bubble sort recursive. And what you need to do, you need to make this index as a comma j plus 1 and n. So here you do not modify the value of n. The number of passes will not change in this case. Okay, so now some of you might find it tricky to understand, so let me clear out those confusions as well. So we had a loop of I, okay, and we had a loop of j. Okay, so the outer loop controls the number of passes, so that is this n. Okay, so it runs from n to 1, so that means it is running n minus 1 times. And inner loop basically does this comparison. If aj is greater than aj plus 1, then we do the swapping. So here you can see what we are doing is, suppose you had this element, you had this array 5 4 3 1. So you're doing okay, j is, let's say, 0. So this case is not executed, this case is not executed, n is 4, and j is not n minus 1. So you basically do this comparison, so it becomes 4 5 3 1, and you make a call on this array. So again, only this case is going to get executed because aj is greater than aj plus 1. You do the swapping, it becomes 4 3 5 1, and you make a call here. So in this call you do not change the value of n because your pass is not complete. Your pass through entire array is not yet complete. So you just increment the value of j and you do 4 3 1 5, and at this particular point you see the j has reached a value of n minus 1. So that is, now you are going to hit the base case. So what you do, you say bubble sort recursive, sort this array recursively, okay, with n minus 1 elements. So this array is now going to have n minus 1 elements, and you start from an index of 0. So j now gets an index of 0. So j gets reset to an index of 0. Okay, and now this loop will run again how many times? It will run 2 more times. Okay, so it will be, you compare 4 with 3, so it becomes 3 4 1. You compare 4 with 1, so it becomes 3 1 4, and again the value of j is now equal to n minus 1. The value of n is 3, so j is 2. So you again make this recursive call. Okay, so that means you give this smaller array 3 and 1 to the recursive function where the value of n is 2 and j is 0. So you again do a comparison. So 3 gets compared with 1, it becomes 1 comma 3, and the value of j is equal to, let's say, 1, which is just 1 less than n. Okay, so it's equal to n minus 1. So you hit this case again. So in the last case, the value of j is 0, the value of n is equal to 1, and you say return. So when you return, and if you see the state of the array, it is 1 3 4 and 5. So that means the array gets sorted. So this is how you build the bubble sort.
Friends, we are talking about merge sort, a very popular sorting technique. And let us see what all steps are involved in merge set. So you are given an array. Suppose this array contains some elements like these. So the first step in the merge sort is that you have to divide your input array into two parts, right? So it is a divide and conquer algorithm. The first step is we divide our array into two parts, and these parts are about the midpoint. So we are going to separate our array of size n into two arrays of the sizes n by 2. So the first array becomes 5 6 1, and the second array becomes 2 4 0. This is when we have divided our array into two parts. Let's say this was the starting point, this was the ending point, and let us say this was the midpoint. So one part is from start to mid, other part is from mid plus 1 till the end. The next step is to recursively sort these arrays. So we can say that we have a recursive function merge sort which recursively sorts these arrays, and this array becomes 1 5 6, and this array becomes, after sorting, as 1 2 and 4. So this is the second step. So first step is divide, second step is to sort, and the third part is to merge. And we know it is quite easy to merge two sorted arrays using a two pointer approach. So what we do, we can simply say that we will keep two pointers. Let us say there is a pointer I which points at this position, and there is a pointer j which points at this position. So we compare which the element is smaller. Sorry, this element is 0. So this element is 0. We say which element is smaller. So we can know that out of 0 and 1, the 0th element is smaller, and I keep a third pointer k here. So whichever is smaller comes to this place. 0 comes to this place. So j moves a step forward. Now we will compare element 1 with element 2. So we know that 1 is smaller, so 1 will come to this place, and our I pointer will move one step forward, so I comes to this place. Now we will compare 5 and 2. I know that 2 is smaller, so 2 comes to this place, and our j pointer moves one step forward. Now out of 5 and 4, I know 4 is smaller, 4 comes to this place, and j moves one step forward. Now since j has already crossed the ending point, or we can say that this array has been exhausted, we do not have any elements in this array which can be compared with the elements of this array. So what we do, we directly copy all the elements till I also reaches end into this array. So we will copy here 5, and we will copy here 6, and I also reaches the end of the array. So this is how we finally get a sorted array. So this is the idea of the merge sort. We will first try to write the same thing into the code, then we will do more analysis how recursion is actually working over this array. So let us get started with the coding part first. So in the merge sort, since it is a recursive function, we are going to have a base case. So the smallest array that we can sort comprises of one element. Let's say I'm getting the starting point of the array, and I also get the ending point of the element. So if there is 1 or 0 elements, then we do not need to sort them. So I can say if start is greater or equal to end, then you can simply return, because you do not need to sort an array containing a single or a no element. Otherwise, you have to follow 3 steps. The first step is to divide. To divide, we need to have a midpoint. Midpoint is nothing but start plus end upon. This gives you the midpoint. Then you have to recursively sort the two arrays, and The first array starts from S and goes till mid, and second array starts from mid plus 1 and goes till end. So you can call merge sort over the two parts. First part is array starting from the S going till the mid. The second part is starting from the mid plus 1 going till the end, and that's it. And the third step is you have to merge the two parts. So let us write the merge function. So in the merge function, what I will get a array. I will get the starting point and I will get the ending point as well. Midpoint can be computed again. So let us first compute the midpoint. Midpoint is nothing but start plus end upon 2. And we now need to keep 3 pointers. So I is at start, j is at mid plus 1, and k is also at start. This is what we need to do. And I take a temporary array which I use to store the combined result after merging. So what I have done is I have taken 3 pointers. One pointer is start, one pointer is I, which points at start, one pointer is j, which points at mid plus 1, and another pointer is k, which points at the starting of a temporary array. This is the temporary array, and finally after merging the result in a temporary array, I'm going to copy back this array into the original array. So we are going to make original array A equal to the temporary array, because this is A, this is also A, and this is temporary array. When the final result is known, we are going to copy the result back to our original array so that the actual array is sorted in place. So how do I compare? So I check while I is less than equal to mid and j is less than equal to end, I can compare the two elements. So if a of I is smaller than a of j, then I can say temporary of k will contain array of I. Otherwise, I can say temporary of k will contain array of j, because that element is smaller. And I also need to increment these pointers. So k plus plus, I plus plus, j plus plus, and again k plus. And this will continue when both of the smaller arrays have some elements. So let us once dry run again. So suppose if the elements are 1, 4, 5, 8, and here suppose the elements are 2, 7, and 10. So what I need to do, this is array A, this is also array A. So in the temporary array, I need to compare which element is smaller. Is AI smaller or is AJ smaller? And if AJ is smaller, I'm going to write temp of k plus plus. This is k. So here I'm going to keep the smaller of the two elements 2, and I'm going to do k plus plus. So k comes to this place and j comes to this place. And suppose the array is exhausted. So suppose that this array is exhausted. So I will write while j does not reach the end. Until all the elements are not copied, we will copy all the elements as it is. Or maybe this array has some pending elements like 18, 20. So I will copy all these elements until all the elements of the array are not exhausted. So I can say while I is less than equal to mid, you can directly copy array I. Or it is quite possible that j is not reaching the end. Then while j is less than equal to end, I will copy all the elements. This is equal to array of j plus. And finally, we need to copy all elements to original array. So I can say for int I equal to start, I less than equal to int I plus plus, and original array a of I will be equal to temp of I. So we are copying all the elements back to the original array. And here we go with the merge function. Let's say merge array a from start to. So this is the merge sort. Now let us test it. We have an array as input, and let's call the merge function on it, sorry, merge sort function on it. We give the array starting point is 0, ending point is n minus 1, and let us try to print all the elements. It's the array after. So I am giving 5 elements and I have to merge them. Let's run our code. So you can see after merging we got a sorted output. This is how the merge sort is working. Now let us try to break down how this is working at the smallest level. So let me draw the diagram again. So I have a array like this. The elements which I had taken are 5, 6, 1, 2, 4 and 0. So the first step is that we divide the array into two parts. So what happens is we divide this array into two parts. So the first part contains 5, 6, 1 and the second part contains 2, 4, 0. Now we say further divide this array into two parts, because what we are going to do, we are calling merge sort on this part. We are calling merge sort on the left part. If you carefully see, so this array becomes like this 5, 6 and the other part becomes 1, and in this direction we will go later after this part has been resolved, right? After calling merge sort on this part, this array should become 1, 5, 6. So now what happens is we call merge sort on this part, so it becomes 5 and it becomes 6. So for this smallest array, this is the left part, this is the right part. So basically we have called merge sort on these two. So since these two are only containing single elements, so our function will return from this point and merge routine will be called. So when we merge them, so it again becomes 5, 6. So this part is now sorted. The second half of this array is also sorted. Left part is sorted, right part is also sorted because it is a single element. The merge function will be called. When we merge these two parts, it will become 1, 5, 6. Now the left part is sorted of this array. It's time to call merge sort on the right part. When we call merge sort on the right part, the same steps will follow. So first we will divide it into two parts. It becomes 2, 4 and a 0. Again it will call merge sort on this. It becomes 2 and 4. Since it is a single element, it is sorted. So after merging it becomes again 2, 4. And for this array, the left part is now sorted. We need to sort the right part. Since it contains a single element, it is also sorted. So after combining, this becomes 0, 2, 4. So we can see clearly that the left and the rightmost parts are now sorted. After merging these two, what we will get Out of 0 and 1, 0 is smaller. Out of 1 and 2, 1 is smaller. Out of 5 and 2, 2 is smaller. Out of 5 and 4, 4 is smaller. And this array is now exhausted. So remaining elements, these elements will be copied here due to the loop we have used. This array will become like this. And finally, these elements are copied back to the original array, thus giving us this final sorted array. So this is our final sorted array. So what we did, we divided our array. We used sorting on a smaller problem. We conquered the smaller problem. That's why merge sort is also called a divide and conquer sorting algorithm.
Hi everyone, in this video we will solve one problem that's called inversion count. So I will first discuss the problem statement and then we will discuss the solution to this problem. Alright, so what this problem says that you are given an array like this, and let's say this array contains n equal to 6 elements. Okay, so you actually have to count number of pairs such that for any two elements of the array, let's say this is array I and let's say this is the jth element, that's called as array j. So let's say this index is j and this index is I. So you have to count the number of pairs such that ai is greater than aj for I less than j. Okay, so that means if an element is coming before the another element, but that element is having a greater value than the jth element. Okay, so I index comes before j and value of array I is greater than array j. For example, in this case, the 5 is located at the first index and it is coming before the element at the fifth index or the fourth index, and its value is greater than j. So 5 comma 3 will form one pair. Okay, similarly you can have more pairs. You can have a pair called 1 and 0, that is a pair. Okay, then you can have you can see 5 comma 2 is a pair, 5 comma 3 is a pair, 5 comma 0 is a pair. Okay, and you also have 2 comma 0 as a possible pair in this case, and you also have 6 comma 0 and you also have 3 comma 0. Okay, so the number of pairs in this example is 1 2 3 4 5 6 7. So you have 7 such pairs. Okay, so one brute force way is, so the brute force way is you use two loops, one to iterate over all elements I, and you use another loop to iterate over all elements which are uh, in front of I. Okay, from I equals to 0 to let's say n minus 2, and for j equal to I plus 1 to n minus 1. Okay, you can check if array I is greater than array j, then you can do something like count plus plus. Okay, but this will obviously take a complexity of order of n square, and we want to reduce this complexity. Okay, so what we will do, we will try to come up with a different approach. Okay, and let's try to use something of the form divide and conquer. Okay, let's try to apply if we can divide this problem into two parts and then we can solve this. Okay, so for example, if I say, okay, if I am given an array like this, the very basic way to divide the array is by dividing at mid. So I divide my array into two parts. Let's say this is the first part of the array and let's say this is the second part of the array. Okay, so suppose if I am able to count inversions from the first part, let's say the number of inversions in this part is called x, and let's say I am also able to count the number of inversions in this part by making a recursive sub problem. Okay, so let's see how many inversions we will have in this part. So it will be like 5 comma 2. There will be only one inversion in this part, that is 5 comma 2. Okay, how many inversions we will have in this part? So it will be two inversions, 6 comma 0 and 3 comma 0. Okay, and also 6 comma 3, that is also one inversion. Okay, so I think we missed this inversion here, so this should also be counted, so it would make 8 pairs. Okay. So what we need to do is, we have three inversions here and we have one inversion in this part, but we know the total number of inversions is actually more than that. Okay, because we are not counting those inversions in which the ith element lies in the first subarray and the jth element lies in the second subarray. Suppose somehow using recursion you are able to find x and you are able to find y, so you actually need to add cross inversions. Okay, so that means those inversions which are starting from the first part of the array and they are ending in the second part of the array. Okay, so that's what you need to find out. Now let us see how we can find out the cross inversions. Okay, so what we will do is, we will use something like a merge sort. So let's say, when you divide this array you also sort it. So when you sort this array becomes 1 2 and 5, and let us also sort this array and this becomes 0 3 6. Okay, now you may ask, why do we need sorting? Okay, so sorting is actually needed because when you are going to count inversions from that are the cross inversions, okay, starting from this part of the array and ending in this part of the array, sorting is actually going to help because we are going to use a trick. Okay, and as I go through the explanation you will also get an intuition why we are doing so. Okay, so also, doing sorting will not affect the count of x and y. Okay, so x and y will remain same because we have already counted how many inversions we have in this particular part. Okay, so after that we do the sorting and that is not going to affect cross inversions. Okay, so I'm making a statement here, sorting will not affect the number of cross inversions. So I hope uh, you agree with this statement. Okay, cross inversions. Okay, because if one element is from this part and another element is from this part, the relative ordering of these two parts still remains the same. So this part comes first and this part comes second. So let's try to merge these two arrays into one. Okay, so I make a bigger array that is going to have, let's say, 6 elements. Now you will do something like a merge function. You have a pointer I here, you keep a pointer j here, and you keep a pointer k at this place. So you compare 1 and 0. So you know, 1 is actually greater than 0. Okay, so 1 is actually greater than 0, and what you will do, you will copy a 0 here. Okay, so that also means, if you have a array element here that is ai that is greater than aj, that would also mean all elements which are greater than 1, because this array is a sorted array, are also greater than 0. Okay, so that would mean 0 will form 3 cross inversions with this array. Okay, so that means 0 will contribute 3 inversions with this array. So those inversions are 1 comma 0, 2 comma 0 and 5 comma 0. Okay, so 0 is making 3 cross inversions, 1 comma 0, 2 comma 0 and 5 comma 0. So that's where sorting is going to help us, because we actually do not need to check 0 with all other elements, and since 1 is greater than 0, so all elements which are greater than equal to 1 will also form cross inversions. So we directly add 3 to our answer. Okay, so whatever is our x and y, we will add 3 to that answer. Now we will see with we will move the j pointer to the next place and we will compare 1 and 3. Okay, now 1 is smaller than 3, so that means uh, we are going to copy 1 here, and 1 is not going to add anything to the inversion. Okay, so that means 1 will not form any inversions with 3 or 6. Okay, so now we will compare 2 and 3. 2 is smaller than 3, so 2 will also not contribute any inversion, so we will add a 0 to our answer. And now we will go to the next place. We go to 5. So 5 is actually greater than 3. Okay, so what we will do is we will add 3 here. Okay, we will copy 3 here, and all elements which are greater than equal to 5 will form a cross inversion with 3. That would mean you will have a cross inversion of this form 5 comma 3. So I move the j pointer to the next place, and now we have a comparison between 5 and the 6. Okay, so 5 is already there. Okay, we do not have any comparison and we have ended our array. So that would mean we will have okay, here we have 1. Right. So between 3 and 5 we pick the 3 and we add 1 cross inversion. Between 5 and 6 we will add 5, we will pick 5 and we will have 0 cross inversions, and finally we will pick 6. Okay, so that would mean you have 3 plus 1, that is 4 cross inversions. Okay, and what will be your final answer now? It will be x plus y plus cross inversions. Okay, that would mean x is 1, y is 3, and cross inversions is 4. That's how you will get 8 inversions. Okay, now you may ask, how do we get the value of x and y? So that we will see once we write the code, and I will try run it again. Okay, so that's what we are going to do now. Okay, so let's get into the code, and let's build a function that will actually help us to count the number of inversions. So let me start by typing in some code. We will have the main part now. Okay, and in the main we will have this array. Okay, let's make a function called inversion count, and that will get the array from this to this. Okay, and here we will do something of the kind merge sort. Let's say int inversion count, that's where we will get the array. We will get the start and we will also get the end. So we can have a base case if you have a single element in the array or 0 elements, you won't have any inversions. Okay, so you can say return 0 if start is greater than equal to end. Okay, no inversions if you have a single element. Then you do something like a merge sort. You have you find out the mid, that is start plus end by 2. You find the number of inversions in the first half, let's say that's called x, and you make a call to inversion count, and you give array start and the mid. You find out y, that's given by inversion count. You give array mid plus 1 and end. And finally you also need to count the number of cross inversions that would be given by the merge function. Okay, so we'll write a merge function that will give us how many cross inversions we will have, and we will return the final answer, that is x plus y plus z. Okay, now you can see this is the divide step, and here we are combining the sub problems. Okay, by merging that array. Now let's write the function to merge the two parts of the array. That's, we get the array, we get the starting point, and we also get the ending point. So let's compute mid, that is start plus end by 2. We will have a pointer I that will point to start. We will have a pointer j that will start from mid plus 1, and we will have a pointer k that will start from s. Okay, and we also need a temporary array so that we are able to uh, merge the two parts into this array. Okay, so I'm making a variable count that is going to count the cross inversions for this particular problem, and here we will do the merging step. Okay, so while I is less than equal to mid and j is less than equal to end, I can check what is going to happen if ai is less than equal to aj. Okay, then I can say in temp of k add the element I, and you can do k plus plus, and you can also do I plus plus. Okay, otherwise if ai is greater than aj, so this is the most important step here. So that's the only change we will have. So if ai is greater than aj, what we need to do is we also need to copy in temp of k array of j, and we will increment the pointer, and also count will be incremented by mid minus I plus 1. So let me explain you this particular step. Okay, so let's say you have something of this form. Okay, let's say you are at this particular point 5, and you have 6 7 8, and in this array you find an element that is ai is greater than aj. Okay, ai is greater than aj. So let's say you find the element 2 at this particular point. Okay, so you're comparing ai, that is this element, with this particular element aj, and you're at this particular index k. So you want to suppose this part of the array is filled, and for this part we have already done the work. So if 5 is greater than 2, that would mean 2 is going to form inversions with all elements which are greater than equal to 5. Okay, that's what I am saying. So effectively, how many elements you will have? So this index is mid. Okay, so how many elements you will have from the index I to mid index? Okay, so that is going to be nothing but mid minus these many elements. Okay, so that is mid minus uh, I minus 1. Okay, that is mid minus I plus 1. So with these many elements you are going to form inversions. So you increment the count by this factor when you're putting an element from this particular array here. Okay, so that's the only case where your count of inversions will increase by this factor. Okay, and this is actually why you will able to get a reduction in the time complexity as well. Okay, and also we will have to uh, fill the array if some elements are left in one of the arrays. Okay, so you can put a condition while I is less than equal to mid. You can say temp of k plus plus equals to array of I plus plus, and you can also say while j is less than equal to e, temp of k plus plus equals to array of j plus plus. So exactly one of the arrays might be non-empty, and you have to uh, copy the remaining elements also. Okay, now finally we will copy all the elements back to the original array a, like we do in merge sort. So for int I equals to start, I less than equals to end, I plus plus, we can say array of I equals to temp of I, and we will return the count from here. Okay, so that will give us the count. So this completes the implementation, and let's try to run the code. Right, so here we should take this array as a. That's it, and let's try to run the code. So yes, it is giving me the correct answer, that is 8, and I hope it's clear. So I will quickly dry run it once more so that you get an idea what we are doing at every step. Okay, So main part is this, and the other part is I have already explained. Okay, so let's see. Again, we start with this array: 1 5 2 6 3 and 0. So eventually what will happen is all inversions will actually come from the cross inversion count function, that is the merge function. So you divide it into two parts: 152 and 630. Okay, you further divide it into two parts, that's 1 comma 5 and 2, and you further divide this into two parts, 1 comma 5 and 2, and here it will be like this: 6 comma 3, sorry, 6, this should be combined, and 2 will be separate, and here you will have 6 comma 3 and 2 will be separate. Okay, so firstly you will merge these two. You say, okay, I merge them into a single array, that's 1 5, and you will have 0 inversions because this is already there. Then you will combine 1 comma 5 with 2, so that will actually give you 1 inversion because 1 is less than 2, so 1 comes here. 5 is greater than 2, so that will make 1 inversion, and then you will have this array 1 2 and 5. So you make this array, you find one inversion in this part. Okay, so the value of x is now 1. Then what you do, you go on the right and you try to combine these two. So since 3 is smaller than 6, you put 3 here and you increment your inversion by 1, so the value of 5 will be at least 1 plus something. So now you compare, you try to copy these elements. Okay, you try to merge these elements. So since 2 is less than 3, so that means 2 is less than all elements greater than equal to 3, so 2 will form two cross inversions, so this array will become 2 3 6. So you will increment this value by a factor of 2. So the value of x is now 1 and the value of y is 3, and you need to count cross inversions. Okay, so when you try to merge these two arrays, and I have already shown you, when you combine these two arrays you will get the value of z, that is the number of cross inversions, that will be equal to 4. Okay, so that will be plus, this is 1, this is 3, and this is 4, so this will be 1 plus 3 plus 4, that is 8. So this is how we are getting 8 cross inversions. So I hope this logic is clear and you would be able to solve such problems now. Hi everyone, in this video we will discuss quicksort, that is another sorting algorithm, and it's quite popular and it's widely used in libraries as well. Okay, so let's discuss the idea behind quicksort. It's a divide and conquer algorithm like merge sort, and it also runs in n log n time on average case, and the worst case complexity is slightly bad, but it can be fixed using a randomized quicksort, so n square in worst case. So I will come to it, why it's n square or why it's n log n, but let's first discuss what is quicksort. Okay, and one thing special about quicksort is it's a in place algorithm. That means it will sort that array in place without creating a new array, but still it may require extra space due to recursion call stack. Okay, so let's see what this algorithm is. So it says you take this array and it's like this. Let's put the elements 2 7 8 6 1 5 and 4. Okay, you will choose one element of this array as a pivot element. It can be either the first element or the last element. Okay, let's call this element as a pivot element, and what we will do now is we will divide the array in two parts. Okay, and these two parts will have elements. One part will have all the elements which are less than pivot. Okay, and second part of the array will have elements that are greater than pivot. Okay, so we will have elements which are less than equal to pivot, and we will have elements which are greater than equal to pivot. Okay, so it's pivot, greater than pivot, right? So what you do, you start scanning your array from left to right. Okay, so these are the elements that we need to divide around the pivot. Okay, we need to do something like this. We have 4, and before 4 we have all those elements which are less than pivot, and after 4 we will have all those elements which are greater than pivot. So if you look carefully in this array, you have 2 is less than pivot, and you have 1 is less than pivot, and you have that's it. And you have elements 7, 6 and 5. These are greater than pivot, and also yes 8. Okay, so 7, 8, 6 and 5, these are the elements which are greater than pivot. Okay, so the first step is to find out the pivot element and arrange the elements of the array such that you have 4 in its correct position, because if you put all the elements which are less than 4 below before 4, then 4 automatically comes in the correct position. Okay, and all elements which are greater than 4 are on the right, and all elements which are less than 4 are on the left. So this is the first step, and in the second step we do this partitioning. Okay, so this is also called a partitioning step. Okay, so once we have done the partition, the third step is to recursively sort the smaller parts. Okay, now this is a smaller array. Let's call it as A. This is a smaller array. Let's call it as A1 and let's call it as A2. So we will recursively sort these two parts. So recursively sort the smaller parts A1 and A2. Okay, so let's say this index of the partition is P. So that would mean you will sort the array A. Let's say this is array A. So that would mean you need to call quicksort on the array um, A from 0 or from the starting index till the P minus 1th index. And you also need to call quicksort on the second part of the array, that is A, starting from P plus 1th index till the ending index. So that's how we are going to solve this. Now, you know, when you're using recursion, the same thing will happen on the smaller part of the array. So you have this smaller part of the array, and if you want to sort it, what you will do? You will pick this as a pivot element. You will try to put 1 in its correct position, and you will put all elements which are greater than 1 here. So you will get this, and then you will get 4, and now you will call quicksort on this particular part of the array, and here you have elements 7, 8, 6 and 5. So if you pick 5, you put it in the correct position, so it will become something of this form: 5 followed by 7, 8, 6, and you will call on the left part of the 5 and right part of the 5. So the left part of the 5 is empty. Then you pick this part of the array, you pick 6 as the pivot element, you try to place 6, so it becomes 5 is 6, 7 and 8. Okay, so this is what you will get, and once you combine these two parts, you will get the sorted array. Okay, so these are the 3 steps that you need to do in quicksort, and now let's try to implement the code of this. Okay, so the most important step is the partition function, and we will have a look how we can partition the array. Okay, so let me write the code, and I will explain you the logic for the partition function side by side. Okay guys, so let's write the main, and let's write the quicksort function first. Okay, so let's say this is the array, the number of elements is given by this. We need to call quicksort, and quicksort, let's say, is with small q, and here we have array. These are the start and the end indices. Okay, so now I will write void quicksort. I will get the array, I will get the start, and I will get the end also. So what I need to do, I need to check for the base case, and I need to write the recursive case. Okay, so it's a divide and conquer algorithm. We will use recursion to help do the work, and in the base case, the smallest possible array will have a single element or 0 element. So if start is greater than equal to end, you say return, do nothing, because element with array with single element will be a sorted array. Okay, then in the recursive function, you first need to partition the array, and you need to know the index of the pivot element. So that can be done using a helper method that we can write, that's called partition. and we have array A, we have start, and we have end. Okay, so once we know the index of the pivot element that has been located in the correct position, we can recursively sort the left part and the right part of the array. Okay, so we need to make a call on quick sort array from start to p minus 1, and we also need to make a call on the right part of the array quick sort from p plus 1 to e. So now this is the main method that we need to see how we can write this function. So let's start writing the partition function. It will get the array, it will get the start, and it will get the ending index of the array. Okay, so the important thing is we have to do it in place. That means we cannot take extra array. Okay, so what I will do, I will keep two pointers. Let's say I have a pointer I have a pointer j, and we need to see how do we initialize or make use of these pointers. Okay, so let's see how we can do a in place partition here. Okay, so let's say the array elements are the same that we have taken, that's 2 7 8 6 1 5 and 4. Let's say these are the array elements, and now what I will do is I will maintain two regions. Okay, so I need to maintain two regions. Let's say one is the region I. So one region starts from start and ends at I. In this region I contain all the smaller elements. Okay, the other region that is ending at j will contain all the larger elements, and let's say this is my pivot element. Okay, let's say this is 4. So what I need to do, I need to iterate over this part that is not covered, and I need to scan every element. Let's say this is my element. Okay, now this element can go either in the smaller region or it can go in the greater region. Okay, so if it's going in the greater region, I can just do j equal to j plus 1, and this element can be merged successfully in the greater region. For example, this element is 6, so I have a smaller region followed by a larger region followed by another element that was greater, so it gets merged in the greater region by doing j equal to j plus 1. But suppose at the next index you get an element 3, so we need to merge this element 3 in this smaller region. So I need to expand I, so that would mean I will go to I plus 1, and we need to swap array of I plus 1, so array of I, that is this particular element, with this element. Okay, so that would be array of j. Okay, so that's what we need to do if we find an element that is smaller than the pivot element. Okay, so now let's try to dry run this approach on this particular array. In the starting I do not have any smaller region, so I start I equal to -1, so I is pointing at this point, and let's say j is going from the starting index, this particular index that is I plus 1, till the last index that is e minus 1. Okay, so I say okay, for j equal to I plus 1, or j equal to, okay, j equal to s. Okay, the starting point is s. Okay, I can say j will go till e minus 1, and I do j plus plus. Okay, so what I will do is I will check if array of j is less than equal to my pivot element. Okay, then what I will do, I will expand my smaller region by doing I equal to I plus 1, and I will also bring that element that is here and that is smaller than the pivot to merge it in the smaller region. So it will be swap array of I and array of j. Okay, so let me make it more clear. So in the beginning we are at 2 and we see 2 is smaller than 4, then we say okay, I equal to I plus 1 and swap array of I and array of j. So I and j both are at 2, so when you swap 2 with 2, 2 stays here. Okay, so that means this part is now the smaller region. Okay, and then you go to the next element. So this element is greater, then 4, so you skip it and you do j plus plus. Okay, you do j plus plus. That means this is now the greater region. You come to 8, you see 8 is greater than 4, you do j plus plus, you come to the next index. You go to 6, you see 6 is greater than 4, you come to the next, you go to the next location. Now you come to 1. Okay, now you come to 1 and you see, okay, this element array of j is actually smaller than the pivot element. So that would mean ideally when we are dividing the region, it should be like this: 2 and 1 followed by 7, 8, 6. This should happen. Okay, so then what you need to do, you need to increment your I will come to this place and you will swap 7 and 1. So once you swap 7 and 1, you will actually get 2 followed by 1, and you will get a region in which you have all the elements which are greater. So it will be actually 8, 6 and 7. Okay, it won't be 7, 8, 6, but it would be 8, 6 and 7. And then you come to 5 and you see 5 is greater than 4, so you simply merge 5 in this particular region and you come to 4. Okay, so this is what this loop is going to do. Okay, it's going to divide the array in two regions, one with the elements which are smaller and one with the elements which are larger. So now final step is left. You need to pick this 4 and you need to place it in the correct position. So this ending index is I, this ending index is j. So what you can do is, finally after the end of this for loop, you can just swap your pivot element, that is array of end, with this particular element 8, because I want 4 to come in between these two. So that would mean it would be array of I plus 1, and pivot would be now placed at the pth index. Okay, so that would mean the pth index is I plus 1. Okay, so finally it would be like this: 2 and 1 followed by 6, 7, 5 and 8. That's the greater region, and you place a 4 here. So this is the correct index of 4. Okay, so this is the correct position. Okay, so now this is the smaller part and this is the larger part, and we can do a recursive call to sort the left part and sort the right part. The same thing will happen recursively. So let me quickly implement this code. So in the beginning, I say j will be at start and I will be one step behind j. So that would mean it would be start minus 1. In the beginning, it is going to be minus 1. Okay. Or you can say, I'm not explicitly writing minus 1 because it's a recursive function. Okay, so it should be one step behind start. So for whatever is the value of j, j should be less than equal to e minus 1. I do j plus plus, and here I can say if array of j is less than equal to my pivot element. So I need to define what is my pivot element. So int pivot equals to the array of end. That's my pivot element. Okay, so if this is the case, I have to merge the smaller element in the region 1. Okay, so that would mean I equals to I plus 1, and then you can do swap array of I with array of j. Okay, otherwise expand the j region. Okay, expand the larger region. So that is done using this statement j plus plus. If it is not clear, you can just write j equal to j plus 1 here also. Okay, so that is also fine. Okay, and finally you can say place the pivot element in the correct index. So that would mean swap array of I plus 1 with array of last element, that is array of e, and finally return the index of pivot element, that is I plus 1, because this index is needed at this particular point so that you can divide the array into two parts. Okay, so that's all about quicksort, and let's try to run the code. Okay, okay, we also need to call the quicksort function, right? This should be actually int. Okay, so small mistake, and we should also print the array. So I can say for int I equals to 0, mm, oh sorry, this should be S and E, my mistake. For int I equals to 0, I less than equal to n minus 1, right here we should give the array, and we should do cout array of I. Okay, so I fixed few errors that I made while explaining the code, so this should be okay. Okay, so build is done. So let's try to run quicksort, and you can see we are getting a sorted array 1 2 4 5 6 7 8. So that's how you can implement quicksort, and thanks a lot. Hi everyone, so let's discuss one problem. In this question you are given a number, and you have to convert that number to print the spellings of that number. Okay, for example, the number is 2048, so you will print a string 2048, and we will try to do this problem recursively, okay, so that you understand recursion better. So let's see how we can break down this problem. So we have a number 2048, and if you want to print spellings of each and every digit in this number, you need to extract digits. Okay, so the first hint is you need to extract digits. Okay, so obviously we know if we want to extract digits, we can easily extract the last digit. That is the easiest digit to extract. So that digit can be extracted using n mod 10. So that will be equal to 8. So we get this particular digit 8. And suppose we know the spellings of 8, so we may print 8. But what we want is we first need to print the spellings of this sub problem, that is 204. Okay. So what you can do, you can break down your problem into a sub problem. So sub problem is n by 10. Okay. And for every step you have to do a work that the last digit that you extract, for that digit you print the spellings of that particular digit. Okay, so this is an hint to solve this problem. So what we can do is we can start with the number 204, okay, 2048, and we will say, okay, we will do two things. We will do a recursive call on 204 because we first want to print 204, and then we will print 8. From here we can make a call on 20, and then we will print uh, spellings of 4. Okay, so digit that we have extracted is 8, digit that we have is 4. We can reduce it to further 2, and the digit that we extract is 0, and we can further reduce it to the number 0, because if you do n by 10, so 2 by 10 is going to be 0, and the digit that you extract is 2. So while going towards the base case, so base case will be your number is reduced to 0, and in every step you are applying this update n equals to n by 10. So this is how you are reducing your problem, and also you are extracting digit by digit is nothing but n modulus 10. So that is what you have in this case, so n mod 10. So while coming from the base case towards the main case, what you can do in this direction, in the bottom up direction, that means after the recursive call you start printing the spellings of each and every digit. So it prints 2, it prints 0, it prints 4, and it will print 8. Okay, so this is how we are going to solve this problem. So what work we have to do, we have to first make a call. Okay, first make a call on a smaller sub problem n by 10, and then we have to print spellings of the last digit. So last digit is nothing but it is n modulus 10. Okay, so let us see how we can write the code. So this is the recursive case, and in the base case you can say if n becomes 0, that means your number has reduced to 0, you just return. Okay, so this is digit and this is number, so you have to be very careful. Okay, so this last digit 0 does not mean that the number is 0, so you have to actually reduce this entire number to 0. Okay, and we are assuming in this question the input that you will get will be greater than 0, so we will not do any work for 0, or you can put a separate if case. Okay, so let us write this function. So function is void, let's say print spellings. Here you get the number, okay. And what I will do, I will make a separate character array, okay. It's a 2D character array. So the 0th index of this array gives me the word 0, the first index gives me 1, the second index gives me 2, and so on, okay. So if I just do see out words of 5, I will get this entire row from this 2D character array, okay. So 5 is a row, 6 is a row, 7 is a row, okay. So it's a 2D array of characters, you can see. So what we can do is we can have a base case. We can say if n is equals to 0, do not do anything, just return. In the recursive case, first print the spellings of, let's say, 204. So that number will be nothing but n by 10. So I can say print spellings of n by 10. So recursion will do the work for us, that we can assume at this particular point. So what you do, print spellings of n by 10, it will print 2, 0 and 4. So what is left? So if the number is 2048, we need to extract the last digit, okay. And doing n by 10 does not change the value of n in this function. It passes a new value to a new function. So we are not doing n equals to n by 10. No, we are not updating the value of n. We are sending a new value of n to a new function. So if you do digit equals to n mod 10, so it will be nothing but 2048 mod 10, that will be 8. Okay. And from here you can see the 8th index of this words array will give you the spellings of 8. So what I can do, see out words of index 8. So that index is nothing but a digit. So digit is n modulus 10, and here I can see out words of digit followed by some space and return. So that's it. That's what we need to do to print the spellings. So in main we can say int n, scene n, and we can say print spellings of the number n. Okay. So it's digit 2 words. So let me give 20448. So it says 20448. Okay, and it will work for all such numbers 19001. So that's the beauty of recursion. So now I think it will be more clear. So this question is quite similar to the increasing decreasing question that we have seen. The only important thing is if I just change this statement and if I just put it here, you will see the ordering in which the digits are printing, it will get changed. Okay, so you can see it's 04. Sorry, we have to build the program again. Okay. uh, okay, so we have to actually move this statement upward also. Okay, so if I just swap these two statements, you will see the ordering will be reversed. Okay, so if it is 1 2 3, it says 1 2 3. Oh, there is a small mistake here. Okay, print spellings, so it will be print spellings of n. So you can see 3 to 1. So we are getting the same output but in the reverse order. Okay, so now you understand what is the meaning of top down direction and what is the meaning of bottom up direction. So in this code we are doing the work in a bottom up direction. That means we are doing the work after the function call. So that's all for this video. Thank you. Hi everyone. So now we will discuss a very simple problem. You have to write a recursive function that converts a string into an integer. Okay, so let's say you're given a number like this. You want to convert this into an integer like this, 1 2 and 3 4. So let's say this is your input and you want an integer in the output. So it's an easy problem. I will suggest you try this problem yourself before watching the solution. Okay, so if we want to use recursion, the idea is to break down the problem. Okay, so let's see, this is a bigger string of length n. We can say we can break this into two strings. So this will form a smaller sub problem and we can extract the last character out of it, and we can subtract 0, and we will get a 4 as a digit. Okay, so what you can do with this thing, so suppose you have a recursive function that converts a string into an integer. So you can call the same function to convert a smaller string into an integer. So you give this to the same recursive function, so that recursive function will give you 1 2 3. Okay, and now you also have a 4 as a digit. So if you want to make a number 1 2 3 4, what you need to do, you need to multiply your smaller answer by 10 and you need to add 4. So this is what your, this will build your recursive case. Okay, and in the base case you can see if n is 0, if number of digits in the current string is 0, you can actually return 0. Okay, that's what you can actually do. So let's see how the recursion will proceed. So you have 1 2 3 4, so you make a call on 1 2 3 and you extract 4. So you make a call on 12 and you extract 3. You make a call on 1 and you extract 2. You make a call on null string and you extract 1 out of it. Okay, and while doing bottom up, when you're coming from bottom to top, so what do, you multiply your previous answer with 10. Okay, so this becomes 10 and you add 2 to it. Okay, so this becomes 12. So you multiply your previous answer, that is 12, with 10 and you add 3 to it, so it becomes 123. You multiply your previous answer with 10, it becomes 1230 and you add 4 to it, and from here you can return the number 1234. Okay, so this is how we are going to do this. So let's see the base case. So I'm getting the character array and the length of the array that I've computed. So I can see if the length of the remaining string is 0, we can simply return 0 in this case. That is the base case. And at the current index I have to extract the digit. So the digit is given by a of, the digit will be at n minus 1th index minus 0. So that will give me the last digit. Okay, and I need to get a number from the smaller sub problem. So that number, or that my small answer, that would be nothing but string to int from the same array but with a reduced length. So I just call this function and my final answer is nothing but smaller answer into 10 plus digit. That's how we can actually code it, very simple. And let me show you. Cout string to int, let me give the array, let me give the length, and I'm let's say adding 5 to it, so that we can see that it's an integer. Okay, so let's say int x is this, and I'm doing cout x and I'm doing cout x plus 1. Okay, so we will get two numbers so that we can see the if addition is correct, that means our this x is actually an integer. Okay, so let's try to run our code, and I can say this is string to int. So you can see I'm getting 1 2 3 4 and 1 2 3 4 5, 1 2 3 5. That means our answer is correct. Okay, so what is the thing that you need to learn in recursion is how to break a problem into two smaller cases. Okay, so I just, while writing the code, I didn't think of call stack, I didn't think how it is going to work, but the only thing that I should know is how do I break my problem into two parts. Okay, so here we have this 1 2 3. I was sure that this will be given by this function string to int. Okay, so this has a length n, so I made a call on length n minus 1, so this gave me a number 1 2 3. Okay, so that is my small answer, and this 4 is a character, and if I subtract 0 out of it, 0 as a character, this will basically subtract the ASCII values and I will get 4 as an integer. Now I have these two integers and I want to form 1 2 3 4. How do I get it? So that will be nothing but smaller answer, that is this 1 2 3 multiplied by 10. Okay, so this is not a string now, that's an integer, plus 4, so that will be my final answer. And you can see this is the beauty of recursion, how flawlessly this code works, how elegant the code is, and it's just one or two lines of code to do the work. Okay, so I hope you understood this idea and you will apply it to solve some more problems as well. Hi everyone, so we will discuss a problem, very easy problem. So it says given a string, okay, you need to replace all occurrences of pi with the value of pi. Okay, so you know value of pi is 3.14. So wherever you see uh, pi in the input string, you have to replace that with the value 3.14. Okay, so one thing to note is this input is a character array and output is the same character array, and you can assume that you have sufficient extra space in the array to accommodate the increased number of characters. Okay, for example, if this is pi, then you have to put 3.1.4 because it cannot be a floating point number that you can put inside the character array. Okay, it has to be a character. So you put 3 as a character, you put dot as a character, 1 as a character, and 4 as a character. That would also mean you need to do shifting of the remaining character. Okay, for example, if there is x, so if there is x followed by pi, then you should have x followed by 3.14, then you have gh, then you should have gh, and so on. Okay, so again, think how you can approach this problem recursively. So we will now build the solution for this problem. Okay, so the idea is we will traverse the entire input array and we will try to locate if there is a pi present at the current location. Okay, so that means the current index contains p and the next index contains I, and once you see there is a pi in the current location, that means I is okay. So whatever is this array, so at the index I you have p and at the index I plus 1 you have I. That means for the corresponding location, okay, you need to start replacing these characters. So we are not making any other output array, we are not printing the result directly, we are just doing it in place. Okay, so that's the question, you have to do it in place without taking any extra array. So what we will do is, so let's say there are some other characters x y z which are here. So what we need to do is we need to do the shifting. Okay, so once you find out a pi here, you will say okay, I will put 3 here, I will put dot here, I will put 1 here, I will put 4 here. Okay, so that means for every pi you need actually 4 places. So that means you need to shift all of these characters by 2 positions forward. Okay, so if this index is, let's say, I plus 2, then this will be moved at I plus 4. Okay, so that means you need to do the shifting. Okay, so it will be 3.14 and x y z, and if there is a pi here, that pi will be moved as well. Okay, so you will have all the remaining characters of the string will be moved uh, by 2 locations in the forward direction. Okay, and you keep on doing this. Okay, you keep on iterating the string from the left to right manner. Once you find out a pi, you replace those locations, those 4 locations, by 3.14. Before that, you shift all the remaining characters of the string by 2 locations in the forward direction. And once you have done this, you make a recursive call on this part. Okay, and if the current string is not pi, then you just make a recursive call on the next part. Okay, for example, if you have x, a b c d, so you scan this input, you say okay, there is an x here, then it doesn't matter. Okay, so you just make a recursive call on this part. Okay, then you see there is an a, no need to do anything, just make a recursive call on the smaller part. You see a pi, then you need to do the work. So what is the work is shift or everything after pi by 2 locations in the forward direction and replace the value of pi with 3.14. Okay, so I'm going to use this logic to build a recursive algorithm, and I will explain you have to think how, what would be the corner cases that we need to handle. So the function is replace pi, we get an input array, and we also get the ith location at which we are currently working at. Okay, so what would be base case? Okay, so you're using a variable called I to read through the entire array. So once you reach the last index, that means you have already processed the entire string. What you will do, you will just print it out. Okay, so if array of I becomes null, that would be your base case. if you reach the last index of the array, that means your work is done. So in that case, you just return, do not do anything, okay? And after that, what you can do is you can look for pi at the current location. That is the recursive case. So look for pi at current location. So I can see if array of I is equal to p, okay, and array of I plus 1 is equal to I, okay. So that means we can look for pi. You can also add this case here, or array of I plus 1 is null, okay. So if the last character is let's say p, okay, and the next character is null, then also we don't need to do anything. So you can also say this thing, or array of I plus 1 is null. We can stop at this point, because to make pi we need at least two characters, okay. So if array of I is p and the next character is I, then we have to do the shifting followed by replacement with 3.14. So let us see how we can do the shifting, but before that let's write the other case also, okay. So else what we can do is we can just go to the next position, else go to the next position, okay. So how do we go to the next position? By calling this function replace pi, and we can say array will remain same, I will be incremented by I plus 1. That's it, and we can have a return statement here, okay. So the else case is easy. Suppose you find an x here, you do not need to do anything, you just go to the remaining part of the array, okay. But the case when we have pi, that is the main case that we need to handle here. So what we will do, we will first do the shifting, okay. So to do the shifting, I will take a variable called j equals to I plus 2, and then I will take j to the end of the array, okay. So take j to the end of the array, while array of j is not equal to 0, I can say j plus plus, okay. So why this is important, let us see. So let's see the shifting operation, how we can do it. Suppose this is a b c followed by p followed by e f g, okay. So what happens is these three are easy, you do not do anything, you just keep on moving forward. But at this location what you see is you got a pi, so in that case you need to shift these characters e f g, okay. So they start from index I plus 2. So I'm taking j which is at I plus 2, and I say while a of j is not equal to null, I do j plus plus. So j goes here, j goes here, j goes here. So j comes to this particular index. Then what I will do is I will start moving these characters. So I need to leave 4 slots for pi. So these 4 slots are left. What I need to do is I need to copy all these characters to the new location, okay. So I will say while j is greater than equal to I plus 2, what I will do is I will say a of j plus 2 equals to a of j and j minus minus. So that means okay, so j is now pointing to this index. I will say while this j is greater than I plus 2, so I will move back j till this point, so that I am able to iterate over these 4 characters e f g and null. I say a of j plus 2 equals to a of j. So I copy first null here, then I copy g here, then I copy f here, and then I copy e here, okay. So this is what I do at this particular location, okay. So once I do this, I see now I have 4 slots empty. So here what I do, I put a 3 here, I put a dot here, I put a 1 here, I put a 4 here, and I make a recursive call on this part, okay. So if there is a pi in this part, it will again go through the same procedure, okay. So this is what I basically do. So I will put this code here, okay. Then after I will do the replacement. So let's do the shifting now. So shifting should be done in the right to left order, because if you do from left to right, you will replace some of the characters that are there in the string. Okay, that will give you the wrong output. So while j is greater than I plus 2, so we are doing shifting in the right to left direction. So we can say a of j plus 2 equals to a of j, and I can do j minus minus. So now we are at a, so we have done the shifting. Okay, so the only thing that is now left is replacement followed by a recursive call for the remaining part. Okay, so I can say array of I will now store 3, array of I plus 1 will now store dot, array of I plus 2 will store 1, and array of I plus 3 will store 4. Okay, so recursive call on the remaining part, it would be replace by, and it would be a followed by I plus 4. Now this is important. Okay, so I plus 4, why I plus 4? Because our remaining string starts from the I plus 4th index. Okay, so if this is pi, this is 3.14, this index was I, this is gha, so this index is I, so this index gha pi whatever you have is, so you make a recursive call on this part of the array. So this index is I plus 4. So that's it, and this is our replace by function. Now we can test our code. So we can make a large character array, we can take it as input, we can say okay, whatever is there in a, we will replace it. We give a, I is 0, and we do cout a. That's it. So it's called replace by. So let me give x pi, gh pi, pi pip gh pip. Okay, so this is what we get. So you can see this is x followed by 3.14 gh, 3.14, 3.14 pgph. Okay, and we can also verify the case where the string ends with pi. So let me say x pi gh pi, so that is also correct. Okay, so that's all for this video, and thank you. Hi everyone, so we will discuss this question called place the tiles. Okay, so let's say it says given a wall of size 4 cross n. Okay, so there is a wall whose height is 4 and whose width is n units. Okay, you need to figure out in how many ways you can build the wall. Okay, and the bricks that are there to fill the wall are of the size 1,4 and of the shape 4,1. Okay, so that means you can either put a brick in a vertical orientation, or you can put these bricks in a horizontal orientation. Okay, so there can be multiple ways to place all the bricks throughout the wall. So you need to figure out what is the total number of patterns or designs or ways in which you can build this entire wall. Okay, so this is what is needed. So this is one such design you can make to fill this particular wall. Okay, so now let us break down this problem into some smaller sub problems. We will say, okay, let us think of the smallest possible case. Okay, so when we have, let's say, only one brick, we can just put it like this, we can put it vertically, so that is one option. Okay, or what we can do is we can put this brick horizontally like this. Okay, so when you put a brick horizontally like this, the top most part has 3 units left, so that means you cannot place vertical bricks in the topmost part. Okay, so the other 3 bricks must go like this. So that is clear to us. Okay, that means if you pick the if you put the first brick in a vertical fashion, then you have a remaining wall that can be filled in how many ways. So let us denote fn as the total ways to fill this wall of size n. But if you put the first brick in a vertical direction, so you have a wall of length n minus 1, which can be built in f of n minus 1 ways. So that is the number of ways when you put the first brick in a vertical orientation. And when you put the first brick in a horizontal orientation, the remaining length of wall is n minus 4 units. And you can just fill this wall in f of n minus 4 ways. So that's you can compute using recursion. Okay, so that is what it is. And there are no other cases. So f of n will be nothing but it will be summation of f of n minus 1 plus f of n minus 4. So this gives us the recursive case. Okay, and we need to figure out the base case. So in the base case, you can see if the wall is of unit length 1, okay, then there is only one way. If wall is of length 2, then also there is one way. If the wall is of length 3, then also there is only one way. And if the wall is of length 4, then there can be two ways. Okay, then there can be two ways, like this or like this. So both of them are correct. So what you can do, you can just make a case if wall length is, if the value of n is less than equal to 3, then you can return 1. Okay, even if it is 0, then you can return 1. So you can say for n equal to 4, you will make a call on n equal to 0 and you will make a call on n equals to 3. So this answer is 1 and this answer is also 1. So 1 plus 1 is 2. So you can actually get this answer from the recursive case only. Okay, so either you can make this as a base case. So you can make this as a base case and solve this problem. The coding is very simple, almost same as the Fibonacci problem, and it is possible to optimize this problem using dynamic programming as well. So I will not discuss it here, it will be covered in the DP section. Okay, so that's all for this video and thank you. Hi everyone, so we will discuss one interesting problem in this video. It's called as a ladder problem. Okay, so you're given there is a person or there is a student who is standing at this bottom of a staircase and he wants to reach the topmost point, and it's given that there are n number of steps that are there in the ladder, and at each step student can take a jump of 1, 2 or 3 steps. Okay, and you're interested in finding out the number of ways in which he can reach top of the ladder. Okay, so that means at this point he can jump 1, he can jump 2, he can jump 3, and same goes with all other steps as well. So you want to find out the number of ways to reach the ladder for a given value of n. For example, if say let's say n is 4, then how many ways you can think of? Okay, so one way would be he will take a jump of 1 every time, that is one way. Another would be he takes a jump of 1 2 1, that is 4, or he does 1 1 2, another way, or he does 2 1 1, that is another way, or he does 2 2, that is another way, or he does 1 3, and or he does 3 1. He cannot take a jump of 4 because the maximum jump size is 3. So you have total of 1 2 3 4 5 6 and 7 possible ways. So you need to come up with an algorithm with a recursive or some method that will help you to count the number of ways in which he can climb this particular ladder. So I'm giving you 2 minutes, take a pause and think about how to approach this kind of a problem. How do we break this value of n? If you want to compute f of n, that basically denotes the number of ways to reach the nth step, what it would be. So think about it. All right, so let us discuss the solution to this problem. So let us say we do not know the number of ways to reach this point, but what we know is if you want to reach this particular step, okay, if you want to reach the nth step, then there are only 3 options to reach this step. You either come from this step by taking a jump of 1, or you come from this step by taking a jump of 2, or you come from this step by taking a jump of 3. So let us assume the total number of ways to reach this step would be f of n minus 1, it would be f of n minus 2, and it would be f of n minus 3. So can you now relate what would be the number of ways to reach the nth step? Okay. So now a student has three options. Either he comes via this step, or he comes via this step, or he comes via this step. So your final answer would be sum of these three options. Okay. So it would be f of n minus 1 plus f of n minus 2 plus f of n minus 3. We will also verify this with the help of a recursion tree diagram, and we can see. Okay. So why this is true? For example, why not multiplication, why only addition? Okay, for example, if you want to reach, let's say, Delhi from three different places, okay, let's say you want to come from X, you want to come from Y, and you want to come from Z. Let's say there are 4 ways via Z, there are 6 ways via Y, and there are 3 ways via some location X. So what would be the total number of ways in which one can reach Delhi starting from X, Y, or Z? So obviously it would be sum of these ways, not a product of these ways. So here also we will do a summation of these three sub problems. Okay, and some of you may ask why we have not counted this way, in which a student first jumps here and then he goes here. So this way is already included when you compute f of n minus 2. So when you calculate the number of ways to reach this ladder, it automatically counts those ways in which you jump from this ladder to this particular step. So that is already there. Now let us see how the answer for n equal to 4 is true. So from n equal to 4, if you see the recursive call, we are going to make 3 calls, one at 3, one at 2, and one at 1. And let us also figure out the base case. So base case is going to be easy. So if n is 0, I can say return 1. So n equal to 0 means how many ways are there to stand on the ground. So obviously this is the 0th step, and there is one way in which he can stand at this particular ground. So the answer is going to be 1. So at every sub problem, I'm going to reduce my problem into 3 problems more. So 3 will make a call on 2, it will make a call on 1, it will make a call on 0. 2 will make a call on 1, 2 will make a call on 0, 2 will not make a call on minus 1. Okay, so 0, 1, 2. So from 2 we can just come via this, and we can come via this. We cannot make a call on minus 1. Okay, so we will just ignore this call, or we will say we will return 0 from this call. Okay, if you want to make a case if n is less than 0, you can just say return 0. Okay, you can do this if you want. So from 1 you will make a call on 0 only, and from 2 you will make a call on 1, you will make a call on 0, and from 1 you can make a call on 0 only. So if you carefully see this structure now, so 0 will return 1 here, 1 will return 1 here, 0 will return 1 here. So that means to reach second step you have two ways, 1 plus 1. That means one way comes via 1, so that is this way, 1 comma 1, and one way comes via 0 directly, that is 2. So that is correct. From 2 you can reach 3 in two ways, and from 0 to 1 there is one way, from 1 to 3 there is one way, and from 0 to 3 there is one way. So to reach 3 there are basically 4 ways, that is 2 plus 1 plus 1. So 3 will return an answer of 4 here. Okay, so 4 makes another call on 2, 2 makes a call on 1, 1 makes a call on 0, 0 returns 1, 1 returns 1, and 0 returns 1. So similarly 2 also returns a 2 here, like we have done here as well. Okay, and 4 also makes a call on 1, and 4 also makes a call, 1 makes a call on 0, it returns 1, and it returns a 1. So to 4 comes to know that there are 4 ways. So 4 knows there are 4 ways via 3, there are 2 ways via 2, and there is one way via 1. Okay, so that's what 4 knows. So the total number of ways to reach 4 will be 7 ways. Okay, so let us also write these ways. You can also evaluate these ways from this recursion tree by looking at this tree. So in the first way you go from 0 to 1, you go to 1 to 2, and then from 2 to 3, and 3 to 4. So the first way is actually 1 1 1 1. So if you want to see, you just take out this difference. 1 minus 0, 1. 2 minus 1, 1. 2 to 3, you take a jump of 1, that is 1. And 4 minus 3, that is also 1. So this is the first way. What is the second way? You go from 0 to 2, so you take a jump of 2. You go from 2 to 3, you take a jump of 1. From 3, you go to 4. So that is one way. The third way is this: 0 to 1, 1 to 3. So that is 1, 2, 1. And the fourth way is this: 0 to 3, and then from 3 to 4. So you take a jump of 3 and you take a jump of 1. So in all these cases, you can see you are stopping at 3. So that is what I mean by saying that 4 ways via 3. Then you have 2 ways via 2. So those are these ways: 0 to 1, 1 to 2, and 2 to 4. So you take a jump of 1, 1, and 2. And then from 0 to 2, 2, and 2. So these are the 2 ways in which you first stop at the second step and then you take a jump to 4. And one way via 1. So that means you take a jump of 1 and then you take a jump of 3. Okay, so this is a jump of plus 1, this is a jump of plus 3. 1 to 4. So you can see we are also able to extract all possible ways using recursion, and we are able to count all possible ways using recursion. So the code is very simple. Now this problem can be extended as n and k problem. So you might be given a letter of size n and you will be given, you can take a jump of maximum size k. Okay, so instead of 3 you are given, okay, the maximum jump that you can take is of size k. In that case, the recurrence will become something like this: f of n will be summation of I goes from 1 to k, f of n minus I. Okay, so you will, instead of taking a sum of previous 3 terms, you will take a sum of previous k terms. Okay, so let us quickly write the code for the nk problem that's going to be solved using recursion. Okay, so there are more ways to solve this problem using dynamic programming, but since we are doing recursion, we will first see the recursive formulation. Okay, so let me give int ladder, int n, int k, or let me just call it as f. Okay, so I will make a base case. If n is 0, I will return 1. Another base case, if n is less than 0, if I'm making a call on a negative value, I will say return 0. Otherwise, I can say, let's assume my current answer is 0. So one thing that you can do is you can simply say, okay, f of n minus 1 plus f of n minus 2 plus f of n minus 3. You can return if the value of k is 3. But if this is not, if k is a variable, then you need to put a loop. So you can say for int I equals to 1, I less than equals to k, I plus plus, you can simply say answer plus equals to f of n minus I. And you can return the answer. So that's it. And here we can just see out f of n comma k. Right, so another thing that we need to pass to this function is k. So let's say n is 4, k is 3. So you can see we are getting the answer as 7, which is correct. So I hope you got an idea how we solve this problem. And in this part we are doing nothing, but we are just making calls on n minus 1, f of n minus 2, n minus 3 up to f of n minus k, and whatever answer we get from each of the sub problems, we combine them into our variable answer. Okay, so we add them, let's say x, y, z, whatever we get, we add here, and we return this answer to the main. So I hope this is clear. And since this value can be negative, let's say n is 3 and k is 4, so if we make a call on -1, we have made a base case to return 0 in such a case. Or you can put a if condition inside the for loop to avoid such a call. So both ways are correct. Hi everyone. So we will discuss another problem. It's friends pairing problem. Okay. So it says given n friends who want to go for a party on bikes. Each guy can go as a single or as a couple. Find the number of ways in which n friends can go to the party. So for example, you're given three friends. Let us just number the friends as 1, 2, 3, and they have motorbikes and they want to go to a party on these motorbikes. Okay. So the maximum motorbikes that is available would be n, so that everyone can go solo. So let us say we have three friends and we have three motorbikes. Okay. So what can happen is everyone can go solo. So let's say one goes alone, two goes alone, three goes alone. That is one way. Okay. So one, two, three. They all go alone, or they can go as a couple. Okay. So maybe one can form a couple with two, and three can go alone, or one can form a couple with three, or two can go alone, or two and three can form a couple and one can go alone. Okay, so the number of ways we have is four ways. Okay, so if you had four friends, then it is also possible all of them go alone, or they can go in couples, or they can go like one and three are going together, two is going single, four is going single. Okay, so there can be lot many ways. Okay, so you need to count the number of ways in which these friends can go for a party. So again, first pause this video, think how you can break this recurrence, break this problem into smaller sub problems, and then we will consider the solution. Okay, so let us discuss the solution now. So solution is very simple. So you assume there is a bunch of people. Okay, let's assume there are n friends, and let's say they are standing in a line, and let us say, let's talk about the first guy or the last guy. Okay, let's say this is the first guy. Okay, now according to the question, this guy has two choices. He can go single or he can go as a couple. So accordingly we will make two cases. Either when he goes alone, what happens? So let us assume this guy goes alone. So there is one way in which this guy can go alone, but the remaining guys can go in how many ways? Okay, so let us assume the total number of ways is fn that we want to compute. So the remaining guys can go in f of n minus 1 ways. Okay, so we are doing a multiplication here, because when we say this guy is going and the remaining friends are also going. Okay, so it and basically means multiplication. Okay, or we have a choice, or this guy can go as a couple. So that means we will add some more number of ways to it. If this guy goes as a couple, okay, so let's say if this guy goes as a couple, it will need someone from the someone else. Okay, so what will happen is, let's say you have n minus 1 people which are left. Okay, and let's say this guy uh, wants to bring this girl on his bike. Okay, so let's say this guy wants to bring this girl on his bike, and they both of them want to go together. Okay, so out of n minus 1 people, he can choose one. Okay, so this guy now has n minus 1 c1 options to choose one of the friends who will go along with him. Okay, and the remaining people, so how many people are left? So out of n people, two people are going as a couple, so remaining people are left is n minus 2. So those people can go in n minus 2 ways. So again, there is a multiplication here, because these two people are going in n minus 1 ways, and the remaining people are going in f of n minus 2 ways. Okay, so again we have a and here, and here we have a or. So this is how we have built the recurrence. So this is nothing but this is equal to f of n. We can even verify our answer. Okay, so let us see, let us consider the base case. Let's say when n is 0, answer should be I think 1, because if no one is going, that is also one way. If n equals to 1, then the answer should be 1. When the n is 2, the answer should be equal to 2. Okay, let us try to compute f of 2 using this recurrence. Okay, so f of 2 would be f of n minus 1, that is f of 1, plus 2 minus 1 c1 1 into f of n minus 2, that is f of 0. Okay, so this comes out to be 1 plus 1, that is 2. So let us try to compute f of 3 using this recurrence. So it is 1 multiplied by f of 3 minus 2, that is f of 2, plus this is 2c1, that is 2, into f of 3 minus 2, that is f of 1. Okay, so f of 2 is 2. We can substitute this answer here. Okay, plus 2 into f of 1. F of 1 is 1, so it is 2 into 1, that is equal to 4. So you can see our recurrence is correct, and this will be our base case. And you can now write the code. That coding part is very easy. You just need to implement the recurrence. Okay, so that's it for this video. The important part was to think how do you break down this problem. Okay, so that is the thing you need to analyze while solving such problems. Hi everyone, so we will discuss one problem this time. So the problem is count the number of binary strings of length n, okay, such that they do not have any consecutive ones. So firstly, you need to try this problem yourself, because it will help you to come up with something. Okay, so for example, if I give you, let's say length is 2, okay, how many binary strings you can make? Okay, so that means you have two places, and binary string mean you can put 0 or 1 at any location. So one string would be 0 0, another would be 0 1, another would be 1 0, another would be 1 1. Okay, so out of these four, this is not a valid case because it contains a consecutive 1. So for n equal to 2, we know the answer is going to be 3. Okay, so now you have to think of what will be the number of strings if I give you a string of length n. So clearly we can try to break this problem into a smaller problem. Okay, so we will say, okay, let us keep string of length n minus 1 as separate, and let us just think of the last digit or the first digit. Okay, so if I can put a 0 here, okay, so that means I can count all valid strings of length n minus 1 which are there. Okay, so you can form all such strings irrespective of they end with a 1 or they end with a 0. Okay, so that does not matter because you're putting a 0 here. Okay, so if f of n denotes the number of valid strings of length n, then f of n minus 1 will give me the number of valid strings of length n minus 1. Okay, so we actually have two possibilities. Okay, so the other possibility is, instead of putting a 0 at the last place, we can actually put a 1 at the last place. Okay, so what will happen in this case? So suppose you have a valid string, but that string ends at, let's say, 1. Okay, so the last bit is 1, so this whole won't be a valid case. Okay, so what we actually want is, we want all those valid strings of length n minus 1 which basically end at 0. Okay, so which basically end at 0. So to count those strings, what we can do is, we can just say, okay, if I put 1 at the last place, that means we must put a 0 at this place, and we can make all valid strings of length n minus 2. Okay, so if I make all valid strings of length n minus 2, whether they end at 1, they end at 0, they will perfectly form valid strings of length n ending at digit 1. Okay, so the number of valid strings of length n minus 2 will be f of n minus 2. So your final answer would be f of n minus 1 plus f of n minus 2. Okay, so this is how we got the recurrence. Base case you have to think, so I just gave you a hint, and you can implement this recurrence and solve this problem. So thank you, and see you guys in the next video. Hi everyone, so we will discuss very interesting classical problem that's called as Tower of Hanoi. Okay, so you can see this diagram. So the problem is related with this game. So there are some rules of this game. So the rules is like this. Okay, so let me tell you what you have to do is, so in this game there are three towers. You can name these towers as, let's say, A, B, and C. So goal is to move all the disks from tower A to C. Okay, so we have to move all disks from A to C, but during this process we can pick one disk at a time. Okay, so that is the task we need to do, but rule is you can pick one disk at a time, and you cannot place a bigger disk over a smaller disk during the movement. Okay, so cannot place a big disk on small disk. Okay, so these two rules must be followed while doing movement of the disks. Okay, so now we have lot of disks, but let us try to start with a very small problem in which we have only two disks. Okay, there will be n number of disks in the tower, numbered from, let's say, 1 2 3 4 5 up to n. But let us say we will try to first do it with two disks only. So let us have two disks, and let us try to move these two disks. Okay, so what steps you will follow? You will first pick disk number 1, you will put it here. Okay, so after the first step, you can say this is ABC. You can put the first disk here, and then you can put the second disk here. Okay, so 1 comes here and 2 comes here. So this is after two steps. Okay, and in the third step you can just pick one and put it here. So it will become something like this. Okay, 1 followed by 2. So you saw you actually needed 3 steps for 2 disks. Okay, so let us try to do it for the case when you have n equal to 3 disks. Okay, so you can try it yourself. It's like a game. You have to think what operations we should do. So this is our initial state. So what I can do, I have 3 disks. I can first move these 2 disks on some other tower. Okay, I can try to move these two disks here, and then I can move the third disk here, and then I can do it on so on. Okay, so if you need to move two disks from this part to this part, what you will do, you will follow similar steps as you done in the case n equal to 2, except there is one difference. Instead of moving the top two disks from A to C, we are now moving top two disks from A to B. So that means these operations will be executed in a on different stands. Okay, so you can assume we have exchanged the stands B and C, and we are going to do the same operations now. Okay, so let us first try to move the top two disks. So what I will do is I will put disk number 1 here, so 1 comes here. I will put disk number 2 here, so after two steps 2 comes here, and 3 remains here. Okay, in the next step I can put 1 here. Okay, so that makes 3 steps till now. Okay, so 1 goes from here, and we can put 3 here. Okay, so that is 4 steps now. So what is the state after 4 steps? We have disk number 3 here, and we have disk number 2 here, and disk number 1 here. Okay, now we need to move these two disks here. So what we will do, we can first put 1 here. Okay, so 1 comes here, that is the 5th step, and then we can say, okay, we will put 2 here. Okay, so that is the 6th step. Okay, 2 comes here, that is after 6 steps, and finally we can put 1 here. Okay, so that is after 7 steps. So you can see finally we are able to put all the 3 disks in the stand after 7 steps. Okay, so for n equal to 3, we actually needed 7 steps to do the work. So you need to think, you need to print all the steps. Okay, for a given value of n. So now this is where recursion is going to help you. So what we can do is, so let us now try to solve this problem recursively. So let us say we have 3 stands, and we have disks, like lot of disks here. Let's say these are numbered from 1 2 3 up to n, and let us try to break this. So what we can do is, we can assume if we can move n minus 1 disks, then our work will be easy. Okay, so what we can say is we can make a function, we can make a recursive function. Let's say move is a function. We can ask move function to shift n minus 1 disks from a to c. Okay, let's say this is a, b and c. So we can ask this function to move n minus 1 disks from a to b. So what will be the state now? You will have one disk here and you will have n minus 1 disks on b. Okay, so this is n minus 1, and then you have one disk in this stand a. So what you can do, you can just move this disk from a to c. So since it is a one disk, you can simply shift it. So you can you can say shift the nth disk from a to c. Your work is done, and then you can just call another function. Okay, you can say, okay, if this disk is shifted, so I will just erase this. So now you have the nth disk here, and what you can do is you can actually move n minus 1 disks from b to c. So you can call move n minus 1 disks from b to c. Okay, so this is recursion. So this is recursion. It will automatically do the work. It will automatically do the movement of all the n minus 1 disks from b to c. And you can see during this process it will not violate the property when we are placing a smaller disk over a bigger disk, because the disk at the bottom is a bigger disk. Even if you place any disk from this stack in this disk during the process, it will make sure that we are not placing a bigger disk over a smaller disk, because the disk at the bottom is already the biggest. Okay, and we will be recursively moving all these disks one by one, because we have seen if we can move n equal 2 disks, we can actually move 3 disks also. If we can move 3 disks, then we can move 4 disks also, and if we move 4 disks, we can move 5 disks also. Similarly, we can assume that n minus 1 disks can be moved recursively, and that's it. Okay, so this is the solution to the problem. So we will first write the code, and then we will also draw the recursive diagram to print the solution. Okay, so let's write the code. Okay, so we will take input the value of n, and we will make this function called void move that gets the number of disks, and also we should give the names of the towers. Okay, so I can just call move n disks from, let's say, tower a. So here I'm taking 3 towers. Let's say char source, char destination, and char helper. Okay, so what is we are going to do? So suppose you have 3 towers, let's say a, b and c. So our task is to move the disk from the source to the destination. Okay, so the destination is going to be b. Okay, sorry, destination is going to be c. So we can also change the order. We can say, okay, helper, and we can say destination. Okay, so we can say the towers are a, b and c, where a is the source and c is the destination. So now we have to think of base case, and we already know the recursive case. Okay, so the base case would be if you have 0 disks, then you do not need to do anything. So if n is 0, you can just simply return. Okay, or you can, if you do not want to make this as a base case, you can also make a base case for 1, in which you have to move one disk from the source to the destination. That is also fine. Okay, let's see in the recursive case. So in the recursive case, our first step is to move n minus 1 disks from source to helper, not to the destination but to the helper. Okay, so let's see what steps we need to do once again. So in the first step, you will pick these n minus 1 disks and you will put them on b. Okay, this is what you do, and the nth disk remains here. So this is the first step. Okay, so that means your destination would become B. So you call the move function, number of disks is n minus 1, source remains same, helper we will see, and the destination is nothing but the previous helper. Okay, so we are exchanging the names of destination and helper, so it becomes destination at this particular point. Okay, and after that what you have one disk. Okay, so to move one disk you do not need recursion, you just need a print statement. So it says, okay, let us take this disk from A to C. So A is your source, C is your destination. So that's what we are going to print. So this is your second step. So we can say cout shift disk disk number n from source to destination. That's it. And what is your next step? So next step is move n minus 1 disks which are lying on B. So what is B here? So B is nothing but helper. Okay, so pick those disks from the helper. Where do you want to place those disks? You want to place those disks on destination. So basically source and helper are exchanged. Okay, so that's it. So you're moving n minus 1 disks from the helper, that is B, to the destination, that is C, using source as a helper. Okay, so that's what we do in the third step. So this is your third step. Here you pick these n minus 1 disks, you put them here. So this is how all your disks are moved. Okay, so let's run this code and see. Okay, this should be 4. So we should give an input. So you can see we are getting some answer. So let us run this for a smaller value of n. Okay, so if you do not give any input, n will take a garbage value and that can lead to segmentation fault. Okay. Okay, you can see for n equal to 3, we are getting this answer and we can actually verify that this is going to be a correct solution as well. Okay, so let me explain you why this code works and how it works. Okay, let us quickly verify all these steps. It says shift disk 1 from A to C. So we move this disk here. So 1 comes here, 2 from A to B, 2 comes here. Then says 1 from C to B, 1 comes here. Then it says 3 from A to C. So it becomes like this. 3 comes here. And then it says uh, it is 1 and 2, so it says 1 from B to A, so 1 comes here. It says 2 from B to C, 2 goes here. So now final state is like this, and it says 1 from A to C. Okay, so you have one disk here which you put here, and now we will try to visualize recursion how it happened. Okay, so what we will do, we will, let's say we will we will draw the diagram here. Okay, so we have a function called move in which we are getting 3 disks and we are getting the names source, helper and destination. So we are getting A, B and C. Okay, so from here we actually performed 3 steps. One is move n minus 1. So we made a call on move function. So we have made this call move 3 disks from A to C using B as a helper. Okay, so this is what we have. Now in each recursive call we are doing 3 steps, 1, 2 and 3. So let me try to draw these 3 steps. So in the first call we make move, source remains same and we exchange destination and helper. So we basically exchange these two parameters and we make a call on n minus 1. So this is 2. and this is A, C, B. And as you know, recursion is making new function calls in which we are passing these values by making a copy. Okay, so in the new function call, you have ACB as a parameters in the function call. Then we execute second line, that is shift disk from. Okay, so this will be executed once this function call is over. So we will first elaborate it as well. So it will execute shift disk n. So n is 3 in this function from source to destination. Okay, so from A to C, that is what it will print. Okay, and finally it will make a call on move n minus 1. So n is 3, so it will be 2. And you can see helper and source are exchanged, destination remains same. So we basically exchange these two in the next function call. So it becomes 2 B A C. Okay, so this is what we do. Now we need to elaborate each of these function calls. So similarly, from this function call we will make a call on move. We will say okay 1, followed by, we will exchange these two. Okay, we will exchange these two, so it will be A B C. And then we will print a statement shift disk number 2 from A to B. Okay, from A to B. So A is source, B is destination. So that is what we do here. And then we will make a call on move. We will say 1 and we will exchange the first two. It will be A, C, A and B. Okay. So now let us try to first extend this function call. So it will make a call on move of 0. So that is a base case. We will not do anything here. Then it will execute a shift statement. So it will say shift disk 1 from A to C, source to destination, and it will make a call on move disk 0. So that is also a base case. We will not do anything. So this is not a call, this is a statement. So we come to the next function call, which is this. So it will make a call on move of 0. It will print a shift statement. So shift disk n, so n is 1 here, from source, that is C here, to destination, from C to B, and it will make a call on move of 0. Okay, so now we come to the next function call, which is this. So from here we will make a call on move of 1. Okay, parameters will be B, C, A, and from here we will make a call on move of 0. From here we will do a shift statement. So shift disk 1 from source to destination. Okay, so it is B to A. So we will say shift disk 1 from B to A. Okay, and then we will make a call on move of 0. That is also a base case. And from here two things are left. We will first print a shift statement. So shift disk what, n is 2 here, from B to C. Okay, from B to C. Okay, and here we will make a call on move disk n minus 1, which is 1. And as you can see in the third call, what we do, we basically exchange the first two parameters. Okay, so we exchange B and A. It becomes move 1 A, B and C. So it will again initiate 3 steps. One is a recursive call that leads to a base case. Then we have a shift statement. So shift 1 from source to destination. Okay, so source is A, destination is C, and finally we make a call on move of 0. Okay, so that is also a base case from where we actually return. So this is the entire recursion tree for the Tower of Hanoi problem. Now if you want to verify what steps have been executed, so you can clearly see the recursion tree executes in the left to right order. So firstly we will go into this branch that will execute this step. So this is the first step, shift disk 1 from A to C, which is correct. Next is this step, shift disk 2 from A to B, which is correct. Then the third is this step. Okay, we come in this branch, we go in this branch, shift disk 1 from C to B, which is correct. Then shift 3 from A to C, which is correct. Fourth is 1 from B to A, correct. 2 from B to C, 2 from B to C, and finally 1 from A to C. 1 from A to C. And you can see these are the steps: 1, 2, 3, 4, 5, 6, 7. So this is how we are able to solve this Tower of Hanoi problem using recursion. And you must be able to draw and understand this tree for other problems as well. Okay, so you can see if if we have done this question iteratively, it would have been very difficult for us to um, implement it as well. Okay, but this can be done using by taking a stack, but the implementation would have been much more complex. Okay, but this is the beauty of recursion. You can just do a lot of complex tasks by writing few lines of code. So that's all for this video. Thank you. Hi everyone. So we will discuss one very important concept this time, that is about finding subsequences or subsets of a given array or a given string. Okay. For example, you're given this string ABC. You need to generate all possible subsets of this particular string. Okay. So if you know the length of the input set is, let's say, 3, then in subset you can have 2 raised to the power 3 possible subsets. Okay, because for each character you have two options: either it will be in the subset or it will not be part of the subset. So it is 2 into 2 into 2 into, so that's equal to basically 8 subsets. So we have 1 2 3 4 5 6 7 and 8. So one thing to note is a subset can also have non-continuous character. For example, you can pick A, you can skip B, you can pick C. Okay, so if the question is about subarray, then subarray means a continuous part of the array. Okay, but a subsequence or a subset means you can also have you can also combine non-continuous parts of the array, like we have done in this example. So AC is a subset, and we can also ignore everyone. We can say we are not taking any character out of it, so it becomes a null subset. Okay, so you have 2 raised to the power 3, that is 8 possible subsets. Now we have to think how we can write a program that basically helps us to generate all possible subsets of this particular string. So let us take help from recursion and let's try to see how we can generate it. So let us assume our current string is ABC, and what we can do is we can say, okay, we know that for A we have two options, and for the remaining length of the string we will ask recursion to generate subsets of that particular part. Okay, so what we have two options: either we can have A with us, or we can say, okay, no, we are not going to have A, we are just going to generate subsets of BC, or we are going to have A and we are going to generate subsets of BC. Okay, so now if you solve this sub problem recursively, okay, you make a function call, you ask your function call to give me subsets of BC. So subsets of BC would mean you will get four subsets. Okay, so one will be a null subset, one would be B, one would be C, and one would be BC. Okay, and similarly here it would be null, it would be B, it would be C, and it would be BC. And in the first case you are saying I am also going to include A with it. Okay, so you say, okay, A plus this, A plus this, A plus this, A plus this. So what do you get? You get four subsets here, you get four subsets here, and if you see, these are all possible subsets. Okay, so this is A, AB, AC, ABC, null, B, C, and BC. Okay, so this is how you get all the possible 8 subsets of the string. So clearly the subset generation problem follows a recursive property. You just need to find out subsets for you need to handle the case for single character, and rest will be handled using recursion. Okay, so now we need to think how we can implement this in the form of a code. So there can be multiple ways to write the code for the same problem. Okay, but the way I'm going to write code is I'm just going to explain you the my way of writing code. Okay, so I'm assuming I will have an input array. Okay, so the input array will contain A, B, and C, and I'm assuming I will have a output array as well. So output array will be initially empty. So what I will do, I will say okay, start with the empty output array and start with this input. So what you do from here, you're going to make two calls, one by including a and one by excluding a. So if I include a, so in my output array, in one call I will have a, and if I do not include a, I will say this will be a empty array. Okay, so in the next call what I will do, I will keep a pointer as well. I will keep a pointer, let's say I, to denote the input index at which I am currently at. Okay, so when I go from this location to the next calls, I increment my input pointer to the next index, and I also increment my output pointer if I am keeping a character in the output array. Okay, so let's say there is a pointer j that is initially 0. So in this case j will come here, in this case j will remain at this particular index. Okay, so from here we will again make two calls. So at when we are at b, we will do two things. We will say okay, either we will keep b, so it will become ab, or we will not keep b, it will remain a. Okay, and similarly here, if we will keep b, it will become b. If we do not keep b, it will remain an empty array as well. Okay, and same goes here. So in the next level I will say okay, increment my I pointer, I will go to the next character, that is c. I will say okay, either keep c or do not keep c. If I do not keep c, it remains ab. If I keep c, it becomes ac. If I do not keep c, it becomes a. If I keep c, it becomes bc. If I do not keep, it becomes b. If I keep c, it remains c. If I do not keep, it remains null. And in the next step I will make a call, I will increment my I, it becomes input of I becomes null. So when input of I becomes null, what I will do, I will say I will terminate my output array with null and I will print it. Okay, so you will see we will get these answers: ac null, a null, bc null, b null, c null, and a null. Okay, so this will be null. So this is what we are going to do. So this is just an idea how I'm going to build my code, and let us first write the code and then we will see in little more detail how this goes on. Okay, so one thing to note here is this output array is the same array. We are not making copies of the output array. Okay, so how this code executes is, we first go in this direction, we go back, we come in this direction, and we update this old output array during this process. Okay, so here what actually happened is, so initially this array was abc null. So then what we do, if we come in this branch, we update c with the null value so that we get this output as ab null. Okay, so this is what actually happens while the recursion is executed. So let me first write the code and then we can go through it in once again. Okay, okay, so let's write the main function. So let's say we have input array that is equal to abc. We have, let's say, an output array that is, let's say, maximum length is 10, or it can be same as input plus 1. So okay, so what we will do, we will write a function void generate subsequence, where we will get the input array, we will also get the output array, we will get input pointer, we will get an output pointer j. Okay, so let's think of a base case. We can say if input of I becomes null, that means we have finished reading our input. So at the same time, what we can do, we can say in the output array at the jth index, you put a null, you print that output, and you return. Okay, so that's the base case. Otherwise, in the recursive case, you have two options. First option is you include the current character. Second option is you exclude the current character. Okay, so if you include the current character, that means in the output array at the jth index you copy the character from the ith index from the input array, and you make a recursive call on the remaining part. Okay, so the remaining part is uh, starts from I plus 1 and j will move to j plus 1 because you have already copied a character at the jth index. Otherwise, if you are excluding the character from the input array, what you can do, you can say, okay, I can simply do output of j equals to null. Okay, because if you want to override this character, then you can put it as null. Or even if you don't do this, you can simply call input output I will go to I plus 1 and j will not move. Okay, so if j does not move, that means whatever is the current value of output of j, that will be overwritten by some other value in the next call. Okay, so this is what is going to happen. Okay, so when you have to exclude the current character, you move the input index. Suppose you are at b and in the output you do not want to keep b. Okay, so if you want to keep b, you say, okay, I will copy b here and move the j index to the next place. If I don't want to keep b, I will keep j at the same index. Okay, and though there is a b present, but it will be written by some other value like null or c or some other in the next function call. So that's the entire code. Okay, so we can dry run this code again, and before that let us test our code. We can say generate subsequence, we give the input, we give output, I is 0 and j is also 0. Okay, this should be output. Okay, so you can see we are getting the correct output and this code is working perfectly fine. Okay, so we are now ready to dry run our code. Okay, so we have this input array that is containing ABC. We have an output array that is empty initially, and you can see both I and j are initially 0. Okay, so what happens in the first function, we basically make two calls. In the first call, we put the output of j equals to input of I. So we say, okay, what we are going to do, we are going to do this thing. We are going to say, okay, we will put what here, we will put in this output array, we will put input of I. So we put a here and we make a call with the value of I as 1 and the value of j as 1. Okay, I plus 1 and j plus 1. And similarly we make another call. Okay, now since this output array has changed, okay, so in recursion the arrays are passed by reference, so you make another call. In this call there is also a which is present here because it's the same output array, the same array. Okay, but what is the difference? In this call the j pointer is at this location, in this call the j pointer is at the 0th location only, so the j is at this location only. Okay, that means the value of j does not change. It's very important, you have to see this is what actually happens in the memory level. In this case the value of j is 1, in this case the value of j is 0. So what you do in this function call, when you come, you again make two calls. In one of the calls, what you do, you do output of j equals to input of I. Okay, so input of I means you put a b here, so that means it becomes ab, and you do I plus 1 and j plus 1, so I becomes 2 and j also becomes 2, so j comes here. And you also make another call that we will expand that call little later on. So the value of I will be 2, the j value will not change, it will be 1, but the array will be actually ab. Why? Because you have made changes in the array and those changes will be reflected here all as well. Okay, so what actually, okay, so the value of j is 1. Okay, so I'm not basically drawing b, but it is present, so that you know what it is going to be. So I'm just leaving this as empty. So yeah, so I'm just leaving this as empty here. Okay, so j is at this particular location. So in this function call, you again make two calls. Okay, so what you do input of I equals to output of j equals to input of I. So you put a c here. So value of I becomes 3 and the value of j also becomes 3. And you also do one thing, you say okay, I will increment the I pointer but I will not increment the j pointer, so j remains at 2. Okay, now in this function call you again come and you see input of I is actually what? Input of I is null. So what you do not make two function calls, you basically say output of j equals to null and you print it. So that means you do put null at the ith index. Okay, so output of j, so output of j at the jth index you put a null and you print this value and you return. Now this is a very important thing here. So when you return from this function call, what will happen is it will have a null here. Okay, and that means from here you will go to this step, it will have abc null here, and from here you will come to this step, it will also have abc followed by null here. Okay, now it's time to execute this particular call. Okay, so the recursion executes in the left to right order. So in this call, the value of I is 3, the value of j is 2. You will make two calls. Okay, so you will not actually make two calls. What you do is you see, in this case, if you see the function from this particular state, what happens is it will hit the base case. If input of I is null, input of I is null because I is 3 and that is null. So what do, you say output of j equals to null. So you say in the output I will put a null here at the jth location. The value of j is 2, so you put a null here. Okay, and this is what it becomes. And from here you backtrack, you go back to the previous function call after printing this output. So first output that you will get is abc, next output that you will get is ab. You go back, this will also become null. Okay, from here you go back to this function call, this array will also become ab null and null. From here you go back, this array will also become ab null and null. From here you come to this state, it will also become ab null and so on. Okay, so this understanding, this is really important. Okay, so rest of the recursion tree I think you can build, it's not very difficult. Okay, but if you want I can draw for some more cases. So let us see the see what happens in this function call ab null and null. This is the state of this array. Because arrays are passed by reference and j is at this location, that means we will actually overwrite this value. Okay, so now you suppose come in this function call, what will happen? So there will be two function calls. Okay, in the first function call you will say okay, in output of j equals to input of I, so you will put output of j. So j is at this index, so you will put a c here instead of b, and there will be null here, there will be null here. I will become 3 and j will also become 3. So from here you will hit the base case and sorry, j will become 2. What you will do, you will replace this null with another null. Okay, and you will print this string ac and you will return. Okay, from here you will return, and now this array will contain ac. From here you will make another call in which you do not want to uh, increment the j pointer, the second call. Okay, this call you will make, so that will say you will increment the value of I but you will not increment the value of j. So that would mean you have uh, so j will remain still at this location, it will be c, it will be null, it will be null. The value of I will become 3, the value of j will become 1. From here you will hit the base case, and in the base case you will say okay, output of j equal to null. Let's terminate this with a null, so this c will be overwritten with the null value. Okay, so this string will be a, and once you print this string, what you will get actually a. Okay, so from here you can see you are able to generate all the four you are able to generate four substrings. Okay, which contain the value a. And similarly, if you see this part of the tree, from here also you will be able to generate four substrings or four subsequences, sorry, not substrings but the subsequences, which do not contain the value a. Okay, so you will have a similar kind of a tree diagram at this side as well. So what you will get is you will get something like bc, b, c and null. Okay, so you can complete this tree on your own, and this is how recursion actually works in this case. Hi everyone, so we will discuss a problem in which we have to generate balanced brackets using n pairs of round brackets. Okay, for example, if n is 2, so we can generate one string like this. Another string that we can generate is like this. Okay, so using two pairs of brackets, only two combinations can be made. For example, if n is 3, then you have to use three pairs to generate a valid string. So one option could be this, another option could be this, another option could be this, another option could be this, and another option could be this. Okay, so you can see we are able to generate almost five different combinations. Okay, similarly for n equal to 2 we are able to generate two different combinations and so on. So we do not need to count, we actually want to print these number of uh, all possible strings. Okay, so each expression is a possible string. So let us see how we can solve this problem. So effectively, if we are given a n as, let's say, 3, we need to fill a string whose length is 6. Okay, so we need to fill 6 brackets in this string followed by a null character. Okay, so what I can do is I can basically keep a I variable, and at each position I can think of putting a opening bracket or I can put a closing bracket, but there will be some conditions based upon some conditions. So let us look at how we can do it. Okay, so clearly we know that at each position we have two options, either put an opening bracket or put an closing bracket, and the remaining part of the string will be filled using recursion. And in the base case we can say, okay, we are filling all the string, all positions. In the worst case, when we reach this index I equals to 2n, okay, at this index we can say we can stop. This will be our base case, and we can put a null. So let us assume we have built some part of the string, let's say n is 3, and suppose we are filling at this index currently. Okay, so what possibilities you can have? Can you put an opening bracket? Obviously yes, because the maximum opening brackets you can have in this string is 3, and currently you have only two opening brackets, so you can put a opening bracket here. Okay, let us see if we can put a closing bracket here at this index only. So yes, we can put a closing bracket. Why? Because to put a closing bracket we must have at least that number of opening brackets. Okay, so if you are putting a closing bracket, then the count of closing bracket should be less than the count of opening bracket. For example, if I go to this position, can I put a closing bracket? Yes, because count of closing bracket is less than the count of opening bracket. I go to this position, can I put a closing bracket here? No, I cannot put. So can I put a opening bracket here? Yes, I can put. Okay, because the max count of opening brackets should be less than the value of n in order to put a new opening bracket. Okay, let's go to next position. Can I put a opening bracket here? No, I can't, because n is 3 and already we have added 3 opening brackets in our string. Okay, so can I add a closing bracket here? Yes, because till now the string has 3 opening brackets and only 2 closing brackets, so that means you can put a closing bracket. Okay, so the conditions that you need to keep in mind is, at any index I, if you want to put a opening bracket, okay, if you want to put an opening bracket like this, the current count of opening brackets should be less than n. Okay, so if it is already equal to n or greater than n, okay, greater than n is not possible. If it is already equal to n, then you cannot put any more opening brackets in your string. Second is, if you want to put any closing bracket, okay, before putting any closing bracket like this, you need to ensure that the count of closing brackets, Okay, so count of closing bracket should be less than the count of opening bracket. Why? Because if the count is, if suppose if the count of closing bracket is already equal to open, then what will happen? If you put a closing bracket here, that will make a invalid expression. Okay, so that's why you have to take care of this condition as well. Okay, so these are two conditions that you need to see while uh, building a string. Okay, now we will come to the logic, how we can build it. For example, let's say n is 3. So what we can do, we can, or let's say n is 2. So let's say we start with an empty string. That means we will fill up to 4 positions. So can I put a opening bracket at this index? Yes, I can put. Can I put a closing bracket at this index? No, I cannot put. So I come to this function call. I will again make two calls. I will make two calls, one for the opening bracket, one for the closing bracket. Can I put a opening bracket here at this index? Yes, I can put, because the count of opening is less than n. Can I put a closing bracket here? Yes, I can put, because the count of closing is less than count of opening. So I put a closing bracket here. So again, can I put a opening bracket here? No, because count of open is already 2, which is equal to n. So we cannot put more opening brackets here. Can I put a closing bracket here? Yes, I can put. So it becomes like this. Okay, and again I will make two calls, one for the opening, one for the closing. Can I put a opening bracket here? No, I can't. Can I put a closing bracket here? Yes, I can. So this becomes like this. Again I make two calls, one for the opening, one for the, okay, so at this point, whatever call I will make, I will okay, so after this point you will see the value of I will become basically this. Okay, so this will actually become a base case. So from this we will hit the base case. Okay, we will not put any opening or closing brackets here, and we will hit the null value. Okay, so this index, as soon as I reaches this index, we will say okay, now it's a base case, we will print this. So the first answer that we will get is this. Okay, so this is one option. From here, can I put an opening bracket? Yes, so it will be like this. Can I put a closing bracket here? No, I can't put, because the count of closing, that is equal to the count of open. So I cannot put any more closing bracket here. From here I will make two calls. Can I put opening? No, I can't, because count of opening is 2, which is equal to n. So we will not do anything here. And from here what I will do is, can I put a closing bracket here? Yes, I can. So it becomes like this, and after that we will hit the base case, we will put a null here, and we will print our answer. So the second output that we will get is this. Okay, similarly for n equal to 3, n equal to 4, we can execute our code. Now let us try to write the same thing in the form of a code. So int n, scene n, let's create a input array, or let's say output array, and let's have a index equal to 0. So here I am taking the output array, the index at which currently I am working at, and I am taking a count for the opening bracket, and I am taking count for a closing bracket. Okay, so we will have a base case. If index, okay, we should also get the value of n. If index is 2 into n, then we can simply print our output and return. Okay, and one more thing we should do is, in the output at the index position we should put a null. Okay, in the recursive case we have two options. We have to call for both options depending upon the condition. Okay, so if I can check if the count of opening bracket is less than n, I can put an opening bracket. So I can say out of index equals to a opening bracket, and I can make a recursive call for the remaining part. So I can say generate brackets, out remains out, n remains m, index becomes index plus 1, open becomes open plus 1, close count remains same. The second option is, so it won't be else if, it won't be else if, it will be a if condition, because we have to make two calls and both calls are independent. So in some cases only one of those calls will execute, in some of the cases both calls will execute, and in some cases none of those calls may execute. Okay, so we have if the count of close is less than the count of open. Okay, so that's the condition on the closing bracket, and this also automatically ensures it is also less than n. Okay, because we are ensuring the count of open is less than n. So if close is less than open, then we can say out of index can have a closing bracket, and we can make a recursive call on the remaining part. So we give out n index close index plus 1, open remains same, close becomes close plus 1, and from here we can just put a return statement. Okay, so let's call our function generate brackets. We give the output array, we give n, we give index as 0, open as 0, close as 0. Okay, let me give n equal to 2, so you can see we are getting correct answer. Let me give n equal to 3, and you can see we are getting correct answer. Okay, so this is how we are able to generate it. So you can see the code is quite similar to generating subsets. So instead of putting a abc or some character in the output array, we are just putting opening or closing bracket based upon a condition. Okay, so in the subset problem we had two cases, include exclude. Here we have two cases, either put an opening bracket or put a closing bracket, and those cases are governed by some conditions that we have seen. Okay, so that's all for this problem, and thank you. Hi everyone, so we are going to discuss one very interesting problem called as 01 knapsack problem. Okay, so it's a very popular classical problem that we will solve in this video. So let's first discuss the problem statement. So it says there is a thief, and this thief goes to a shop to steal some items, but the problem with this thief is he cannot steal all of the items. He has a bag which has a fixed capacity. Okay, so it has a capacity C, and in this example let's assume the capacity of this bag is 6 kg. So that means he cannot hold more than 6 kg of weight in this bag. So let us discuss what's there in the shop as well. Okay, so shop contains several items. So each of the items has a weight, and each of the items has a price. For example, there is a bag of 1 kg and price is, let's say, 40. There is a ball of 2 kg, let's say price is 20. There is another ball of 3 kg, let's say the price is 35. And there is a uh, bat and ball of, let's say, weight 5 kg, and let's say the price is 100. Okay, so now you have to tell me what is the maximum profit that this thief can make, the maximum profit he can make. Okay, so if we want to fill the bag of up to, let's say, 6 kg capacity, one option is he can pick the 1 kg item, 2 kg item, and 3 kg item. Okay, so he can do 40 plus 20 plus 35, that is somewhere around 95 rupees. Okay, or we can do is he can pick the 1 kg item and he can pick the 5 kg item and he can make 140 rupees. Okay, or there could be another options, he could pick, let's say, yeah, so there can be multiple options. So he can pick anything that is even less than 6 kg, that is also fine. For example, let's say the capacity of the bag is 7 kg, then what you will pick? So in that case also you will pick the first and the last item, so you will again get 140 rupees. So you can pick anything that is less than equal to 7 kg. Okay, 140. So you have to tell me what is the maximum profit this thief can make by stealing those items and selling them later. Okay, so this is the problem. So can you think of something, some solution, some approach that we can apply in this question to solve this problem? Okay, so let's discuss the solution to this problem now. Now suppose there are multiple items. Okay, so let's say you have items A, B, C, D. So what you can do is you can start with the left to right or from right to left. You can pick one item from this direction, and this item now can have two options. Okay, so every item will have two options. Either you will pick that or you will reject that, or you pick it or you reject it, or you pick it or reject it, or you pick it or reject it. So idea is you try to make all possible subsets of items such that the total weight of items in that particular subset, okay, so total weight of items in that subset is less than equal to bag capacity, and out of all those subsets choose a subset such that profit is maximum. So this is what you have to do. Okay, so what we can do, we can say, okay, I'm going to start with the last item in the array. So if I pick that item, so let me just make this item as, so we have 0 1 2 3 up to n minus 1. For each item we have a weight, we have a price, w2 p2 w3 p3 and so on, wn minus 1 pn minus 1. So we have two arrays, one for weight and one for prices. So what I can say is, okay, let us pick the last item. So if I include the last item, what is the maximum profit I can make by including that item? So I can say it will be the profit that I get from the last item, that is p of n minus 1, plus the remaining profit from the remaining items. Okay, so let us assume there is a function profit which accepts the number of items in the array. Okay, and it also accepts the capacity of the thief. Okay, so I can see if I include this item. Okay, so if I include this item, what is the profit I will get? I will get p of n minus 1 plus I will get is profit of remaining items. So how many items are left? N minus 1 items are left. And what is the capacity of the bag that is left? So if you pick an item, suppose the bag capacity is 7 kg, and you pick an item which is having a weight of 3 kg. So what is the remaining capacity of the bag? So that capacity will be C minus the weight of the item you have picked. So the item you have picked is the last item, so its index is n minus 1, so you subtract it. So this is what it would be. Or what you can do is, if you are excluding this item, okay, so we have to take both the cases. Okay, so if you are excluding the current item, so in that case your profit that you will get will be 0, because if you're not going to take this item, so what you need to do, you need to solve a sub problem with n minus items. So you can call your recursive function profit, and you can say, okay, tell me what is the profit I can get by choosing a subset of items from the remaining n minus 1 items with the capacity of the bag that is equal to C. Okay, now you have two cases. The first case you only need to make when your current capacity of the bag, that is C, is greater than equal to the item that you are picking. Okay, so that should be equal to weight of the current item that you are picking. So current item has an index of n minus 1. So this will be nothing but, it will be maximum of this will be equal to profit of n comma c. So whatever is maximum, you will return it from the profit function, profit of n comma c. So this is the recursive formulation, and if you carefully see here, what we are doing is, it's nothing but we are making two cases at every step. Okay, so if you have a lot of items, you say, okay, if I take this item, I make this function call where in my profit I add the value of this item. Okay, so let's say this price is p, so I say, okay, this plus the profit I get from the remaining item. If I do not take this item, then it will be nothing but the profit that I get from the remaining item. So this is the exclude case, this is the include case, and similarly we make a recursion tree, and we will consider the maximum of these two cases to get the final answer for this one. Okay, so this is one sub problem, this is another sub problem. In this sub problem we reduce the capacity of the bag by the factor of, by the weight of current item that you have picked, weight of n minus 1. In this case the capacity of the bag actually remains same. So you can see these two sub problems are different. The number of items in both the sub problems remain same, but the capacity for which we are solving the sub problem changes. Okay, So let us talk about base case now. Now in this function call there are two variables that are getting updated. One is n, so we are reducing the problem in terms of n, we are also reducing the problem in terms of capacity. So we will have a base case that will depend upon both the value of n and c. So we can say if n becomes equal to 0, that means there are no items in the mall, then we can say we will get zero profit. Okay, otherwise we can say if there are number of, if the remaining capacity of the bag is 0, if c is equal to 0, then also we will say we will return 0 in that case. Okay, now let us try to write the code for this problem and solve it recursively. Okay, so let's write the code. So let's see the base case. If n is 0 or the remaining capacity of the bag is 0, we can say return 0. Okay, so very simple base case. Otherwise we can say in the recursive case we just need to write the recursive case for one item. Okay, so you have an array in which you have items from 0 to n minus 1. So let us just pick this item, or let's reject this item, and we will make this as a sub problem. So there will be two cases. If I include the last item, okay, so if I include the last item, in that case, or let me say I do not know what is my answer, so let's say answer is not known. Okay, let's say answer is 0, and let me say I have include, I will make two options. Okay, so I have variable include, exclude, include equal to int min. Okay, so I'm assuming I will make negative profit, but what can happen is I can say if I pick the last item. Okay, so if I pick the last item, then the profit I can make is, it will be the price of the last item. So I can say prices of the last item, that is n minus 1, plus the profit that I can make from the remaining n minus 1 items. Okay, so that will be n minus 1 c minus weight of the last item. Okay, so that is wt of n minus 1 that I have picked, and weight array will remain same, prices array will remain same. So this statement will execute only if this is greater than equal to 0. For example, the capacity of the bag is 6 kg and there is an item in the mall whose weight is 8 kg, then you cannot pick that item. Okay, so you have to make sure you put a if condition. If weight of the last item that you are picking is less than equal to the current capacity of the bag, only then you can include it. In that case, include will be equal to this, otherwise include will be equal to minus infinity, that means a very small value. Okay, or you can just put it as 0 as well. Okay, so if this sounds confusing, let us say it is 0. Otherwise I can say if you just exclude that item, okay, in that case your profit will be nothing but it will be the profit you get from the remaining n minus 1 items. The remaining capacity of the bag remains c, and weight and prices. That's it. Now you have solved two sub problems. So the first problem is the include one, and the second sub problem is the exclude one. In order to get the solution for the current problem, you have to just say your answer is going to be max of include comma exclude, and you can say return answer. So this answer is your solution to the current problem. Okay, so let's test our code. I can say cout profit, and here I give n, c, weights and prices. That's it. This should be capital N, right? And here also it should be capital N, it should be capital N, and okay, so code is complete. Let's run our code, and you can see the maximum profit that we are getting is 140. That means we pick the first and the last item to get the maximum profit in this case. So that's all for this video. Thank you. Hi everyone. So we will discuss phone keypad problem in this video. Okay. So what the problem says is you have the access to a smartphone and you press some numbers. Let's say you press the number 2 and 3. You have to generate all possible strings from this number. Okay. So 2 is mapped with ABC as you can see from the phone, and also 3 is mapped with DEF. Okay. So to generate a possible string, we have to consider all possibilities. So that means one possible, if we consider 2 as A, okay, so then B has three options. So it can become AD, AE, AF. If we consider 2 as B, it can become BD, BE, BF. And if we consider C, so it can become CD, CE, and CF. Okay, so basically 2 has three options, 3 has three options. So total number of possible strings that we can generate is 9. So the question is print all possible strings. Okay, so this is actually quite a useful application. For example, if you want to dial phone number to your mom, okay, so then what you need to press on your phone? You need to press 666. So what happens is your system automatically generates all possible strings. Let's say one possible string is mmm, one string is mnm, one is mom. Okay, so moo. So it generates all possible strings, and it will try to find in your contact list that if there is a name in which these strings lie as a substring. For example, mom is a string in your contact list, so you will eventually get the contact of your mom as a suggestion in the phone dialer app. Okay, so this is where this kind of an algorithm can be used. So we will use a brute force approach to generate all possible strings. For example, what we can do, we know we have an input array. Okay, so the input array, let's say, contains 2 and 3. We can say, okay, we will make an output array that is an array of characters, and we will read the first digit from here. Okay, and we can have more numbers, let's say 2, 3, 3, 4, 6, whatever. So what we can do is, for 2 we can make 3 calls, because 2 is mapped with 3 different digits, three different characters. So we can say, okay, if you are reading 2, you put A in your output array and try to fill the remaining array, or you put B in your output array and try to fill the remaining array, or you put C in your output array and try to fill the remaining array. Okay, so in the next call, okay, so let's say this is I was initially 0, and in this call I was at 1, I was at 1, I was at 1. And also we will take an index j to store uh, to denote the index of the position where we are feeding the output. Okay, so in this call we are at this index. Okay, so 3 is mapped with def. So what we can do is we can make 3 calls. So one by putting d in front of a, one by putting e in front of a, one by putting f in front of a. Similarly from here, bd, be, bf. Similarly from here, cd, ce, and cf. Okay, so something similar to the subsets part, and so on. So this will go on until we hit the null character in our input array. Okay, so finally at the end of this recursive branch, or at the base case, you will get the final string. Okay, for example, if it is only 2 3, you will get this, and you can just terminate it by adding a null in the end. Okay, so now let us try to write the code for the same, and let's see how we can implement it using recursion. Okay, so I have already generated a keypad array. Okay, so it's a 2D array. You can see it's stored like this. Okay, so keypad of 0, 0 is a null, 1 is mapped with null, 2 is mapped with ABC, 3 is mapped with DEF, and so on. Okay, so I have up to 9. So what I will do is, I will first write the base case, then I will write the recursive case, and in the main, what we can do, we can accept the input array from the user. Okay, and we can create output array which is empty array, and we can call this function generate names input output I0 J0. So I denotes the index of your input, and j denotes the index of your output array at which you are currently working at. So in the base case, you will terminate if input of I is null. That means you have reached the last position in your input string. So that means your work is done. So in that case, you will say, okay, let's terminate the output by adding a null at that last index, and we will print that output and we will return. Okay. So in the recursive case, what you will do, you will first extract the current digit. Okay, so current digit, for example, if you're reading this number 2 3 4 and so on, we just need to see what happens for 2. For this number, it will be done automatically by the recursive call. So we will get 2 as a character, so we will say, okay, digit is input of I, we want to convert it into integer, so we will subtract 0 as a character, so we will get 2. For example, if this has a ASCII value as 52, this has ASCII value, let's say 50, so difference will give us an integer. So I can say digit is nothing but it's input of I minus 0. Okay, now we need to know what all characters are mapped with 2. Okay, so we can say for int k equal to 0. So what I'm doing is, now 2 is also mapped with these characters A, B, C and null. Okay, so in the phone keypad here, so I say, okay, I will iterate over these characters and I'm taking a variable k to iterate over them. So I can say keypad of digit, so keypad of 2, that gives me ABC, comma k, that gives me each character is not equal to null. Okay, so I do k plus plus. So basically I'm taking a variable k to iterate over all of these. So what we need to do is, in the recursion, in the output array, we need to make 3 calls, one by putting a, one by putting b, one by putting c and so on. So what we will do, we will put the current character in the output and we will make a recursive call for the remaining part. So we can say output of j equals to keypad of digit comma k, so that is a, another time it is b, another time it is c, and fill the remaining part. Okay, so actually the way recursion is going to proceed is, let's say you are reading 2 and in the output you are filling a, and then you're saying, okay, fill this whole part, then you are making a call on b, you're saying, okay, fill this remaining part, you're making a call on c, and you're saying, okay, fill this remaining part. Okay, this is what we are doing. So first put a and then fill the remaining part by making a recursive call. Okay, so what we will do is, we can say print, oh sorry, it should be generate names, and here we should give the input array and the output array. Input will be increased by a value of 1, I plus 1, and output will be increased by 1, that will be j plus 1. So that's it, and we can put a return statement here. Okay, okay, so build is successful, so let's try to run our code. So let me give 2 3, and you can see we are getting all possible answers for 2 3. Let me give 1 1 2 3. So now there is some small problem that we need to handle in this case. So you can see we are not getting any output because 1 and 0 are mapped with null. Okay, so in that case this for loop does not work and we directly hit the return statement. So what we need to do, we need to put a special case. If digit is 1 or digit is 0, then what we need to do, we need to just skip that particular digit. Okay, so we will make a recursive call on the next digit in the input. So input will be increased by I plus 1, but the output will not increase. So let's build the code. And let's run it. So let's say 1 1 2 3, and you can see we are getting the output for 2 3. And let me try with one more example. Let's say 6 6 6, and you can see we will get 3 into 3 into 3, that is roughly 27 possible outputs, and there is an output called mom. So 666 refers to the mom phone number as well. So I hope you got an idea how we could solve this problem, and that's all for this video. And as a homework, you try to build the recursion tree for the entire problem by yourself. Hi everyone, so we will discuss one problem in this video. It's called generate strings. Okay, so what's given to you? You're given there is a mapping. Okay, so 1 means A, 2 means B, 3 means C, and 26 is mapped with Z. Okay, so yeah, this mapping is given to you, and you're also given a number in the form of a character array. So this is an array of numbers, you can say it's given to you, and you have to generate all possible strings that you can make from this array. Okay, so if 1 is treated as A, 2 is treated as B, 3 is C, and 4 is D, so this is one string you can generate. Okay, or you can say I will treat 12 as a number, and I will treat 3 and 4 as separate. So you can say this will be nothing but 12 is mapped with L, 3 is mapped with C, and 4 is mapped with D. So this is another string that you can make, and you cannot club 3 and 4 because 34 is not a valid number. So you have numbers only in the range 1 to 26. What you can do is you can actually club 1 and 23, and 4 can be treated as separate. So 1 is A, 23 is W, and 4 is D. So this is another string. Okay, so these are the three possible strings that you can make using this array. And if it is something like this 1 2 1 2, then you can also do 12 and 12, that is LL as a string, or you can say AB AB, it's a string. Okay, or you can do 1 21 and 2, this is also a valid string you can make. Okay, so A B, and this you can see whatever character it is. So this is the problem that you need to solve. So let's see how we can do it, but before that you must try it yourself. Okay, but it's quite similar to the problems we have solved earlier, just little bit of twist in the coding part and in the recurrence, and you will be able to solve it. Okay, so let's see how we can do it. So let's assume the number is 1 2 3 4. I will maintain two arrays, one for the input, one for the output. So assuming the output array, so I'm just going to draw how I'm going to think about this problem. Okay, so what I will do is at each step I will keep a variable, let's say I, to denote uh, the current index at which I'm currently standing at. Okay, so if I talk about this current index I, what I can do is I actually have two options. Either I can treat 1 as a number, or I can treat 1 and its next digit as a number. So suppose if I treat 1 as a number, then I can convert that 1 into A, and I can make a recursive call on the remaining problem, that is 2 3 4. Or what I can do, I can treat 1 and 2, that is 12 as a number, and I can convert this into L, and I can make a recursive call on the remaining part. Okay, and at this point again what I can do is I can treat 2 as a 2 as my current number, or I can treat 2 3 as my number. Okay, so if I treat 2 as my number, I can make a recursive call on 34, and if I treat 23 as my current number, I can say 23 is W, so I can make a recursive call on 4. That's it. Okay, so we have converted 23 into W. Here also we can say, okay, I will treat 3 as my current number, so that becomes LC. The remaining part is 4. We cannot treat 34 as a valid number, so this will not go anywhere. So we will terminate at this particular point. Okay, so okay, let's further do two calls. So here I can say 3 is my number or 34 is my number. If I just take 3, it becomes ABC, and remaining part is 4. I cannot take 34, so I do not make this call. Here also I just have only one option, so it becomes ABCD, and the remaining string that is left is a null string. So if this is the case, I terminate it on my base case. I make it as ABCD null. That's it. And here we have 4. So what we do, we say okay, there will be only one call. Okay, that will be AW. I replace 4 with D. So this is what I get. I do not make other call. Okay. And here also I have only one digit left. So there will be only one call. I do not need to make two calls because I don't have two numbers. Okay. So it becomes LCD. Null is left. So this leads to the base case. I make it as LCD null. This becomes my output. Similarly here it becomes AWD null. This is my output. Okay, so this is the recursion tree diagram, how we are going to work with this. Okay, so now let's quickly write the code for the same. So I can say, okay, so let's start by writing the main code. So I'm taking a array, I will take that as input, and I'm making another array for output. So output will store characters, and this will store digits. Okay, so that's my input array. So what I will do, I will accept my input array here. So char star in, char star out, input index I, output index j. That's what we have in the base case. If you reach till the end of your input array, so if input of I is null, or you can consider it like this: the smallest possible input is null, that's your base case. Then in the output you also put a null, and you print that output and you return. Okay, in the recursive case, what do you need to do? You have two options. You have to pick one digit at a time, and second is you have to pick two digit at a time. So we will see what to write in both of these cases. So one digit means pick the first digit, so that is input of I minus 0. Okay, so that converts this 1 into 1 as a character into 1 as an integer. Suppose you pick this one. Okay, so you want to convert this into an integer, so this becomes 1, and now you want to convert this into a. So what I will do is I will say char ch equals to digit plus a minus 1. So basically what we do is, if digit is 1, it is 1 plus a minus 1, so it becomes a. If it is 2, it becomes 2 plus a minus 1, so it becomes basically a plus 1, so that is b, and so on. Okay, for 26 you will be able to make a z, and after that you can say output of j, that's equal to ch. So you put that in your output, and you make a recursive call for the remaining part. Okay, so remaining part is generate strings. You give input, you give output. I will be moved by I plus 1 because you read one character from the input, and j will be moved by j plus 1 because you stored one character in the output. So this is the case when you have one digit at a time. Okay, so if you want to take two digits at a time, so firstly you need to check the next digit is not null. For example, if you are standing at 4 and you want to take two digits, so you should check the next should not be equal to null. So we can say if input of I plus 1 is not equal to null, so I will pick the ith digit and I plus 1th digit. So the second digit, it would be input of I plus 1 minus 0, and the number we will form. Okay, so what I'm doing here is, consider this case: you are at standing at 1 and you want to use 12 to make a w. Okay, so what you do, sorry, to make a l. So what you do, you pick 1, you pick 2, and you multiply this with 10 and add it 12 plus a minus 1. So this makes a l. So this is what we are going to do here. So number will be nothing but first digit into 10 plus second digit. Another check you want to make is the number should not exceed 26. Okay, so if this number is less than equal to 26, only then it is a valid number, otherwise just skip this one. So the character that we will make is, it will be nothing but number plus a minus 1. So we get the character and we put that character in our output array. So output of j equal to ch, and generate strings. Go do for the remaining part. Okay, so remaining part is input, output. I will now go to I plus 2 and j will go to j plus 1, because you used two inputs to create one output. Okay, so you used 1 and 2, that's to create one output, that is L. So I will be incremented by 2, j will be incremented by 1, and that's it. We can put a return statement here. Okay, so this is the code. So if I just show you what I have done is, this is your input array, this is your output array, this is your I, this is your j. I say okay, digit is input of I minus 0, so digit is 1, character is a, so I put output of j equal to ch. So I make a call in which I first put a and I make a call for the remaining part. Okay, so I put a here and I do it for the remaining part. In the another call, so j goes as j plus 1, so j comes here. Okay, and I goes as I plus 1, so this is the remaining string, so we are left with 2 3 4 here. In the other call, I say okay, I plus 1 is not null, so 2 is not null. I pick the second digit, that is 2. I form the number, that is 1 into 10 plus 2, that is 12. I see this is less than 26, so the character that I get is L, so this is L, and output of j equal to ch. So output of j, so this is now overwritten by L, and I make another function call. So this is now L, and you can see output of j. So we are overwriting at the same index. So earlier it was a here, now it is L here, and I create a new function call, and I say I plus 2 j plus 1. So the remaining numbers are 3 plus 4, because I goes from I plus 2 and j goes from j plus 1, so j comes here. Okay, and this goes on, and eventually we will end up getting the similar kind of a tree. So this is what it is. Okay, so let's run the code. We need to call the function as well. Okay, so it's generate strings, and here I give input, output, I is 0, j is 0, input is actually a. Okay, so let's try our code. So let's say 1 2 3 4 is the input, so we get these three strings. If it is 1 2 3, we get this, so that means it's working fine. 1 2 2 2 1 2. Okay, so yes, we are able to generate lot of strings. Okay, so there is one case we might have missed, is if there is a 0. Okay, so what happens if we have 1 0 1 2? So then we cannot take this 0 as alone, but we can take it with 1. So we can make 10 as L, but we cannot say it will be 1 followed by. So we can, if we take a single 0, we can just skip it. Okay, so try to write a code which also handles the 0 case. So that's your homework, you have to think about it.
Hi. So now we are going to discuss a very interesting rat in a maze problem, which is a backtracking based problem. So the question says that you are given a matrix which is of the size m cross n, means it has m rows and n number of columns, and our task is to move the rat from source is 0 0, and destination is the last cell, m minus 1 and n minus 1, and it is given that some of the cells are blocked, right? So let us say this is blocked, this is blocked, this is also blocked, right? So you have to find out all possible paths from the source to the destination, right? So maybe one of the path could be this, then you can have more number of paths like this. So lot of paths are possible, so your task is to find out all possible paths from the given source to the destination, right? So now let us see how we can approach this problem and solve it, right? तो सबसे पहले हमें क्या देखना है कि how to use recursion, right? How to reduce the problem and what is the recursive relation, right? Suppose you are standing at this point and there is one more condition, that the rat can move only in the forward and in the down direction. It has only two choices at every step, right? So if you move forward, if the rat moves to this cell, we know that the problem is reduced to this grid, right? बिकॉज ही कैनॉट कम बैक टू दिस सेल, यहाँ पे नहीं आ सकता दोबारा, राइट. अगर if the rat moves in the downward direction, we know that the problem is reduced to this grid. So you can see that in every, by taking one step, you are reducing the problem size. So if the grid is of the size m cross n, in the next step it will be either m minus 1 or n, or it will be m comma n minus 1. एंड ऐसे करते रहेंगे जब तक हमारा ग्रिड सिर्फ एक सेल का ना हो जाए. दिस इज द स्मॉलेस्ट प्रॉब्लम व्हेन सोर्स एंड द डेस्टिनेशन are at the same position, right? So let's say this cell is I comma j and this cell is, let's say, m comma n, right? Or m minus 1 or n minus 1. This is the cell, right? So what would be the base condition? That we have solved the problem if I becomes equal to m minus 1 and j becomes equal to n minus 1. And this is the base case. At that time we have to print the solution and we have to return true that we have solved the problem, right? And what about the recursive case? So in recursive case we have two options, that we will either go right, or we can go down, right? Now when to call go down or go right, so it will depend upon if you want to find a single path or if you want to check if the path exists. Then you can first call on the right side. If right hand side returns true, you do not need to check on the downward side, right? So you can keep a if else block, right? Or if else if block, right? And if a go down returns true, then we know that the multiple paths are possible, one from the right hand side and one from the down side, right? From the current cell. So this is the idea, and now there can be various ways to implement this. So you can implement a function for this part, or you can implement a function for this part, but in the current problem I'm going to solve for this part, that we are going to print all possible paths. So if you want to find out all possible paths, then you have to call on the right hand side. Even if the paths are found from the right hand side, you will still call on the downward side, so that you can find the other paths which are passing through this cell, right? So now the question arises, how do we store the path, right? So this is an important question, कि path को हम store कैसे करें, right? So the basic idea, the basic thing comes in mind is कि हम जहाँ जहाँ ट्रैवल कर रहे हैं, जो जिस हम सेल पे जा रहे हैं, एक बूलियन मैट्रिक्स ले लेते हैं या फिर एक इंटीजर मैट्रिक्स ले लेते हैं, उस सेल को मार्क करते रहेंगे. सपोज ये ब्लॉक्ड हैं सेल्स और मैं यहाँ से ऐसे जा रहा हूँ, यहाँ से मैं राइट गया, मैंने यहाँ पे 1 कर दिया, नीचे आया यहाँ 1 कर दिया, इधर गया यहाँ 1 कर दिया, इधर गया यहाँ 1 कर दिया, इधर गया यहाँ 1 कर दिया, एंड सो ऑन, राइट. अब ऐसा भी हो सकता है कि हम गलत डायरेक्शन में चले जाएं, राइट. सो ऐसा भी हो सकता है कि हम इस पाथ पे ना जाके, क्योंकि हम रिकर्जन यूज़ कर रहे हैं, तो इट विल ट्राई टू एक्सप्लोर ऑल द पाथ्स. तो ऐसा भी हो सकता है कि हम यहाँ से इधर गए, यहाँ से इधर गए, इधर गए, राइट. तो हमने यहाँ पे देखा, क्या हम राइट जा सकते हैं? राइट गए बट ये वाला सेल बंद था, तो व्हाट वी विल डू, वी विल कम बैक, वी विल रिटर्न फॉल्स एंड वी विल कम बैक. यहाँ से हम क्या डाउन जा सकते हैं? डाउन नहीं जा सकते, क्योंकि ये सेल भी बंद है. वी विल कम बैक, एंड जैसे इस सेल से हम वापस पीछे की तरफ जाएंगे, इस सेल को वापस क्या कर देंगे? 0. एंड इसी स्टेप को क्या बोला गया? बैक ट्रैकिंग, राइट. सो ऐसे रास्तों से वापस आना है जहाँ पे रास्ता नहीं है, राइट. तो डेड एंड्स है, यहाँ से हमें वापस आते वक्त क्या कर देना है? उस सेल को 0 कर देना है, राइट. सो अवर एजम्पशन इज़ कि हम जिस सेल पे जा रहे हैं, हम एज्यूम करेंगे कि वहाँ से रास्ता होगा, बट आगे जाके हमें पता चलता है कि अगर वहाँ पे रास्ता नहीं है, तो वी विल बैक ट्रैक एंड उस सेल को हम 0 कर देंगे, राइट. तो सिमिलरली यहाँ से वापस आएंगे. अब यहाँ से राइट से तो आ रहा है फॉल्स, नीचे जा सकते हैं, तो यहाँ 1 कर दिया. राइट जा सकते हैं, नहीं जा सकते, नीचे जा सकते हैं, यहाँ 1 कर दिया. राइट जा सकते हैं, राइट जा सकते हैं, नीचे राइट जा सकते हैं, नहीं जा सकते, नीचे जा सकते हैं, यहाँ 1 कर दिया, राइट. तो यहाँ पे क्या होगा? तो हमारा करंट सेल कौन सा हो जाएगा? ये हो जाएगा. तो बेस केस हिट होगा, एंड बेस केस में हमें पता है कि इस सेल तक पहुँचने के लिए हमने कौन कौन से सेल्स को फॉलो किया, तो यही हमारा पाथ हो जाएगा, राइट. तो अभी यहाँ पे प्रॉब्लम स्टॉप नहीं होगी, हम फिर से बैक ट्रैक करेंगे, क्योंकि हमें और रास्ते भी ढूंढने हैं. तो यहाँ से हम बैक ट्रैक करेंगे इस पाथ को प्रिंट कराने के बाद वापस गए, इसको ज़ीरो किया, यहाँ से वापस गए, इसको ज़ीरो किया, इस पे आए। अब यहाँ से हमने अभी सिर्फ राइट साइड को एक्सप्लोर किया, डाउन साइड को एक्सप्लोर नहीं किया। तो डाउन जा सकते हैं, जा सकते हैं, यहाँ पे 1 कर दिया। यहाँ से राइट जा सकते हैं, जा सकते हैं, यहाँ पे भी 1 कर दिया, राइट। तो फिर से हमने बेस केस को हिट किया क्योंकि हम लास्ट सेल पे पहुँच गए, राइट। हम क्या करेंगे, अब इस बार इस पाथ को प्रिंट कर देंगे, राइट। तो जितनी बार हम बेस केस में पहुंच रहे हैं, इसका मतलब उतने हमारे पास नंबर ऑफ वेज हैं। एंड हमारे पास एक 2D एरे के अंदर पाथ पड़ा होगा, उस पाथ को हम प्रिंट भी करवा सकते हैं, राइट। So I hope the idea behind the question is now clear, and we will now try to implement this using recursion and the backtracking, right? So let us see how we can solve this problem. All right, so let me take a grid, right? So let us define a maze, and we will also define one solution matrix, right? तो मेज़ मैंने बनाया हुआ है, तो दिस इज़ द मेज़, राइट। एंड यू कैन क्लियरली सी इसको हमने एक 2D कैरेक्टर एरे से इम्प्लीमेंट किया है। एंड सोल्यूशन के लिए हम एक मैट्रिक्स ले लेते हैं ऑफ साइज 10,10 विच इज़ बाय डिफ़ॉल्ट 0, ऑल ज़ीरोज़, राइट। कोई भी एलिमेंट इसमें फिल नहीं किया हमने। एंड यहाँ पे हमें एक फंक्शन बनाना पड़ेगा, लेट्स से बूल रैट इन अ मेज, राइट। फंक्शन रिटर्न करेगा कि पाथ एग्जिस्ट कर रहा है और या नहीं कर रहा है, एंड सारे पाथ्स को प्रिंट भी करेगा, राइट। इफ़ यू वांट यू कैन आल्सो टेक द इंट डेटा टाइप की कितने नंबर ऑफ पाथ्स हैं। So this function will accept the maze. This will also get the solution matrix. This will also get कि हम अभी कहाँ पे the coordinates of the current cell and the coordinates of the last cell, right? So base case we know that if I becomes equal to m and j becomes equal to n, right? तो coordinates है लास्ट सेल के m और n, right? तो हम क्या करें, क्योंकि लास्ट सेल पे आ गए हैं तो सोल्यूशन ऑफ m और n को हम कर देंगे 1 एंड पाथ प्रिंट कर देंगे, राइट। जो हमारे पास सोल्यूशन मैट्रिक्स में पाथ पड़ा है उसको हम प्रिंट कर देंगे, बट इसको थोड़ा सा बाद में करते हैं। एंड वी विल रिटर्न ट्रू, राइट, कि वी फाउंड अ पाथ, एक पाथ हमें मिल गया, राइट। एंड अब हमें क्या करना है, रिकर्सिव केस लिखना है, राइट। तो रिकर्सिव केस के लिए हमें कुछ कुछ कंडीशंस देखनी पड़ेंगी कि जो हमारा रैट है दैट शुड बी इनसाइड द ग्रिड, रैट कभी ग्रिड से बाहर ना जाए, राइट। तो रैट ग्रिड के अंदर होना चाहिए। इसका मतलब क्या है, इफ़ किसी पॉइंट पे आई अगर m से ज़्यादा हो गया और जे n से ज़्यादा हो गया तो रिटर्न फॉल्स, हम ग्रिड से बाहर नहीं जा सकते, राइट। एंड द सेकेंड कंडीशन इज़ कि वो सेल ब्लॉक नहीं होना चाहिए। इफ़ maze of ij equals to x means that cell is blocked, then also we will return false, right? So ये दो केसेस है जहाँ पे हम कुछ नहीं करेंगे, हम सिर्फ वहाँ से रिटर्न करेंगे, या तो डेड एंड सेल ब्लॉक्ड है या फिर हम ग्रिड से बाहर चलेंगे, राइट। अदरवाइज वी विल एज्यूम कि जो करंट सेल है उसके थ्रू सोल्यूशन एग्जिस्ट कर रहा है, राइट। सो एज्यूम सोल्यूशन एग्जिस्ट्स थ्रू करंट सेल। तो लेट्स सी, तो उसका मतलब ये है कि सोल्यूशन ऑफ आई जे इक्वल्स टू 1, राइट। सो ऐसा ज़रूरी नहीं है कि ये स्टेटमेंट हर बार ट्रू हो, हमारी अजम्पशन हो सकता है गलत हो, बट हमें ये अजम्पशन लेके चलना पड़ेगा, राइट। सपोज हम यहाँ पे खड़े हैं और ये सारे ब्लॉक्ड हैं, राइट। तो हम यहाँ से यहाँ गए, हमने 1 कर दिया, बट अब इस सेल के थ्रू सोल्यूशन नहीं है, तो हमें कैसे पता चलेगा। हम राइट जाएंगे, राइट से आएगा फॉल्स, हम डाउन जाएंगे, डाउन से भी क्या आएगा, फॉल्स। इसका मतलब क्या, राइट से भी रास्ता नहीं है, डाउन से भी रास्ता नहीं है, तो सोल्यूशन एग्जिस्ट नहीं कर रहा है। सो व्हाट वी विल डू, इसको हम ज़ीरो कर देंगे बाद में, राइट। तो राइट से आंसर मंगवा के देखते हैं राइट से क्या आंसर आ रहा है. So let us try कि if we are getting success from the right hand side, so we will call our function recursive function rat in a maze. एंड जैसे हम राइट पे कॉल करेंगे हमारा मेज छोटा हो जाएगा. सब प्रॉब्लम में हमने रिड्यूस कर दिया. आई हो जाएगा आपका i+1, सॉरी ये हो जाएगा i एंड j+1 एंड m और n वही रहेंगे. एंड सेम चीज़ हम डाउन के लिए कर सकते हैं. क्या हमें नीचे से रास्ता मिल रहा है? इट विल बी rat in a maze सॉल्यूशन i+1 एंड j. राइट, तो हमने राइट पे भी कॉल कर दिया है और डाउन पे भी कॉल कर दिया. राइट, एंड अब हमें क्या करना है? हमने दोनों तरफ कॉल कर दिया. राइट, तो अगर हमें राइट से सक्सेस मिला या फिर डाउन से सक्सेस मिला, एक भी जगह से अगर ट्रू आ गया तो हमें क्या बोलना है? हमें रास्ता मिल गया, रिटर्न ट्रू. अगर एक भी जगह से ट्रू नहीं आया तो हमें क्या करना है? रिटर्न फॉल्स. हमें रिटर्न कर देना है फॉल्स. राइट, एंड अब यहाँ पे एक बहुत इंपॉर्टेंट स्टेप आएगा कि अब यहाँ से क्या हो रहा है? हमने फंक्शन कॉल के बाद डिस्कस किया था कि फंक्शन कॉल के बाद जो स्टेप्स होते हैं वो वापस जाने वाले स्टेप्स होते हैं. राइट, तो रिकर्जन कॉल में अगर हम सपोज करो यहाँ से यहाँ गए, यहाँ से यहाँ गए, यहाँ गए और मे बी यहाँ पे आ गए, तो अब यहाँ पे क्या हो रहा है? बेस केस हिट हुआ एंड ये फंक्शन कॉल्स कंप्लीट हो चुकी हैं. दोनों फंक्शन कॉल के बाद जो कोड होगा वो वापस आते वक्त एग्जीक्यूट होगा. राइट, तो वापस आते वक्त आप क्या कर रहे हो? यहाँ से रिटर्न ट्रू या फॉल्स तो कर ही रहे हो, प्लस इस सेल को जब हमने 1 किया था इसको 0 भी करना है. राइट, तो रिटर्न करने से पहले जिस भी सेल से हम वापस जा रहे हैं वहाँ पे 0 करके जाएंगे. राइट, तो यहाँ पे बैक ट्रैकिंग का स्टेप आएगा कि जिस भी सेल पे आप खड़े थे सोल्यूशन आई जहाँ जहाँ पे आपने 1 किया था वहाँ पे उसको 0 भी करना है. राइट, तो वो कह रहा है आगे जाते वक्त हम 1 करते जा रहे हैं, बेस केस हिट हो रहा है तो हम उसको प्रिंट कर रहे हैं. उसके बाद हम जब बैक ट्रैक कर रहे हैं तो हम अपने सेल्स को 0 करते जा रहे हैं. तो इनिशियली सोल्यूशन मैट्रिक्स पूरा 0 था, फाइनली भी सारा 0 होगा. बस जब बेस केस हिट होगा तब हमारे पास रिक्वायर्ड पाथ स्टोर होगा. राइट, तो अभी हम इसको प्रिंट कर लेते हैं. लेट से पाथ कैसे प्रिंट होगा? सोल्यूशन मैट्रिक्स को अगर हम प्रिंट कर दें. राइट, so for int I equal to 0, I less than equal to m I plus plus, and then for int j equal to 0, j less than equal to n j plus plus. अब हम क्या करें? सोल्यूशन को प्रिंट करें. सी आउट सोल्यूशन ऑफ i and j followed by some space. ऑलराइट, तो यहाँ पे कॉल करते हैं फंक्शन को. सो यहाँ पे मेरे पास m और n की वैल्यूज़ क्या होने वाली हैं? नंबर ऑफ रोज इज़ 4 एंड द नंबर ऑफ कॉलम्स इज़ ऑल्सो 4. एंड जब मैं अपने फंक्शन को कॉल कर रहा हूँ तो इट नीड्स फ्यू पैरामीटर्स. राइट, हम देखते हैं कि आंसर एग्जिस्ट कर रहा है या नहीं कर रहा. सो रैट इन अ मेज, we give the maze, we give the solution matrix. Starting cell is 0 0 and the ending cell is m minus 1 and n minus 1. Right, so if answer equals to false, we will say that the path does not exist. Otherwise हमारे सारे path print हो जाएंगे. Right, अदरवाइज हमारे पाथ तो प्रिंट हो ही जाएंगे बिकॉज हम यहाँ पे प्रिंटिंग कर रहे हैं. राइट, सो लेट अस रन अवर कोड. ऑलराइट, तो एक हैंडल यहाँ पे और दे रहे हैं सो दैट वी आर एबल टू डिस्टिंग्विश बिटवीन द पाथ्स. राइट, ऑलराइट, सो हमारे पास मल्टीपल पाथ्स आ गए हैं एंड इनको हम काउंट भी कर सकते हैं. राइट, इफ़ यू वांट टू काउंट द पाथ्स यू कैन have a integer data type and you can increment the count in the base case. So let us see this maze and the paths we got. Right, so there are multiple paths. So this is the maze. Right, so you have a maze of size 4 cross 4 and this is blocked, this is blocked and this is blocked. Right, So you will get paths through this cell, right? So one of the paths, if we see this path, it is this path, right? This path, right? And there will be more paths, right? And from these cells, the path will be there, right? So you can see that we are able to generate all the paths and with the help of backtracking, right? So the most important step is this, right? Because when you're going back from a particular cell, even if it was right or it was wrong, you have to make it zero, right? Because you're backtracking and you do not want it should remain one, otherwise you will get a wrong answer, right? And this is something very obvious कि we are reducing the problem. This is like the recursive case, right? Recursive case, you will try both the directions, right? So if you had a case like कि सिर्फ हमें find out करना path है या नहीं, then you will need only one of the calls. अगर right से हमें true मिल जाता है, so we do not need to call on the down part. But अगर right से false मिलता है तो हमें down पे भी call करना पड़ता. But since यहाँ पे हमें दोनों चीज़ें करनी थी, हमें सारे paths निकालने थे, तो right पे भी हम call करेंगे, हम down पे भी call करेंगे, right? So I hope this is quite clear and you will try this problem yourself as well and try to implement the solution which counts the number of paths. All right, so thanks for watching. I will see you in the next tutorial.
Hi guys, we are now going to talk about permutations problem, and from this problem onward we are going to learn the concept of backtracking in recursion, right? So very important step, important technique which is called backtracking, right? So we will make the use of this technique in this problem and you will see how this is being used and in what all problems you will need this technique, right? So we will learn more about it, but first let us try to understand what is this problem of permutation, right? So the question says you're given a string, let's say the string is abc, and you want to find out all possible permutations of the string, right? So these permutations could be a lot of, right? So you can have 3 factorial permutations and you will get 6 permutation, right? So it could be abc, it could be acb, bca, cab, and bac, c, cba, right? So you will get all these 6 permutation, right? Now the idea is we want to write a program which computes all these permutations automatically, right? So let us think about that also, right? So let us now try to think recursively, right? So अगर हमें इस चीज़ को खुद से करना होता, सो व्हाट अप्रोच वी वुड हैव फॉलोड. सो यहाँ पे भी हमने क्या किया है, हमने किया है कि हम ए को आगे रखेंगे और जो हमारा रिमेनिंग पार्ट होगा बी सी उसको हम परम्यूट करेंगे, राइट? या फिर दूसरा ऑप्शन हमारे पास आता है कि हम बी को आगे रखेंगे और जो हमारा रिमेनिंग पार्ट है, बी को हमने एज अ फर्स्ट करेक्टर रखा और जो हमारा रिमेनिंग पार्ट है दैट इज़ ए सी, इसको परम्यूट करेंगे. एंड थर्ड ऑप्शन इज़ कि हम सी को आगे रखेंगे एंड जो हमारा रिमेनिंग पार्ट है बी ए उसको परम्यूट करेंगे, राइट? सो अब रिमेनिंग पार्ट के हमें पता है, राइट? सो एन फैक्टोरियल परमुटेशन हम कैसे निकालेंगे, एन ऑप्शन ये होगी एंड रिमेनिंग पार्ट कितना होगा एन माइनस वन, इसके परमुटेशंस निकाल लो, राइट? सो इसके जब हम परमुटेशंस निकालेंगे तो वो क्या निकलेंगे, बी सी एंड सी बी. सिमिलरली वी विल गेट हेयर सी ए एंड सिमिलरली यहाँ पे हम वी विल गेट ए बी एंड सी सबके साथ लगाया, बी लगाया एंड ए लगाया, राइट? सो यू कैन सी दैट ए से स्टार्ट होने वाले ये परमुटेशन हैं, बी से स्टार्ट होने वाले ये परमुटेशन एंड सी से स्टार्ट होने वाले ये परमुटेशन, राइट? सो हमारे पास ऑल एन फैक्टोरियल परमुटेशंस आ गए हैं, राइट? नाउ वी हैव टू सी कि हम इसको कैसे जनरेट करें, राइट? सो एक काम करते हैं, इसको थोड़ा सा सोचना स्टार्ट करते हैं कि हमारे पास स्ट्रिंग था ए बी सी, राइट? सो यहाँ से हमने क्या किया, वी मेड 3 कॉल्स, राइट? तो फर्स्ट कॉल में हमने ए को ए से रिप्लेस किया तो स्ट्रिंग ए बी सी रहा और कॉल कहाँ पे किया, हमने बी से पे किया. एक बार हमने ए को बी से स्वैप किया, राइट? सो बी यहाँ पे आ जाएगा और हम क्या करेंगे, ए सी यहाँ पे आ जाएंगे और ए सी के परमुटेशंस निकालेंगे. एंड एक बार क्या होने वाला है, ए सी से स्वैप होगा एंड हम परमुटेशंस निकालेंगे बी ए के, राइट? तो ये हमारे पास आ जाएगा, राइट? अब एक काम करते हैं, सेम प्रोसेस रिपीट करते हैं हर एक नोड के लिए, बिकॉज रिकर्जन में तो सब प्रॉब्लम भी तो सेम टाइप की प्रॉब्लम होती है, तो हम यहाँ पे भी सेम चीज़ करेंगे। एंड यहाँ पे हमारे पास सब प्रॉब्लम सिर्फ बी सी है, तो बी को बी से रिप्लेस किया, सी पे कॉल कर देंगे। बी को हमने सी से रिप्लेस किया, तो हम सी बी पे कॉल कर देंगे, और ए एज इट इज़ हमारे पास ऑलरेडी था, वो तो रहेगा ही। यहाँ पे ए को ए से रिप्लेस करेंगे, तो हमारे पास बी ए सी बनेगा, और सी पे कॉल किया। ए को सी से रिप्लेस करेंगे तो बी सी ए बनेगा, राइट, बी सी ए, राइट। एंड यहाँ पे भी वी विल गेट सी बी ए, एंड बी को ए से रिप्लेस किया तो वी विल गेट सी ए बी, राइट। सो यहाँ पे हमें लग रहा है कि हाँ सारे परमुटेशंस बन गए, राइट। एंड इसके बाद भी हम एक स्टेप फॉलो कर सकते हैं कि सी को सी से रिप्लेस किया और आगे कॉल किया। जैसे ही हम आगे कॉल करेंगे, आगे तो नल पड़ा है, तो हमारा परमुटेशंस ए बी सी रहेगा, यहाँ से हमारा ए सी भी रहेगा, यहाँ से बी ए सी रहेगा, एंड यहाँ से बी सी ए रहेगा, राइट। यहाँ से हमारा सी बी ए, एंड यहाँ से हमारा सी ए बी। ए की कॉल होगा बिकॉज आगे नल करेक्टर है, तो वो किसी से रिप्लेस नहीं होगा। जैसे ही हम नल एनकाउंटर करेंगे इनपुट में, हम रुक जाएंगे और ये हमारा आउटपुट प्रोड्यूस हो जाएगा। अगेन दिस इज़ अ बेस केस, राइट। बेस केस में जनरेट हुआ है, तो हम प्रिंट कहाँ पे करेंगे, बेस केस में प्रिंट करेंगे, राइट। तो आई होप रिकर्जन ट्री समझ आ गया क्या हम करना चाह रहे हैं, एंड इसी चीज़ को हम कोड के फॉर्म में इम्प्लीमेंट करके देखते हैं कि हमारा सही आंसर आ रहा है या नहीं आ रहा, राइट। सो लेट्स से यू हैव अ इनपुट स्ट्रिंग जो यूज़र इनपुट देगा, और वो इनपुट हमने ले लिया है, एंड यहाँ से हम रिटर्न कर रहे हैं। एंड यहाँ पे हमारे पास एक फंक्शन है void permute, एंड इनपुट में हमारे पास क्या आ रहा है, एक स्ट्रिंग, राइट, एक करेक्टर एरे। एंड हम एक अलग से आउटपुट एरे नहीं ले रहे, उसी के अंदर ही हम काम करने वाले हैं, राइट। सो इफ़ यू वांट यू कैन टेक अ एक्स्ट्रा आउटपुट एरे, बट अभी हम उसी इनपुट एरे में चेंजेस करने वाले हैं। एंड आई डिनोट कर रहा है कि कौन से इंडेक्स तक का काम हो चुका है, कहाँ तक हमने स्ट्रिंग को ऑलरेडी प्रोसेस कर लिया, या फिर रिमेनिंग पार्ट कहाँ से हमारा स्टार्ट हो रहा है। सो परम्यूट को कॉल करेंगे, एंड इनपुट एरे, एंड स्टार्ट हमारा 0 से होगा, राइट। तो सबसे पहले हमें फिगर आउट करना है कि बेस केस क्या होगा, एंड सेकेंड थिंग इज़ रिकर्सिव केस क्या होगा, राइट। सो बेस केस में हमें पता है कि हम क्या कर रहे हैं, यहाँ पे तो हमें ऑलरेडी पता है। तो वैसे अगर हम सोचें कि अगर एक इनपुट एरे है हमारे पास और उसको हमें परम्यूट करना है, राइट। सो अगर इनपुट आई नल है, मतलब इनपुट में कुछ है ही नहीं, सबसे छोटा इनपुट है, तो उसका कुछ परमुटेशन भी नहीं निकलेगा। तो वी कैन डायरेक्टली से दैट सी आउट कर दो इनपुट एंड रिटर्न, कुछ मत करो, बस उसको प्रिंट कर दो, राइट। बेस केस में हमें जो भी स्टेट होगी इनपुट एरे की वो हमें दिख जाएगी, एंड रिटर्न कर दिया हमने वहाँ से। रिकर्सिव केस में हमें क्या करना है, राइट। सो कोई भी नोड ले सकते हैं और हम रिकर्सिव केस देख सकते हैं, राइट। सो अभी के लिए हम बोल रहे हैं कि आई हमारा यहाँ पे है, और ये जो वेरिएबल है, ये वेरिएबल जे है, एक बार ए पे गया, एक बार बी पे गया, और एक बार सी पे गया। यहाँ पे भी आई हमारा यहाँ पे है, और जे वेरिएबल एक बार बी पे गया और एक बार जे सी पे गया। तो हमने दो वेरिएबल लिए हैं। आई डिनोट कर रहा है कि कौन से स्ट्रिंग पे, कौन सी पोजीशन पे काम हो रहा है, और जे क्या कर रहा है, वहाँ से लेके आगे तक सब पे आइट्रेट कर रहे हैं, राइट। सो यहाँ पे से सब पे आइट्रेट कर रहे हैं, यहाँ पे इतना ही है बस, राइट। सो ऊपर ब्लू वाली लाइन हमारा जे का ट्रेवर्सल डिनोट कर रही है, राइट। सो हमें क्या करना है, जो हमारा जे है वेरिएबल, वो स्टार्ट होगा आई से, वो जाएगा कहाँ तक, जब तक स्ट्रिंग खाली नहीं हो जाता। सो इनपुट ऑफ जे इज़ नॉट इक्वल टू नल, एंड वी आर गोइंग टू डू जे प्लस प्लस, राइट। एंड अब यहाँ पे हम चेक कर सकते हैं इफ़ की ज़रूरत नहीं है, स्वैप ही करना है हमें, राइट। सो हमें क्या करना है, स्वैप कर दो एरे ऑफ आई को विद एरे ऑफ जे, एंड आगे कॉल करो, राइट। सो यहाँ पे हमने क्या किया था, एक बार ए को स्वैप किया था ए से और इस पे कॉल किया था, फिर एक बार ए को स्वैप किया था बी से और इस पे कॉल किया था, और एक बार स्वैप किया था ए को सी से और इस पे कॉल किया था। तो सेम ही चीज़ हम यहाँ पे लिख रहे हैं, ठीक है। सिर्फ इतने केस को एनालाइज करके हम अपना लॉजिक लिख रहे हैं, बिकॉज हर एक रिकर्सिव केस में सेम ही चीज़ होती है। तो आगे कॉल करने का मतलब क्या है, परम्यूट कर दो आई को इनपुट एरे वही रहेगा और आई हो जाएगा i+1, राइट। सो ये हमने यहाँ पे चेंजेस कर दिए, राइट। सो ए नहीं होगा, यहाँ पे इनपुट होगा, राइट। सो इट शुड बी इनपुट एंड यहाँ पे भी इनपुट होना चाहिए, राइट। सो एक बार इतने प्रोग्राम को रन करके देखते हैं कि व्हाट इज़ द आउटपुट। सो इनपुट देना चाहिए हमें, और यहाँ पे मैं लेट्स से कॉमा दे देता हूँ एंड लेट अस इनपुट इज ABC, और यहाँ पे हमने रीड भी कर लिया, राइट। सो ऑल राइट, सो कुछ आउटपुट आया है, बट इज दिस आउटपुट करेक्ट? नो, इट इज़ नॉट, राइट। सो वी कैन क्लियरली सी क्या हो रहा है यहाँ पे कुछ रिपीट हो रहे हैं, राइट। सो ये रिपीट हो रहे हैं एंड हमारे बी वाले परमुटेशंस गायब है, BCA इज़ नॉट देयर, BAC इज़ नॉट देयर, राइट। सो ये दो एक्स्ट्रा आ गए और ये दो मिसिंग हो गए। सो ऐसा क्यों हुआ, इसको हम अभी एनालाइज करेंगे थ्रू द ड्राई रन ऑफ दिस प्रोग्राम, राइट। सो इसको ड्राई रन करते हैं एंड देखते हैं कहाँ पे गलती हो रही है। सो लेट अस सी, राइट। सो यहीं से हमारा कॉन्सेप्ट स्टार्ट होगा बैक ट्रैकिंग का। सो केयरफुली लुक एट दिस थिंग, राइट। सो इनपुट था हमारे पास ABC, तो हमने क्या किया, फर्स्ट टाइम हमने A को A से स्वैप किया तो हम इधर आ गए, फिर हमने इस पर कॉल किया। सो B को B से स्वैप किया, हम फिर से इधर आ गए, अभी तक सब सही चल रहा है। फिर हमने C को C से स्वैप किया और हम इधर आ गए, एंड फिर हमने नल पे कॉल किया, ABC, यहाँ पे नल था तो हमने इसको प्रिंट कर दिया ABC को, तो यहाँ तक सब सही है। अब यहाँ से जब प्रोग्राम कंट्रोल वापस गया तो कुछ भी चेंज नहीं हुआ, एंड सिमिलरली यहाँ से वापस गया, राइट। तो इस पॉइंट पे B स्वैप होगा C से, तो हमारा जो स्ट्रिंग बन जाएगा वो ACB बन जाएगा, और B को B से स्वैप करेंगे तो हमारा ACB बन जाएगा, राइट। तो यहाँ तक भी सब सही था। यहाँ से हम वापस गए, यहाँ से भी हम वापस गए, बट जैसे ही हम इस पे वापस आए यहाँ पे, तो हमारा स्ट्रिंग अब ABC नहीं रहा, वो क्या हो गया ACB, बिकॉज ये चीज़ एक एरे थी एंड वी नो एरेज जो हैं वो बाय रेफरेंस पास होते हैं। तो अगर एक बार एरे में चेंज हो गया वापस आते वक्त, वो चेंज वापस रिस्टोर नहीं होगा। तो एरे यहाँ पे क्या हो गया ACB, एंड यहाँ पे भी क्या हो गया ACB, एंड यहाँ पे भी क्या हो गया ACB। तो अगली बार एक इससे स्वैप होगा, C से स्वैप होगा, तो यहाँ पे बन जाएगा CAB, एंड जब इसके परमुटेशन हम निकालेंगे AB के, तो एक बार निकलेगा CAB और एक बार हमारा निकलेगा CBA, राइट। तो जब हम CBA से वापस जाएंगे यहाँ से, तो हमारा ये एरे क्या हो चुका है CBA, एंड यहाँ से जब हम वापस जाएंगे तो हमारा ओरिजिनल एरे अब क्या हो चुका है CBA। तो फाइनली अब स्वैपिंग किस में होगी, स्वैपिंग हमें पता है इसकी इस इंडेक्स की इस इंडेक्स के साथ स्वैपिंग होनी थी, तो हमारे पास स्ट्रिंग क्या आ जाएगा ABC, और इसके परमुटेशन हम निकालेंगे, क्या निकलेंगे ABC, और यहाँ पे क्या निकलेगा ACB, राइट। एंड यहाँ से जब हम वापस जाएंगे तो हमारा ये स्ट्रिंग हो जाएगा ACB, एंड ये स्ट्रिंग भी क्या हो जाएगा ACB। सो ये फाइनल स्टेट होगी। तो आउटपुट में क्या आ रहा है, आउटपुट में ये आ रहा है, राइट। दीज ऑल आर द आउटपुट्स, ABC, ABC, ACB, CAB, CBA, ABC एंड ACB। सो यू कैन क्लियरली सी ये दोनों और ये दोनों सेम है, ये रिपीट हो रहे हैं, एंड हमारा BCA और BAC गायब हो गए हैं, राइट। सो दिस इज एग्जैक्टली हाउ दिस प्रोग्राम इज वर्किंग। एंड इसी चीज़ को हैंडल करने के लिए हमारे पास एक कॉन्सेप्ट है विच इज़ कॉल्ड बैक ट्रैकिंग, राइट। सो बैक ट्रैकिंग अभी देखते हैं हम, बैक ट्रैकिंग का क्या मतलब है। तो बैक ट्रैकिंग को देखते हैं कैसे होगा, राइट। सो देखो यहाँ पे हमारे पास जो ओरिजिनल एरे था, तो उसमें एक्चुअल में कोड ऐसे काम करना चाहिए था, बट ऐसे काम नहीं किया। वाई? बिकॉज हमने वापस जाते वक्त एरे को रिस्टोर नहीं किया। यहाँ से जैसे ही एरे ACB हुआ, यहाँ से जब हम वापस गए तो उसको ABC बनाना था, राइट। तो हमें क्या करना पड़ेगा, जिस स्वैप से यहाँ पे नीचे आए थे उसी स्वैप को ऊपर जाते वक्त अंडू करना पड़ेगा, राइट। तो हमने डिस्कस किया था कि फंक्शन कॉल जब हम करते हैं, एक फंक्शन के अंदर फंक्शन कॉल करते हैं रिकर्जन में, तो दो डायरेक्शंस होती हैं। सो फंक्शन कॉल से पहले जो कोड होता है वो नीचे जाने की डायरेक्शन होती है, एंड फंक्शन कॉल के बाद जो कोड होता है वो ऊपर आने की डायरेक्शन होती है, राइट। इसका मतलब ये है कि हमने नीचे जाते वक्त जो एरे में चेंज किया था, उसी चेंज को दोबारा से हम कर देंगे तो हमारा ओरिजिनल एरे रीस्टोर हो जाएगा, राइट। सो हमें ए बी सी से हमने ए सी बी कैसे बनाया था, बी और सी को स्वैप करके। तो अगर वापस जाते वक्त इन दोनों को फिर से स्वैप कर दें तो हमारा ओरिजिनल एरे क्या बन जाएगा, ए सी बी, ए बी सी बन जाएगा। यहाँ से ऊपर जाएंगे तो फिर से ए बी सी रहेगा, नीचे आएंगे तो बी ए सी बनेगा, बट जब और ऊपर जाएंगे तो फिर से क्या बन जाएगा, ए बी सी। सो आइडिया हेयर इज टू रीस्टोर द ओरिजिनल एरे, बिकॉज एरे जो है वो बाय रेफरेंस पास हो रहा है एंड हम नहीं चाहते कि हमारा एरे ख़राब हो जाए, सही, ठीक है। सो हमें ओरिजिनल एरे को रीस्टोर करना है एंड ये तब हो पाएगा अगर हम किसी भी नोड से वापस जा रहे हैं तो हम पिछली कॉल में जो एरे की स्टेट थी उसको रीस्टोर कर पाएँ। एंड वापस जाने वाला काम कब होता है, फंक्शन कॉल के बाद। एंड वो स्टेप क्या होगा, इट विल बी द सेम स्वैप जो हमने नीचे जाते वक्त स्वैप किए, वही स्वैप हम ऊपर आते वक्त भी कर सकते हैं। सो दिस स्टेप here is called backtracking to restore the original array। एंड अगर ये हम कर लेंगे तो हमारा जो फंक्शन होगा वो एज एक्सपेक्टेड बिहेव करेगा, जैसा हमें चाहिए। तो एक बार रन करते हैं इसको। सो यू कैन सी आउटपुट इज ए बी सी, ए सी बी, बी एस सी, बी सी ए, सी बी एंड सी ए बी, विच इज़ परफेक्टली फाइन। दिस इज़ वॉट वी नीडेड। सो एक बार आई विल सजेस्ट यू टू ड्राई रन इट योर सेल्फ एंड you can ask if any doubts are there in the comment section. So thanks for watching. I will see you in the next tutorial.
Hi everyone, in this video I'm going to show you one example of set STL, okay, and how you can use this in solving a problem. So the question we are discussing is about finding permutations of a string. For example, the string is like this and you know how to permute it, okay. You say, okay, I will keep A at first place, I will permute BC. I keep B at first place, I permute AC, and I can keep C at first place and I can permute BC. So if you permute BC, you can get ABC and ACB. If you permute AC, you can get BAC and BCA. And if you permute this part, you can get CBC, CBA and CAB. Okay. So now the question is, suppose you're given a string like this, A, B, B, and you want to generate permutations. Okay. So if you follow this same method, you will end up having redundant permutations. Okay. So suppose I want to get unique permutations and I want to get these permutations in a lexicographic sorted order, okay. So what I can do, I can generate permutations and I can store all of them inside a set data structure, okay. And set is going to do both of the things for us. So let us see how we can apply set to a function in which we have already written the code to find permutations. So if I just run this code and give some input like ABC, you can see this generates this particular output. And if I change the string to ABA, again I will get 3 factorial permutations, that is 6, but number of unique permutations should be less, okay, because A is repeating twice. So what we are going to do, you can see some of the permutations are getting repeated here. So what we can do, we can include set, we can also include the string header file, and what I'm going to do, in main I'm going to maintain a set, okay, set of strings, and let's call it as S, and to the permute function I'm going to pass in the set, okay. So here we will also accept the set of strings by reference, and what I do, instead of printing the output here, I can say, okay, I will make a string T and I will initialize this string from array A, that is my current output, that is going to be printed on the string on the screen. And now I can push this string object inside my set, okay. So I can say s dot insert T. So this string that was initially output is not an output now, it will go inside the set, okay. And if there are any strings that are redundant, then set will maintain only the unique strings, okay. So once you're done, so what you need to do, we also need to pass in the set at this in the function call, okay. So after the permute function is over, all the strings are inserted in the set and only unique ones are stored, okay. So loop over the set and print all the strings for, let's say, auto s in uh, or auto, let's say, str that is in this s, see out that particular string. Okay, so let's see the output now. So now this set is going to store only the unique strings, and you can see with three characters in which two are repeating, you are going to get 3 factorial upon 2 factorial, that is three distinct permutations. Okay, so this is how you can use set in a practical problem, and you can have more number of examples. Okay, so that's all for this video. Thanks a lot, guys. So let's see the n queen problem. Okay, so question says in a n cross n chessboard, you have to place n queens such that all queens are safe and no queen cuts each other, right? So there is no direct way, we have to try for every position. हर एक position पे हमें हर एक queen को रखना पड़ेगा, right? So what we can do is we can place a queen in the first row. Let's say मैं इसको row by row fill करता हूँ. I can either go it row by row. रो बाय रो क्यों? बिकॉज आई नो हर एक क्वीन में, हर एक रो में एक ही क्वीन होगी, राइट? देर कैन नॉट बी अ रो और अ कॉलम विच हैज़ मोर देन वन क्वीन, राइट? So what I can do is I can place one queen in every row. I can place one queen in every row. So let's say पहली queen को मैं यहाँ पे रख देता हूँ, रख दी, and I call on the smaller part. Smaller part पे मैं call कर देता हूँ. This is the smaller part, right? So इसके लिए कौन सॉल्व कर देगा? रिकर्जन सॉल्व करके मेरे को देगा, राइट? तो रिकर्जन मेरे को क्या देगा? ट्रू और फॉल्स. इज इट पॉसिबल टू प्लेस अ क्वीन और नॉट? इज इट पॉसिबल टू प्लेस अ क्वीन और नॉट? तो ये मेरे को कौन बताएगा? मेरा रिकर्सिव फंक्शन मेरे को बताएगा, राइट? तो अभी देखते हैं कैसे होगा काम. लेट्स सी कैसे होगा ये काम. तो अगर मैंने यहाँ पे क्वीन रख दी और मैंने अगली रो पे कॉल किया, तो अगली रो में दिस इज़ नॉट अ वैलिड पोजीशन बिकॉज यहाँ पे क्वीन पड़ी हुई है, इसके ऊपर एक क्वीन पड़ी है, राइट? सो सिमिलरली दिस इज ऑल्सो नॉट अ वैलिड पोजीशन, ये भी वैलिड पोजीशन नहीं है. दिस इज अ वैलिड पोजीशन, यहाँ पे हम क्वीन को रख सकते हैं, इट इज़ अ सेफ पोजीशन. यहाँ पे मैंने क्वीन को रख दिया. तो यहाँ पे मैंने क्वीन को प्लेस कर दिया. अगेन अगली रो पे जाऊँगा, आगे चेक करने की ज़रूरत नहीं है बिकॉज एक रो में एक ही क्वीन आ सकती है. सो यहाँ पे मैं नहीं रख सकता, यहाँ पे अगेन नहीं रख सकता, यहाँ भी नहीं रख सकता, यहाँ भी नहीं रख सकता, राइट? तो ये वाली रो में देर इज़ नो ऑप्शन टू प्लेस द क्वीन. तो इट मीन्स जो पिछली क्वीन है उसकी पोजीशन गलत है, राइट? सो इट मीन्स द पोजीशन ऑफ द प्रीवियस क्वीन इज रॉन्ग. so this grid will return, this row will return false. so this will return false to the previous row कि मेरी, मैं अपनी रो में कहीं पे भी क्वीन नहीं रख पा रहा हूँ. तो रिकर्जन बोलेगा द प्रीवियस कॉन्फ़िगरेशन इज रॉन्ग, so this current row will return false to the previous row. it means इसको यहाँ से हटाएंगे एंड इसके पास अब एक लास्ट ऑप्शन बचता है विच इज़ दिस ऑप्शन. तो यहाँ पे क्वीन को रख देता हूँ, रख देता हूँ, रख दी, एंड आई कॉल. अब अगेन मैंने अगली रो पे कॉल किया, तो अगली रो मेरे को बताएगी कि रख पा रहे हैं या फिर नहीं रख पा रहे. तो यहाँ पे मैं क्वीन रख ही नहीं सकता, यहाँ पे क्वीन रख सकता हूँ, राइट? यहाँ पे कोई भी क्वीन को डायगनली या रो और कॉलम के लॉन्ग कट नहीं करेगी, और मैं अगली रो पे कॉल कर देता हूँ, ठीक है? इसमें यहाँ पे मैं रख नहीं सकता, यहाँ पे भी नहीं रख सकता, यहाँ पे भी नहीं रख सकता, यहाँ भी नहीं रख सकता. तो अगेन दिस रो विल रिटर्न फॉल्स. सो ये बोलेगी गलत है, पिछली क्वीन को, पिछली रो को पता चलेगा मेरी पोजीशन सही से फिल नहीं हुई है, तो इस पोजीशन को हम छोड़ देंगे. यहाँ पे क्वीन रख सकते हैं, नहीं रख सकते, यहाँ पे क्वीन रख सकते हैं, नहीं रख सकते. तो ये वाली रो अब पिछली रो को बोलेगी पिछली पोजीशन की क्वीन, पिछली रो की पोजीशन गलत है, दिस विल रिटर्न फॉल्स और ये सारे हट जाएंगे। जब हम पीछे चले गए, करंट रो का कोई काम नहीं है, सो अब करंट रो ही है, तो ये बोलेगी ये पोजीशन गलत है, आगे कहीं पे ट्राई करो। आगे मतलब कोई भी वैलिड पोजीशन नहीं है। तो अब करंट रो प्रीवियस रो को बोलेगी ये पोजीशन गलत है, यहाँ पे गए तो इसकी पोजीशन यहाँ से हटा के मैंने चेंज कर दी यहाँ पे। एंड अगेन मैं नेक्स्ट रो पे कॉल किया, अगेन मैंने नेक्स्ट रो पे कॉल किया, यहाँ पे नहीं रख सकता, यहाँ पे नहीं रख सकता, यहाँ पे नहीं रख सकता, यहाँ रख सकता, रख दी। नेक्स्ट रो पे कॉल किया, नेक्स्ट रो से पूछा क्या तुम क्वीन रख पा रहे हो या नहीं रख पा रहे, तो नेक्स्ट रो बोलेगा यहाँ पे रख सकते हैं, हाँ रख सकते हैं, रख दी। और अपनी नेक्स्ट रो पे कॉल करो, यहाँ नहीं रख सकते, यहाँ पे नहीं रख सकते, यहाँ पे रख सकते हैं, सो यहाँ पे क्वीन रख देंगे और नेक्स्ट रो पे कॉल करेंगे, नेक्स्ट रो ये वाली होगी। जैसे ही ये कॉन्फ़िगरेशन अचीव हुई, इट मीन्स अगर मैं बोलूँ मेरे पास n was 4, n was 4 and I want to just तो बेस केस क्या होगा मेरा, यहाँ पे I0, I1, I2, I3 और I4। बेसिकली I becomes equal to, अगर n हो जाता है तो I just need to print the current configuration। इट मीन्स हम n रोज में क्वीन को प्लेस कर चुके हैं, तो उसको प्रिंट कर देना बेस केस। यू कैन जस्ट प्रिंट द configuration, right? So this is how the nqueen algorithm works, and we will now see in the code, right? So we will now see in the, so let's write a code for the nqueen problem, right? तो देखते हैं। तो यहाँ पे आई हैव वन वेरिएबल n, जिससे जो कि मैं इनपुट लूँगा यूज़र से, और फाइनली रिटर्न 0। एंड यहाँ पे एक फंक्शन होगा void या bool सॉल्व nqueen प्रॉब्लम। nqueen प्रॉब्लम जो है दैट विल टेक वन बोर्ड, राइट? अभी के लिए मैं बोर्ड ले लेता हूँ, चेस बोर्ड ऑफ लेट्स से मैक्सिमम साइजेस 10x10, राइट? एंड इट इज़ इनिशियलाइज्ड विद 0। तो जहाँ जहाँ पे क्वीन होगी वहाँ पे मैं 1 प्लेस कर दूँगा। तो ठीक है, सॉल्व एन क्वीन एक फंक्शन है विच टेक्स योर बोर्ड एरे एंड द करंट रो विच इज़ आई एंड एन, कितनी रोज हैं टोटल, ठीक है? सो आई कैन कॉल दिस फंक्शन सॉल्व एन क्वीन and I just pass the board, and the starting row is the 0th row and number of rows is n। I can take input n input ले सकता हूँ। तो यहाँ पे एक बेस केस ले लेते हैं। तो बेस केस मीन्स I have completed all the n rows, right? So if I becomes equal to n, so it means you have successfully placed queens in n rows, and these rows are numbered from 0 till n minus 1. So you just need to print the code print कर लेंगे and you can return true। मेरी n queen problem solve हो चुकी है. दिस वी विल डू लेटर. कोड को हम बाद में प्रिंट करेंगे. ठीक है. सो अब देखो यहाँ पे जब मैं क्वीन प्लेस करने जा रहा हूँ, तो दिस इज माई रिकर्सिव केस. Recursive case, right? So how do we think recursive case? So as I have already told in the class कि जब भी हम recursion की problem को approach कर रहे हैं, तो the assumption which we have to take is कि आगे की rows fill हो जाएंगी, right? So while solving this problem, I can assume जो मेरा subgrid है या sub problem है वो solve हो जाएगी, right? तो recursive case के लिए I can assume कि ये जो part है this will get solved automatically by recursion, right? So मेरे को ultimately करना क्या है? I have to try to place a queen in the current row, right? So I have to try to place the queen in the current row and call on the remaining part, which will be solved by recursion. ठीक है. So I can iterate over all the columns of the current row for int j equal to 0, j less than n, j plus plus. I can just iterate over all the columns, and I cannot place the queen blindly. I have to check if I comma jth position is safe to place the queen or not. ठीक है. So हम अगर किसी एक सेल में क्वीन को प्लेस कर रहे हैं, लेट से मैं यहाँ पे क्वीन प्लेस कर रहा हूँ. यहाँ पे अगर मैं क्वीन प्लेस कर रहा हूँ तो मेरे को चेक करना है इसके डायगोनल के लॉन्ग कोई क्वीन तो नहीं है, इसके अपर डायगोनल के लॉन्ग कोई क्वीन तो नहीं है, और इसके कॉलम में कोई क्वीन तो नहीं है, राइट. सो अभी इसके लिए हटा देता हूँ. तो आई हैव टू चेक कि देयर इज नो सच क्वीन along its right diagonal, left diagonal and the column, right. नीचे चेक करने की ज़रूरत नहीं है बिकॉज मैं रो बाय रो भर रहा हूँ. रो बाय रो भर रहा हूँ तो नीचे वाले कॉलम में चेक करने की ज़रूरत नहीं है, नीचे वाले डायगोनल्स में भी चेक करने की ज़रूरत नहीं है, राइट. तो ये जो सेल्स होंगी ये क्या होंगे, राइट. सो आई कैन से if this coordinate is I comma j, so these coordinates will be nothing but I minus 1 and j plus 1, right. so अगर डायगोनल पे जाना है तो माइनस करना होगा i में और j पे प्लस करना होगा. सिमिलरली अगर लेफ्ट डायगोनल पे जाना है, सो दिस इज नथिंग बट I minus 1 j minus 1. दिस इज नथिंग बट I minus 2 j minus 2. तो मेरे को यहाँ से दो डायरेक्शंस में मूव करना है. एक डायरेक्शन ये जिसमें रोज कम होंगे और कॉलम्स प्लस होंगे, एक डायरेक्शन रे जिसमें रोज भी कम होंगे और कॉलम्स भी कम होंगे, राइट. सो वी कैन चेक, वी कैन मेक अ वन हेल्पर फंक्शन bool is safe. Is it safe to place the queen in the board at cell I comma j? So this function will return true or false if it is safe or not. So let's say, so you can check for the column. तो कॉलम में चेक करने का मतलब क्या है? फॉर इंट रो इक्वल्स टू 0, रो लेस देन इक्वल्स टू रो लेस देन आई, रो प्लस प्लस. So column is constant if board of row comma j, column is j equals 1. It means there is a queen at that place, so you cannot place the queen, so you return false. Then you can also check for the left diagonal, right. You can check for left diagonal, and you know the starting point is I and the y coordinate is j. So for the left diagonal I can do while x is greater than equal to 0 and y is also greater than equal to 0, because we have to remain inside the board. So if board of x comma y equals to 1, so I can say just return false. There is a queen in the left diagonal and पिछले सेल पे जाना है तो x minus minus j minus minus. Again you have to check for the right diagonal also. So top right diagonal के लिए there will be similar logic, so I'm just copying it. तो राइट डायगोनल में x और y यहाँ से स्टार्ट होंगे, बिल्कुल होंगे, बट दोबारा डिक्लेयर करने की ज़रूरत नहीं है. ठीक है, x will be greater than equal to 0 while y should be less than equal to n, less than n basically, not equal to n, and j में इंक्रीमेंट होगा और नंबर ऑफ रोज में डिक्रीमेंट होगा. तो अगर कहीं से भी फॉल्स रिटर्न नहीं हो रहा, इट मीन्स द पोजीशन इज नाउ सेफ बिकॉज वी हैव चेक्ड फॉर कॉलम्स, कॉलम में भी चेक कर लिया एंड डायगोनल्स में भी हमने चेक कर लिया. सो आई कैन से जस्ट रिटर्न ट्रू. So this function will return true if it is safe to place that queen at a particular position. So now what I have to do is I have to check if is it safe to place the queen in the board at I comma jth position and the board is having n rows and columns, right? So if it is safe, so I can place the queen, right? So I can say place the queen, right? So placing the queen means you have to do board of ij equal to 1. हमने यहाँ पे queen को place कर दिया है, right? The next part is, what is the next part? Let's see. So what is the next part? मैंने क्या किया, यहाँ पे एक क्वीन को रखा और क्योंकि सेफ था तो मैंने आगे अगले पार्ट पे कॉल कर दिया, राइट? तो द नेक्स्ट पार्ट कैन रिटर्न ट्रू अगर कॉन्फ़िगरेशन जनरेट हो रही है. द नेक्स्ट पार्ट कैन रिटर्न फॉल्स इफ दिस इज नॉट अ वैलिड पोजीशन. अगर ये वैलिड पोजीशन नहीं है तो नेक्स्ट पार्ट फॉल्स भी रिटर्न कर सकता है, राइट? सो फर्स्ट स्टेप इज टू प्लेस द क्वीन इफ इट इज सेफ टू डू सो. सो हमने यहाँ पे रख दिया है एंड वी विल कॉल ऑन द नेक्स्ट पार्ट टू आस्क क्या क्वींस को हम रख पा रहे हैं, क्या हम रिमेनिंग पार्ट में क्वींस को रख पा रहे हैं. तो आई कैन से बोल नेक्स्ट क्वीन रख पा रहे हैं. सो ये कौन बताएगा? दिस विल बी डन बाय द सेम रिकर्सिव फंक्शन सॉल्व n queen. So it takes the board array, it takes this, it also, sorry, I have to just pass the board array, I have to pass the next row के लिए I plus 1 होगा and n will be now n. So अगर नेक्स्ट क्वीन हम रख पा रहे हैं तो बहुत सही. अगर नेक्स्ट क्वीन हम रख पा रहे हैं तो आई कैन से जस्ट रिटर्न, तुम भी ट्रू रिटर्न कर दो, यू डू नॉट नीड टू मूव टू द नेक्स्ट पोजिशन, राइट? बट व्हाट इफ अगर हम नेक्स्ट क्वीन नहीं रख पा रहे, तो अगर हम नेक्स्ट क्वीन हम नहीं रख पा रहे, कोई बात नहीं, फॉर लूप चलेगा, अगली पोजीशन के लिए ट्राई करेगा, है ना? तो दिस स्टेटमेंट इज इनसाइड द लूप. अगर नेक्स्ट क्वीन नहीं रख पा रहे तो फॉर लूप चलेगा और नेक्स्ट पोजीशन के लिए ट्राई करेगा, राइट? बट इसका मतलब क्या है यहाँ पे? प्लेस द क्वीन एज्यूमिंग ij इज द राइट पोजीशन. बट अगर यहाँ पे आता है, यहाँ पे अगर फ्लो आ रहा है, इट मीन्स ij is not the right position. ij is not the right position. It means our assumption is wrong. जो हमने assumption लिया अभी, जैसे यहाँ पे हो रहा था, क्वीन यहाँ पे रखना सेफ था, यहाँ पे रख पा रहे हैं, बट नेक्स्ट पार्ट ने इसको क्या रिटर्न किया? फॉल्स. मेरे को क्वीन यहाँ से हटानी भी तो है, आई हैव टू ऑल्सो रिमूव द क्वीन. तो यहाँ पे मेरे को क्या करना पड़ेगा? ज़ीरो करना पड़ेगा वापस से, और अगली क्वीन मेरे को यहाँ पे रखनी पड़ेगी. यहाँ भी नहीं रख पा रहे तो यहाँ भी ज़ीरो करना पड़ेगा और अगली क्वीन मेरे को यहाँ पे रखनी पड़ेगी, राइट? So what I have to do is, so our assumption is wrong, so what I do is आई डू बोर्ड ऑफ आई जे इक्वल्स टू 0, इट मीन्स हमने बैक ट्रैक कर लिया है, पिछली पोजीशन जो हमने गलत फिल की थी उसको वापस से हमने करेक्ट कर दिया है, एंड हेयर आई विल रिटर्न फॉल्स। इसका मतलब क्या है? याद है वो वाला केस जब एक रो में हम कहीं पे भी रख नहीं पा रहे थे, यहाँ पे फॉर लूप खत्म हो रहा है, यहाँ पे इफ स्टेटमेंट खत्म हो रही है, तो इसका मतलब क्या है? यू हैव ट्राइड फॉर ऑल पोजीशंस इन द करंट रो बट कुड नॉट प्लेस अ क्वीन, तुम क्वीन को नहीं रख पाए, so it means return false, the current row will return false to the previous row कि हम क्वीन को कहीं पे भी रख नहीं पा रहे, राइट? सो दिस completes your n queen code. The only thing left is the base case, right? So we have to just print the board. So you can, for int I equals to 0, I less than n, I plus plus, for int j equals to 0, j less than n, j plus plus. So if you could place the queen, if board of ij equals to 1, so you have to see out queen पड़ी है, otherwise you can see out, let's say dot, एक डॉट रख देते हैं और सम स्पेस रख देते हैं, या फिर ऐसा कुछ रख देते हैं, क्वीन नहीं पड़ी, राइट? एंड फॉर आफ्टर एवरी रो आई कैन जस्ट सी आउट एंडल, हर एक रो के बाद एक एंडल हमने डाल दिया है। सो लेट्स टेक द इनपुट लेते हैं और प्रोग्राम को रन करते हैं। लेट्स से द नंबर ऑफ रोज इज 4, मेरे पास 4 रोज हैं, सो आई कैन रन द कोड। ओ देयर इज स्मॉल मिस्टेक, कुछ छोटी सी गलती हुई है यहाँ पे, सॉरी, दिस इज नॉट y प्लस प्लस j प्लस प्लस, दिस शुड बी y प्लस प्लस, x और y में चेंज कर रहा हूँ ना, j नहीं चेंज होगा, यहाँ पे भी इट शुड बी y माइनस माइनस, स्मॉल मिस्टेक। So let's run the code again. So you can see this is the configuration that we had generated. हमने अभी यही वाली configuration generate की थी. So there can be multiple answers to this question. So this is the configuration जो हमने अभी generate की थी, right? Exactly same आ रहा है because हमने उसी logic को अपने code में लिखा है। तो हो क्या रहा है, जब हम फर्स्ट क्वीन को यहाँ पे प्लेस करते हैं और आगे कॉल करते हैं, राइट? सो आगे कॉल करने से आई गेट आइदर ट्रू और फॉल्स, तो इसको मिला फॉल्स, तो ये क्वीन कहाँ पे चली जाती है? यहाँ पे। अगेन ये आगे कॉल करती है तो इसको मिलता है ट्रू, तो इट मीन्स इसकी पोजीशन ये सही है। अब इस रो में हम बाकी क्वींस को ऑलरेडी रख चुके हैं। दिस सॉल्व्स योर एन क्वीन प्रॉब्लम। तो अभी देखो इसके ना मल्टीपल सॉल्यूशंस हो सकते हैं, देयर कैन बी मल्टीपल सॉल्यूशंस टू दिस प्रॉब्लम। सपोज यू वांट टू प्रिंट ऑल सच कॉन्फ़िगरेशंस, आप सारी वो कॉन्फ़िगरेशंस प्रिंट करना चाहते हो। लोने इज सेइंग सबसे पहले लास्ट क्वीन रखी जाती है, यू कैन से, बट हम नहीं, हम रो बाय रो क्वीन रख रहे हैं और अगली रो पे कॉल कर रहे हैं। अगली रो से अगर गलत आता है तो करंट रो की हम पोजीशन चेंज करते हैं। तो हम ये देख के आते हैं कि लास्ट रो तक हम सक्सेसफुली भर पा रहे हैं या नहीं भर पा रहे। तो क्वीन हम फर्स्ट रो से ही रख रहे हैं, बट हम लास्ट रो तक चेक करते हैं कि क्वीन लास्ट रो तक हम रख पा रहे हैं या नहीं रख पा रहे। ठीक है? सो एक एक चीज़ मैं और बता रहा हूँ। सो इफ़ यू वांट टू प्रिंट ऑल द सॉल्यूशंस, राइट? सो अभी हम क्या हुआ, अभी हमने यहाँ पे क्या किया, जो हमारा सॉल्यूशन निकला वो ये था, राइट? यहाँ पे मैंने क्वीन रखी, यहाँ पे मैंने क्वीन रखी, और एक मैंने यहाँ रखी, और एक मैंने कहाँ रखी थी, यहाँ रखी थी, और एक मैंने
तो बेसिकली देखो कोड कैसे काम कर रहा है, जैसे हमने ट्राई रन किया था वैसे ही काम कर रहा है, राइट। तो उसने फर्स्ट रो में यहाँ पे रख के देखा, आगे कॉल किया, उसको फॉल्स मिला, उसने यहाँ रखा। नेक्स्ट रो में वो यहाँ नहीं रख सकता, यहाँ नहीं रख सकता, यहाँ नहीं रख सकता, यहाँ रख दी। नेक्स्ट रो में वो यहाँ पे रख सकता है, रख दी। नेक्स्ट रो में वो यहाँ रख सकता है, नहीं, यहाँ रख सकता है, नहीं, यहाँ रख सकता है, यस। और अगली रो पे उसने कॉल कर दिया। पहले वाले केस वही थे जो मैंने बैक ट्रैकिंग में शुरू में एक्सप्लेन किया। दिस इज़ अ वैलिड कॉन्फ़िगरेशन, बट ऐसा भी हो सकता है इसकी मिरर इमेज ले लूँ तो आई विल गेट वन मोर कॉन्फ़िगरेशन, एक और कॉन्फ़िगरेशन निकल के आ जाएगी। आई एम जस्ट टेकिंग द मिरर इमेज, राइट। सो मिरर इमेज से क्या होगा, तो दिस कॉन्फ़िगरेशन विल बिकम समथिंग लाइक दिस। क्यू यहाँ पे आ जाएगा, ये क्यू यहाँ पे आ जाएगा, एंड ये क्यू मेरा यहाँ चला जाएगा, एंड दिस क्यू विल कम हेयर। सो दिस इज़ अनदर कॉन्फ़िगरेशन, एक और कॉन्फ़िगरेशन बन गई। तो सपोज आई वांट टू जनरेट ऑल कॉन्फ़िगरेशंस ऑफ द एन क्वीन, सो तब क्या करना होगा मेरे को, अगर मेरे को सारी जनरेट करनी है, तो सिंपली हो क्या रहा है, अगर मेरे को क्वीन को यहाँ पे रखने से सक्सेसफुल आंसर मिल जाता है तो मैं रिटर्न कर देता हूँ ट्रू। तो इंस्टेड ऑफ रिटर्निंग ट्रू, अगर मेरे को आगे से ट्रू आ रहा है या फॉल्स आ रहा है, आई कैन स्टिल ट्राई द नेक्स्ट कॉन्फ़िगरेशन। मैं क्वीन को यहाँ पे रख के बाकी कॉन्फ़िगरेशन जनरेट कर लूँ, इट इज़ पॉसिबल। आगे से ट्रू आ रहा है या फॉल्स आ रहा है उससे फ़र्क नहीं पड़ रहा, मैं क्वीन को अगली बार यहाँ पे रख के बाकी कॉन्फ़िगरेशंस जनरेट कर लूँ, राइट। सो मिरर इमेज, हर बार मिरर इमेज नहीं होगा, इट इज़ पॉसिबल एक डिफरेंट कॉन्फ़िगरेशन हो जो मिरर इमेज ना हो या रोटेट ना हो। So I'm just going to comment out one line, so you will see, you can just generate all valid configurations, right? In this code, अच्छा, there is a small hack, अगर मैं यहाँ पे return false लिख दूँ, अगर मैं यहाँ return false लिख दूँ तो can anyone tell me क्या होगा, अगर बेस केस में मैं false लिख दूँ तो can anyone tell इससे क्या होगा। I have just changed the base case, so I'm waiting for the answers. बिल्कुल ठीक है, so everyone is giving me the yes, so it will continue to search for the next valid configuration, but क्योंकि हमने बेस केस में वो कॉन्फ़िगरेशन प्रिंट करवा दी है, तो वी विल गेट ऑल द कॉन्फ़िगरेशंस, हमें सारी कॉन्फ़िगरेशंस मिल जाएंगी। सो यहाँ पे मैं कर देता हूँ एंडल, तो यू विल सी आई विल गेट ऑल पॉसिबल कॉन्फ़िगरेशंस। तो यू कैन सी एक कॉन्फ़िगरेशन मिल रही है, दूसरी भी हमें मिल रही है, तो दिस इज़ द second configuration, which is the mirror image of the first configuration. सपोज मैं इनपुट में कर देता हूँ 9, राइट। सो इनपुट में कर देता हूँ 9x9 का बोर्ड है, तो वो एंड इसको रन करता हूँ, तो यू कैन सी देर आर लॉट ऑफ कॉन्फ़िगरेशंस, बहुत सारी कॉन्फ़िगरेशंस प्रिंट हो रही हैं एन क्वीन के लिए, ठीक है। तो इन दिस वे यू कैन जनरेट ऑल कॉन्फ़िगरेशंस, यू कैन ऑल्सो काउंट द कॉन्फ़िगरेशंस। ऐसा क्यों हो रहा है, दिस इज़ अ हैक। हमने क्या किया, हमने बस प्रीवियस रो को बोला कि आगे का बोर्ड सॉल्व नहीं हो रहा, ऑल दो आगे का बोर्ड सॉल्व हो चुका है, बट हमने हमेशा फॉल्स रिटर्न किया, हमने हमेशा फॉल्स रिटर्न किया। तो इसको लगा कि ये जो पोजीशन थी विच वॉज करेक्ट, ये सही नहीं है, तो इसने यहाँ पे क्वीन रख दी, अगली पे रख दी। इसको लगा ये भी ठीक नहीं है, तो इसने नेक्स्ट पोजीशन पे रख दी, राइट। तो ऐसे केसेस जिनमें हमारा बेस केस हिट हो रहा है, आई इक्वल टू हम एन पे पहुंच रहे हैं, तो वो वाले केसेस में जब पहुंचे तो हमारे पास बोर्ड की एक वैलिड कॉन्फ़िगरेशन थी जिससे मेरा काम हो गया। तो दिस इज़ द एन क्वीन प्रॉब्लम।
So you returning false will help me to search for the next valid configuration, right? तो return false से क्या होगा, this statement will always return false, तो यहाँ पे false ही आएगा, ये true कभी execute होगा नहीं, this will not get executed. All right, so I hope this question is clear to everyone. So let me know, you can just go through the code also.
हाय गाइस, तो अभी हम रिकर्जन एंड बैक ट्रैकिंग को यूज़ करके वी आर गोइंग टू बिल्ड अ सुडोको सॉल्वर. सो वेरी इंटरेस्टिंग प्रॉब्लम. And in this problem you are given a sudoku puzzle. You might have played sudoku, and you also know what are the rules of sudoku. So in sudoku you have to fill this grid such that every row has numbers from 1 to n, right? So in this case the n is 9, right? The grid size is 9 cross 9, and it will be a square grid which is divided into 9 subgrids, right? So n cross n puzzle will have n subgrids, and each subgrid will be of the size root n cross root n, right? So यहाँ पे n 9 है, तो we have a 3 cross 3 subgrids, and हमें करना क्या है, हमें जो numbers, जो positions empty हैं उनको fill करना है with numbers, and वो numbers होंगे from 1 to 9. 1 से लेके 9 तक हमारे पास numbers होंगे, उनको इसमें fill करना है such that every row has numbers from 1 to 9, every column has numbers from 1 to 9, and every subgrid has numbers from 1 to 9, right? हर सबग्रिड के अंदर 1 से लेके 9 तक नंबर्स होने चाहिए, राइट? तो यहाँ पे क्या हम 1 रख सकते हैं? माइट भी रख सकते हैं, क्योंकि रो में नहीं आ रहा, कॉलम में नहीं आ रहा और सबग्रिड में भी नहीं आ रहा. बट ऐसा ज़रूरी नहीं है कि 1 को रख के हम सोल्यूशन यहाँ पे बना पाएँ, राइट? तो हमें सोचना पड़ेगा कि इसको कैसे करें, राइट? तो हमारे दिमाग में आइडिया क्या आ रहा है कि हम ब्रूट फोर्स अप्रोच लगाएंगे. हम हर नंबर को रख के देखेंगे, जिससे सोल्यूशन बन जाएगा वो हमारा फाइनल आंसर होगा, राइट? तो हम एक काम करते हैं, तो फर्स्ट नॉन एम्प्टी सेल को ढूंढते हैं विच इज़ दिस, एंड यहाँ पे हम नंबर रख देते हैं 1, राइट? और नेक्स्ट सेल पे कॉल कर देते हैं. यहाँ पे हम 2 नहीं रख सकते बिकॉज रो में आ रहा है, 3 नहीं रख सकते बिकॉज कॉलम में आ रहा है, 4 नहीं रख सकते कॉलम में आ रहा है, 5 माइट भी हो सकता है 5 रखने से सोल्यूशन बन जाए या ना बने, हमें नहीं पता, राइट? तो हम नेक्स्ट सेल पे कॉल करेंगे, राइट? तो जैसे हम नेक्स्ट सेल पे कॉल करेंगे तो हमारा प्रॉब्लम रिड्यूस हो जाएगा इन अ सब प्रॉब्लम. तो सबग्रिड कुछ ऐसा दिखेगा, दिस बिकम्स द सबग्रिड, राइट? तो ये सबग्रिड पे हमने कॉल किया, एंड ये सबग्रिड हमें बताएगा कि सुडोको सॉल्व हो रहा है तो ट्रू देगा, सुडोको अगर सॉल्व नहीं हो रहा तो ये फॉल्स देगा. तो सपोज करो अगर फॉल्स आया तो यहाँ पे हमें क्या करना पड़ेगा, 5 की जगह कुछ और रखना पड़ेगा. तो मे बी हम 5 को 6 रखेंगे, बट 6 तो रख ही नहीं सकते, 6 सबग्रिड में आ रहा है. माइट भी हम 7 रख के ट्राई करें, तो ऐसा हो सकता है 7 रखने के बाद हमने फिर से यहाँ पे कॉल किया, ये पूरा ग्रिड सॉल्व हुआ, उसके बाद हमारे पास आया ट्रू या फिर फॉल्स. ट्रू आ गया तो हमने बोला कि हाँ सुडोको सॉल्व हो गया, ये अपने पिछले सेल को ट्रू रिटर्न कर देगा और ये मेन को ट्रू रिटर्न कर देगा, और जो नंबर्स ऑलरेडी फिल्ड हैं उनको हम चेंज नहीं कर सकते, राइट? तो यहाँ पे हमें अगेन रिकर्जन और बैक ट्रैकिंग का यूज़ करना है. नेक्स्ट नॉन एम्प्टी सेल पे कॉल करना है, एंड सॉरी नेक्स्ट एम्प्टी सेल पे कॉल करना है, और अगर नॉन एम्प्टी सेल आए तो उसको स्किप करना है, राइट? एंड सो आइडिया क्या हो गया कि हम एक करंट सेल पे काम करेंगे एंड आगे के लिए रिकर्जन काम करेगा. तो हमने करंट सेल पे कुछ नंबर रख के देखा, सब प्रॉब्लम पे कॉल किया, सब प्रॉब्लम से ट्रू आया तो हमने भी ट्रू रिटर्न कर दिया, सब प्रॉब्लम से अगर फॉल्स आएगा तो हम अपने करंट नंबर को चेंज करेंगे, राइट? तो इसको लिखने का ट्राई करते हैं कि इसको कैसे हम इम्प्लीमेंट कर सकते हैं. सो लेट अस सी इन द कोड, राइट? सो यहाँ पे मेरे पास एक सुडोको पजल बना हुआ है, राइट? सो दिस इज़ द पजल जिसको मैं सॉल्व करना चाह रहा हूँ. So let us write one function bool solve sudoku, right? And this will get the matrix. This will also get the integer I. This will also get the integer j, which is basically a position of the cell. अभी हम कौन सी रो और कौन से कॉलम में काम कर रहे हैं वो डिनोट कर रहे हैं. I, j सेल की बात हो रही है. तो बेस केस क्या होगा, अभी बेस केस देखते हैं. लेट अस फर्स्ट फिगर आउट द बेस केस. बेस केस ये होगा कि हमने सारी रोज में काम कर लिया और हम लास्ट रो में को भी क्रॉस कर चुके हैं. एंड वी विल ऑल्सो टॉक अबाउट रिकर्सिव केस, राइट. तो देखते हैं बेस केस क्या होगा. देखो बेस केस ये होगा कि हम अब कॉलिंग कैसे कर रहे हैं, हम सेल बाय सेल कॉल कर रहे हैं, एक सेल से अगले सेल पे कॉल कर रहे हैं, राइट. फिर यहाँ से हम अगली रो पे आ जा रहे हैं, फिर ऐसे ऐसे चलते जा रहे हैं. एंड फाइनली जब हम लास्ट रो को क्रॉस करके इस रो पे आ जाएंगे, राइट. सो यहाँ पे आई ज़ीरो से लेके n-1 तक होगा. एंड जैसे ही आई इक्वल टू n होगा, मतलब लास्ट रो को भी हमने क्रॉस कर लिया है. इट मीन्स n नंबर ऑफ रोज को हम कम्प्लीटली फिल कर चुके हैं. तो हमें क्या करना है, उस पॉइंट पे सॉल्यूशन प्रिंट कर देना, राइट. तो इफ़ i becomes equal to n, तो we will print the solution, right. so you will print the matrix, इसको हम बाद में कर लेंगे. एंड वी विल रिटर्न ट्रू कि हमें सोल्यूशन मिल गया है, ठीक है. एंड रिकर्सिव केस में जाने से पहले वी विल फिगर आउट कि और कुछ केसेस भी होंगे क्या. सो व्हाट इफ अगर आप एक रो के एंड पे आ गए, राइट. सो केस फॉर द रो एंड, अगर एक रो ख़त्म हो रही है तो आपको नेक्स्ट रो में शिफ्ट करना है. तो इफ़ j इक्वल टू n, राइट. अगर ऐसा हो गया, मतलब कॉलम्स ख़त्म हो गए हैं, हम लास्ट कॉलम को क्रॉस कर चुके हैं, तो यू विल रिटर्न सॉल्व सुडोकू. नेक्स्ट रो पे जाना है, मैट्रिक्स i+1, j विल बी नाउ 0 एंड n विल रिमेन सेम, राइट. सो n डिनोट कर रहे ग्रिड का साइज. तो देखते हैं. तो अगर मैंने इस सेल से यहाँ कॉल किया, यहाँ कॉल किया, यहाँ कॉल किया, जैसे मैं यहाँ पे आया, मेरे को कहाँ जाना है, यहाँ जाना है, राइट. मैंने वही किया, रिटर्न सॉल्व सुडोकू. रो आई थी, अब रो हो जाएगी i+1 और j क्या हो जाएगा 0. तो इस सेल पे हम आ जाएंगे, राइट. ऑल राइट. अब ऐसा भी हो सकता है कि कुछ सेल्स ऑलरेडी फिल्ड हो, राइट. सो स्किप द प्री फिल्ड सेल्स. अब किसी हम सेल पे अगर काम कर रहे हो और वो ऑलरेडी प्री फिल्ड है, मतलब दैट इज गिवन इन द क्वेश्चन. सो इफ मैट्रिक्स ऑफ ij इज नॉट इक्वल टू 0, उसमें ऑलरेडी नंबर पड़ा है, तो हमें उसमें उसको चेंज नहीं करना है, तो उसको स्किप करना है. तो स्किप करने का मतलब क्या है, गो टू द नेक्स्ट सेल. नेक्स्ट सेल होगा सेम रो में, नेक्स्ट कॉलम पे चले जाओ, राइट. दिस इज़ अ इम्पॉर्टेंट केस. एंड नाउ वी हैव द मेन रिकर्सिव केस कि हम ऐसा सेल है जो हमें फिल करना है, राइट. तो फिल द करंट सेल विद पॉसिबल ऑप्शंस, राइट. हर एक नंबर नहीं हम रख सकते, सिर्फ कुछ ऑप्शंस होंगी जिनको हम रख सकते हैं. तो ऐसे नंबर्स जो उस रो में नहीं आ रहे हैं, जो उस कॉलम में नहीं आ रहे हैं और जो सबग्रिड में नहीं आ रहे हैं, राइट. तो पॉसिबल ऑप्शंस हमारे पास नंबर जो है वो 1 से लेके 9 तक होंगे, या 1 से लेके n तक होंगे, एंड नंबर प्लस प्लस, राइट. 1 से लेके n तक या 1 से लेके 9 तक के नंबर्स को रख सकते हैं, राइट. बट कैसे चेक करेंगे कि कौन सा नंबर फिजिबल है. तो लेट अस राइट वन फंक्शन, कैन प्लेस, जो मैट्रिक्स ले, कोऑर्डिनेट ले, ग्रिड का साइज ले और नंबर भी ले. तो ये फंक्शन मेरे को बताएगा कि हम उस सेल पे वो नंबर रख सकते हैं या नहीं रख सकते. तो इसको लिखना पड़ेगा हमें पहले. तो बूल कैन प्लेस, दिस फंक्शन एक्सेप्ट्स द मैट्रिक्स, इट एक्सेप्ट्स द इंडेक्स, इट ऑल्सो एक्सेप्ट्स n, एंड दिस ऑल्सो एक्सेप्ट्स कि हम क्या नंबर यहाँ पे रख रहे हैं, राइट. तो एक बार देखते हैं कैसे क्या करना चाह रहे हैं हम, राइट. तो दिस इज अगेन एन इम्पॉर्टेंट स्टफ, राइट. यहीं पे देख लेते हैं. तो अगर आप यहाँ पे ध्यान से देखो, अगर सपोज करो मैं यहाँ पे एक नंबर रखना चाह रहा हूँ 6, राइट. तो वो इस कॉलम में नहीं आना चाहिए, राइट. तो कॉलम तो हम चेक कर सकते हैं, सिंपली आइटरेट कर सकते हैं इस कॉलम पे, और वो इस रो में भी नहीं आना चाहिए, रो पे भी हम आइटरेट कर सकते हैं. बट थोड़ा सा डिफ़िकल्ट क्या है कि इस सब ग्रिड पे कैसे आइटरेट करें. गिवन एक i, j इंडेक्स अगर हमें गिवन है, तो हम उस सब ग्रिड को कैसे फाइंड आउट करें, राइट. तो दिस इज़ द सब ग्रिड इसके लिए, राइट. इस सब ग्रिड पे हमें आइटरेट अगर करना है, तो हमें इस सब ग्रिड का स्टार्टिंग पॉइंट पता होना चाहिए, राइट. लेट्स से स्टार्टिंग पॉइंट को एस बोला है और SY बोला मैंने, ये कोऑर्डिनेट्स हैं सब ग्रिड के स्टार्टिंग पॉइंट के. तो अगर ये वाला सेल i, j है, राइट. तो एस एक्स हमारा कैसे निकलेगा, एस एक्स ऐसे निकलेगा आई डिवाइडेड बाई 3 इंटू 3, राइट, एंड एस वाई निकलेगा जे डिवाइडेड बाई 3 इंटू 3। तो देखते हैं ये फॉर्मूला क्यों आ रहा है, राइट, वेरीफाई भी इसको हम करेंगे अभी। सो लेट्स से नंबरिंग कर देते हैं रोज और कॉलम्स की। तो 0 1 2 3 4 5 6 7 8 एंड सिमिलरली है, यहाँ पे भी नंबरिंग कर देते हैं 0 1 2 3 4 5 6 7 8 9। तो ये जो सेल है, दिस सेल इज 4,5, दिस सेल इज 4,5। तो अगर हमें पता है कि सब ग्रिड्स 9 लेंथ के ग्रिड को 9 लेंथ के ग्रिड में 3 सब ग्रिड्स हैं, राइट, सो 9/3 वी गेट 3 सब ग्रिड्स। एंड अगर हमें एक सेल की आईडी पता है तो 4/3 करते हैं और 5/3 करते हैं, वी गेट 1,1, राइट। इसका मतलब क्या है, ये वाला जो सब ग्रिड है वो 1,1 है, राइट। तो अगर सब ग्रिड्स को मैं बोल दूँ, ये 0th है, ये फर्स्ट है, ये सेकेंड है, ये अगेन 0th है, फर्स्ट है, सेकेंड है, ये हमने रोज़ के लॉन्ग नंबरिंग किया, सेम नंबरिंग में इसके लॉन्ग भी कर सकता हूँ, राइट। तो इट वुड बी राइट, तो ये वाला जो सबग्रिड होगा वो 1,1 होगा। तो अगर मैं नंबरिंग इनकी ऐसे करूँ 0 0 0 1 0 2 1 0 1 1 1 2, राइट, मेरे को सबग्रिड की आईडी मिल रही है अलॉन्ग द रो एंड अलॉन्ग द कॉलम, राइट। तो ये जो सबग्रिड है ये 1,1 है। एंड अगर अब मेरे को ये भी पता है कि हर एक सबग्रिड के अंदर 3 सेल्स हैं, राइट। तो ये वाला सबग्रिड 1,1 है, तो इसका स्टार्टिंग पॉइंट कहाँ पे होगा, इंटू 3 करने पे, राइट, 1 इंटू 3 एंड 1 इंटू 3। तो ये सबग्रिड का स्टार्टिंग पॉइंट होगा 3,3, राइट। तो ये सेल हमारा 3,3 होगा। आप किसी और के लिए भी वेरीफाई कर सकते हो। सपोज व्हाट इज़ दिस पॉइंट इज़ 7,7, राइट, और हमें ये वाला पॉइंट चाहिए स्टार्टिंग पॉइंट। सो 7/3 इंटू 3 विच इज़ 6 एंड दिस इज ऑल्सो 6, राइट। सो 7/3 इंटू 3 इज 6। तो हमें ये वाला पॉइंट मिल गया 6,6, राइट। या फिर हम यहाँ पे खड़े हैं, लेट से हम यहाँ पे हैं, हमारा सेल है 5,1 है, राइट। तो इससे हमें ये वाला पॉइंट चाहिए सब ग्रिड का स्टार्टिंग पॉइंट, ताकि हम इतने रीजन पे आइटरेट कर पाएँ। तो इट इज़ 5/3 इंटू 3 विच इज़ 3 एंड यहाँ पे हमारा ये सेल है 1/3 इंटू 3 विच इज़ 0, राइट। तो हमारा सेल क्या आ जाएगा 3,0, राइट, एंड विच इज़ दिस सेल 3,0 ये। तो हमें मिल रहा है, तो दिस इज़ द राइट फॉर्मूला। एंड अगर मेरे को एक एन की टर्म्स में लिखना है तो वो क्या होगा, एस एक्स विल बी आई डिवाइडेड बाई √n इंटू √n एंड एस वाई विल बी जे डिवाइडेड बाई √n इंटू √n, राइट। तो ये फॉर्मूला हमारा होगा। तो इसी को यूज़ करके हम अभी अपने सुडोकू सॉल्वर को इम्प्लीमेंट कर लेते हैं, राइट। तो अब यहाँ पे कैन प्लेस फंक्शन के लिए हमें रो चेक करना है, कॉलम चेक करना है और सब ग्रिड चेक करना है, राइट। सो देख लेते हैं। फॉर इंट x इक्वल्स टू 0, x लेस देन n, x प्लस प्लस, इफ मैट्रिक्स ऑफ x कॉमा j इक्वल्स टू नंबर, रो में नंबर आ रहा है या फिर कॉलम में आ रहा है, मैट्रिक्स ऑफ i कॉमा x इक्वल्स टू नंबर, तो हम उस नंबर को वहाँ पे प्लेस नहीं कर सकते, रिटर्न फॉल्स, राइट। तो ये हमने चेक कर लिया फॉर द रो एंड कॉलम, दिस इज रो एंड द कॉलम चेक, राइट। नेक्स्ट चेक हमें कहाँ पे करना है, सब ग्रिड में नंबर रिपीट नहीं होना चाहिए, राइट। तो सब ग्रिड को निकालने के लिए हमें सबसे पहले √n पता होना चाहिए। √n विल बी नाउ स्क्वायर रूट ऑफ n एंड द हेडर फाइल वुड बी cmath, स्क्वायर रूट निकाल लो, राइट। एंड जो स्टार्टिंग पॉइंट होगा एस एक्स, दैट विल बी आई डिवाइडेड बाई n, आई डिवाइडेड बाई √n into root n, राइट. एंड जो स्टार्टिंग पॉइंट y होगा सबग्रिड का, दैट विल बी j डिवाइडेड बाय रूट n इंटू रूट n, राइट. एंड हम आइट्रेट करेंगे अब ग्रिड के ऊपर, राइट. तो फॉर लेट्स से x इक्वल्स टू एस एक्स, x लेस देन एस एक्स प्लस थ्री, राइट. प्लस थ्री ले लो या फिर प्लस रूट एन ले लो, बिकॉज जो सबग्रिड है वो 3x3 साइज का है, या फिर रूट एन क्रॉस रूट एन साइज का है, x प्लस प्लस. एंड फॉर int y इक्वल टू एस वाई, वाई लेस देन इक्वल टू एस वाई प्लस रूट एन y प्लस प्लस. एंड इफ मैट्रिक्स ऑफ x कॉमा y इक्वल्स टू नंबर, वी विल से रिटर्न फॉल्स. इसको हम यहाँ पे नहीं रख सकते. एंड फाइनली वी कैन से रिटर्न ट्रू, कि हम यहाँ पे रख सकते हैं. तो अब सुडोकू सॉल्वर में आ गए हम, right? तो यहाँ पे हम कैन प्लेस हमें बताएगा रख सकते हैं या नहीं रख सकते. तो हम एज्यूम अगेन अजम्पशन लेंगे कि उसको रखने से हमारा आंसर बन जाएगा. सो लेट अस एज्यूम कि यही सही नंबर है, राइट. तो रख देते हैं मैट्रिक्स ऑफ आई जे इक्वल टू नंबर, राइट. एंड हम आगे कॉल कर देंगे, राइट. एंड बूल कुड बी सॉल्व, मतलब क्या हम सुडोकू को सॉल्व कर पाए. मैट्रिक्स आई जे पे नंबर रखने से क्या हमारा सुडोकू सॉल्व हो रहा है. सो वी विल कॉल द सॉल्व सुडोकू फंक्शन फॉर द नेक्स्ट सेल. नेक्स्ट सेल हमें पता है आई कॉमा जे प्लस वन होगा एंड एन ही रहेगा, राइट. सो इफ कुड बी सॉल्व इज ट्रू, कि अगर सुडोकू सॉल्व हो गया तो हम यहीं से रिटर्न क्या कर दें, ट्रू. वी विल रिटर्न ट्रू. बट अगर सुडोकू सॉल्व नहीं हुआ है, राइट, तो हमें क्या करना पड़ेगा, हमें बैक ट्रैक करना पड़ेगा, राइट. तो बैक ट्रैक हम कहाँ पे करेंगे, फॉर लूप के बाद करेंगे, राइट. तो वी विल बैक ट्रैक हेयर, राइट. देखो क्या हो रहा है कि हमने यहाँ पे नंबर रखा 7, राइट. यहाँ पे नंबर जो लेट से 8 पड़ा था, यहाँ 7 रखा था, आगे कॉल किया. इस पूरे सुडोकू से या तो ट्रू आएगा तो हमने भी पीछे रिटर्न कर दिया ट्रू. बट अगर यहाँ पे फॉल्स आया, हमने 8 रखने का ट्राई किया बट 8 हम रख ही नहीं सकते, तो हम क्या रखेंगे, 9. 9 हमने रखा, अगर वो रो में कॉलम में और सबग्रिड में रिपीट नहीं हो रहा है तो 9 हमने रखा. एंड 9 रखने से भी फॉल्स आ रहा है, राइट. तो 9 रखने से भी फॉल्स आ रहा है. तो अब हमें क्या करना है, हमने सारे नंबर ट्राई कर लिए 1 से लेके 9 तक. तो हम बाहर आ जाएंगे फॉर लूप से और इस 9 को क्या कर देंगे, 0, एंड पीछे रिटर्न करेंगे फॉल्स. इस पीछे वाले सेल को पता चलेगा कि यहाँ पे जो 8 रखा था वो गलत था, राइट. इसको फॉल्स आएगा, इसका फॉर लूप एग्जीक्यूट होगा. 8 के बाद यहाँ पे वो 9 रखेगा, राइट. एंड अब 9 रख के फिर से आगे कॉल करेगा इस सेल के ऊपर, इस सब प्रॉब्लम पे कॉल करेगा वो. ये पूरा ग्रिड फिर से सॉल्व होगा, राइट. एंड यहाँ से अगर ट्रू आ जाएगा तो ये भी ट्रू रिटर्न कर देगा. बट अगर यहाँ से फॉल्स आ रहा है तो ये अपने पीछे फॉल्स रिटर्न करेगा. लेट से यहाँ पे 6 रखा था तो इसको हम चेंज कर देंगे 7, राइट. 7 से बात नहीं बनी, 8 से बात बन गई तो हम ट्रू रिटर्न कर देंगे, राइट. तो एक सेल पे हम सारे नंबर्स ट्राई कर रहे हैं और आगे कॉल कर रहे हैं हर नंबर रखने के बाद. जैसे ही आगे से ट्रू आ जाएगा हम रुक जाएंगे और पीछे ट्रू पास ऑन कर देंगे, राइट. सो बैक ट्रैक करने का मतलब क्या है कि फाइनली यहाँ पे आपने कौन सा नंबर रखा होगा, n रख दिया होगा ना मैट्रिक्स में. बट आप फंक्शन कॉल हो चुका है, फंक्शन कॉल के बाद आप वापस जा रहे हो, यहाँ पे 8 रखने के बाद आप पीछे जा रहे हो बट 8 गलत है, राइट. पीछे इसलिए जा रहे हैं ताकि 8 गलत है, राइट. आगे से फॉल्स आ रहा है तो इसको हमें यहाँ पे बाद में 9 करना है. 9 से भी बात नहीं बनी तो इसको हमें 0 करना है, राइट. तो यहाँ पे सारे नंबर्स ट्राई करने हैं 1 से लेके n तक. अगर किसी से भी सोल्यूशन नहीं आता है तो बैक ट्रैक करते वक्त उसको हम 0 कर देंगे, राइट. सो मैट्रिक्स ऑफ आई जे विल बी नाउ 0 एंड वी विल से रिटर्न फॉल्स. करंट सेल से हम सुडोकू को सॉल्व नहीं कर पा रहे. वी हैव ट्राइड ऑल पॉसिबल ऑप्शंस एट द करंट सेल एंड किसी से भी आंसर नहीं आया तो वी विल रिटर्न फॉल्स. एक से भी आंसर आ गया तो हमने यहाँ पे रिटर्न क्या कर दिया, ट्रू, राइट. सो दिस इज़ योर सुडोकू सॉल्वर फंक्शन. एंड अभी हम इसको प्रिंट करवा के देखते हैं. सो सॉल्व सुडोकू को कॉल किया एंड यहाँ पे हमें एक मैट्रिक्स को प्रिंट करना है, राइट. बेस केस में हम प्रिंट करेंगे फॉर int I equals to 0, I less than n, I plus plus. For int j equal to 0, j less than n, j plus plus. We will do cout matrix of ij, right? तो ये काम हमने कर दिया है एंड फॉलोड बाय अ एंडल आफ्टर ईच लाइन, राइट? ऑल राइट, तो यहाँ पे अगर हम थोड़ा सा देखें, राइट, तो ओरिजिनल सुडोको भी देख लेते हैं, राइट? तो हम देख सकते हैं कि हमारा जो सुडोको है वो सॉल्व हो गया एंड किसी भी रो में कोई नंबर रिपीट नहीं हो रहा है, किसी भी कॉलम में नंबर रिपीट नहीं हो रहा है एंड सब ग्रिड्स भी हमारे सही हैं, राइट? तो रो में कोई नंबर रिपीट नहीं हो रहा, राइट? कॉलम में भी नहीं हो रहा, सब ग्रिड में भी नहीं हो रहा है एंड ओरिजिनल इनपुट में जो नंबर्स जहाँ पे थे वो वहीं पे हैं। इसका मतलब हमने सुडोको को सही सॉल्व किया, राइट? So I hope you have understood the solution. If you have any doubts, please ask in the comments section, right? All right. So thank you for watching. I will see you in the next tutorial. Bye. Happy coding.
All right, guys. So today's class is about backtracking, and I will clear some of the backtracking concepts that that people find generally confusing. And I'm just calling this session as backtracking plus plus, so that if you're familiar with basics, then it will be more helpful for you to understand this particular session. Okay, so right. So one particular thing that I want to discuss in this session is how to use bit masks during backtracking, that we will see while solving one problem. Okay. So the problem, I know most of you might have solved earlier also. It's a very common and popular problem. That's the n queen problem. So we will see how to approach n-queen problem. I will quickly give you a recap. How do you approach n-queen problem? And basically in most of the backtracking questions, you will have two type of variants. So one variant will have, okay, given a board or given a maze or given a Sudoku board or given a night, you print one configuration that is a valid configuration, or it is possible you might be asked to print all configurations. Okay, so in both of these cases, the approach remains very similar, except for a small change. So we will see what that small change is. And let's go through the n-queen problem statement. Okay, so n-queen problem says, given a n cross n board, you want to find out a configuration in which you are able to place n queens on the board so that no queen conflicts each other. So if I try to find out a configuration, you can say, okay, if one queen is here, let's say, let's put a queen here, let's put a queen here, let's put a queen here, and let's put a queen here. Okay, so if you just look at this configuration, you can see no queen is going to cut any other queen. Okay, either vertically or diagonally, it's not going to cut any other queen. So that is one possible configuration. Another configuration is you can just take the mirror image of this one and you will get another configuration. Okay, for n equal to 4, so there are two such configurations. One is this configuration that I have just shown you. Another is a mirror image of this configuration that you can build. Okay, so what we generally do in solving such problems is we try to generate all possible configurations, okay, until we get the first configuration. Okay, so if you want to find out the first valid configuration, okay, so maybe in the first you start from this, you say, okay, I will place a queen at this location, and I know since there is one queen in each row. I cannot place a queen in this row, so I just move on to the next row. Here you try to place queens. So you see if this location is safe. This is not safe. You go on the next position. Is this location safe? It's not safe. You go on the next location. Is this location safe? Yes, this is a safe location. So you place a queen here and you go on the next row. Is this location safe? No, it is not. You go here, you go here, and you go here. Okay. But in this row, now you can see there is no location which is safe because of these two queens. Okay, so what you need to do? You need to go back. Okay, so what we can do is we will solve for one row and we will make a call on the sub problem. Okay, so that recursive call will try to fill out the remaining grid and it will return us how many ways are there to solve the remaining grid. Okay, so either it will return the number of ways or it will return if it is possible or not. Okay, maybe true or false. Okay, so if it returns a false, then it means our current configuration is not correct, so we need to update that. So since we are making a call from this row to the next row, that means this location is incorrect, so we try to place a queen here and do the work again. Okay, so are you guys getting what I'm trying to say? Let me open OneNote, that would be better. Question is clear? Everyone knows the n-queen problem? Just let me know quickly. Yes, everyone knows it. Come on, guys, you can respond quickly, okay? Right, good. So I think all of you also know the basic approach, okay? So I think this would be better. So we were at this point, we placed the first queen here. We went to the next row. We placed a queen here. We went to the next row. And in this row, we could not place a queen at any given location. So we just go one step back. So when you go one step back, that means you need to update the location of this particular queen. So you place a queen here and you again come back in this particular row. Okay. So you come back in the third row and you try to fit the queen again. So you say, okay, let me place a queen here. Not possible. Here it is possible. You go on the next row. Here it is not possible. Here it is not possible. Here it is not possible. Also here it's not possible. So what we should do now? We should backtrack to the previous row. That means you remove the queen from this location. You try to place it on the next location. Here it is not possible. Here it is not possible. You backtrack to the previous row and you remove the queen from this location and you go back. And if you go back to the previous row, now you remove the queen from this location and you go to the next location. Okay, you place a queen here, then you come to this row. Here you cannot place, here you cannot place, here you cannot place, and here you can place. You come to the next row, that is this row, and you try to place the queens again. Okay, so what you need to do? At this location, can you place? Yes. You come to the next row. At this location, you can't. At this location, you can't. At this location, you can. You come to the next row. So as soon as you reach, or as soon as you cover n number of rows, you can say our work is done and we have got one configuration. Okay. So the very first time you hit a base case, that basically completes one configuration. Now my question to you is, if you want to generate more configurations, what we should do? If you want to generate more configurations, what we should do? Come on, guys. So that gives us the one configuration. If you want to generate all possible configurations, just print and do nothing else in the base case. Again backtrack. So Akshit has given me the correct answer. We will backtrack. So what we will do, we will try to remove this queen from this location and we will try to place this queen in the next location, but this does not make a valid configuration. So we backtrack and we go to the third row and again we backtrack, we place it here, it doesn't make sense, we place it here, doesn't make sense, we place it here, doesn't make sense, we again do backtrack, we remove this one, we again backtrack, we pick this queen and place it here. Okay, so this way we will again do the same work and we will end up in a configuration that is a mirror image of this configuration. Okay, so for n equal to 4 you will be able to generate 4 configuration. So the difference between one configuration and all configuration is you do not stop once you have found a successful solution. Okay, so if you find one particular solution, you don't stop at that particular point, you keep on backtracking and you try to generate more and more um, possibilities. Okay, so that's what we need to do. So let me show you the code. So here is the code. So there are multiple ways I am going to discuss to implement this approach. So I will come to each and every code one by one. So the first code is you want to just see if there is a possible configuration, then you want to print it. So what we will do, we will have two cases. One is our base case and one is our recursive case. Okay. Okay, so let me also give you the pseudocode along it. Okay, so what you can do is, what you need to do, you need to go over entire all the rows one by one. Okay, you need to go over all the rows one by one. So it's a recursive function. So here I denotes in which row you are currently at. So in the beginning you are in the 0 row. So let's say you are at I equal to 0. For each row, what you need to do? Can anyone tell me what are the steps you need to do in every row? Okay. What is the first step? Try to place the queen at every column in the current row. That's what you need to do. So that's what we will do. We will try to place the queen at every column in the current row. So for j equal to 0, j less than n, j plus plus. So j goes from 0, j goes till n minus 1. So we have to first check if it is possible to place that queen at this location. So we will make a function that will check if it is possible. So that will check if there is a queen in the column or if there is a queen in the diagonal, then that position is not safe. Okay, so if there is a queen here, then this particular position is not safe. So if this position is safe, we will place a queen at that particular place. Okay, so that makes board of ij equal to 1. And what we need to do, we need to make a recursive call on the next sub problem. So next sub problem will be like this. We have n, we have board which remains same. So row number will increase to I equal to 1, I equal to I plus 1. So here we will come to know from recursion that whether we were able to solve this problem by placing a queen at this particular point or not. Okay. So if aage queen rakh pai kya is true, then we have to return true. That means from the current row, we asked the remaining board if you were able to fill the entire board. If this board returns true, then you also return true. Okay, to your parent. Okay, or to the previous row. But if this board returns false, then what is the meaning of this? Suppose you place a queen here and the remaining board returns a false. Then what you need to do? Obviously, you have to check for the other column. Okay, so you have to remove the queen from this particular place and you have to place the queen here, and you again need to do this work. You call on the next sub problem, that is this board, and so that's why we need to remove the queen from the current location. So this removes the queen from the current location, and since this loop is running, it will try to place a queen at the next column in the same row, and we will repeat the work. Okay, and if we try for all the columns, okay, suppose this for loop try to place the queen over all the columns but no location was available, in that case what we should do? So in that case we will come out of the loop and we have to return false because we were not able to find a single solution in which the condition was satisfied. That would mean this return false will go to the previous row, and that row was again using a for loop to control the position of q, and that position of q will get updated, okay, in the previous row. That's what you need to do. So are you getting this code? And what we do in the base case, we just check if I equals to n, then we just print out all the configurations of the board and we say return true. Okay, great. So this will actually help you to print one configuration. Okay, so let me just build this code. Okay, let me just copy this and okay, one इसको कर लेते हैं. Okay, so we have the terminal, and the problem is n queen print 1. Okay, so dot slash n queen print 1. So if I give n equal to 4, I get this one configuration. So this is the code that you need to create one configuration. If you want to print all configuration, then what change should I make? We will return false in the base condition so that it prints all the condition. So in the base case, we are returning true. Okay, so Naveen has given me one hack to do it. He says if you return false in the base case, that will actually print all the configurations. Yes, it is true, because this statement will never get executed, because you will not get aage queen rakh pi kya as true anyway. Okay, so this statement will never get executed and you will always try to generate a new configuration. Okay, so that is actually a hack that you can use. So let me just try to run this one. So dot slash n queen print all. Okay, what's this program? Okay, I have to build it. And n queen print all. Sir, in the base case of n queen function. Right. Sorry. I changed it somewhere else. This should, I think this was true. Okay, let me just copy this and paste this. Yes, so in the base case, here we have to return false, and that will actually give us all configurations, because every row will think that no configuration is possible. So if I give n equal to 4 now, let me build it. I'm getting two configurations. Okay, so that is actually a hack. Okay, but ideally what you should do is you can make this function as a void function. You can return, you can just remove all the return statements, and you can also return this if statement, and you can just make a function call like this and do this. So now this becomes a void function, and if you need to call this function, you will just call this function n queen. So what this void function is doing, it is actually trying to make all possible calls. It does not check for the return value from the next function call, and it will try to make all possible calls. Okay, so if you place a queen here, irrespective of the remaining board was solved or not, uh, irrespective of the remaining board was solved or not, you will always place a queen at the next position. Okay, irrespective of the board was solved or not, you will try to place a queen at the next position. Okay, so you will actually try all positions in the current row, and that will actually happen recursively for all the rows. So are you guys getting this thing? This is the code to print all possible configurations. Any doubts in this one? Okay, no doubt. Everyone says no doubt. Okay. Now suppose you want to count. You want to count the number of configurations instead of printing them. What changes you need to make? Okay. So one way is you declare a global variable, you call it as answer, and every time it hits a base case, you say okay, answer plus plus, and I will put a return statement here. Okay, this return statement is actually important. So base case, at the base case you should terminate the code. And yes, so what changes you will make to this function? If you want to count the number of ways, so one thing is you can do answer plus plus in the base case, and that will increment the answer, right? Okay, so this method is fine. Okay, we keep a counter to increment it. But suppose I do not want to take this global variable. I want to say this is int n queen. Then what should I do? This function should return me the number of ways to place the queen. Then what should I do in this? What should I return in the base case? Return 1. Okay, great. So I think you guys are getting it. So what will happen now is you have this, you're trying to place queen at multiple locations in the current row, and at every location you will maintain a count. You say okay, count is 0, and in this count you add the number of ways which are returned by the remaining board. Okay, so let's say the remaining board says the queens can be placed in 3 ways. So you say okay, the count is 3. You go to the next location, you again call the sub problem, and the remaining board says it can be solved in 2 ways. So you add 2 to your count, and so on. Okay, so that's what you will do. We will add total possible configurations. Yes, that's what we need to do. So for the recursive case, we will assume there is a variable count, let's say 0, and that count will be incremented by the number of ways in which the sub problem can be solved. And here I can return count. Okay, so let me explain this one to you more clearly with the help of one example. Let's say you have this particular board. Okay, and you say okay, and I could put a queen here. Just go and count the number of ways for the remaining board. Okay, so in the remaining board we cannot place queens at this point. At this point we can place, at this point we can't, at this point we can't, at this point we can't. So we backtrack. Okay, so we backtrack. So when we backtrack, can you tell me what is the count returned from here to here? So for this particular row, the count was 0. Count is a local variable that will be created for every row. I will show you the code for can place. That is easy. Okay, so for this particular row, the count will be a local variable that will be 0. And can you tell me when this function returns from here, what will be the value of count? Come on, guys. Yes, so everyone is saying it will be 0. Great, great. So this value will be 0. So this queen knows that if you try to place a queen at this particular location, you have 0 ways to solve this problem. So you remove this queen from here and you try to place it at the next location. So you again do it here. You remove it from here. You cannot place here. You cannot place here. You cannot place here. So that means you go to the next row. Sorry. Yes. So with this, you cannot place it. So let's say you again go back. So once you go back, this row will return a value of count that is equal to also 0, because you could not find a way. So this queen knows that if I put this queen at this location, there are 0 ways to solve it. Then there is a count variable for this particular row also, that is initially 0, and you add a 0 to it. Then you try to place a queen at this location and you try to make a call on the sub problem. Okay, so when you make a call on the sub problem, what will happen is, let's see. Okay, so count is 0 for this location and count is initially 0. It is 0 plus 0 plus if you place a queen here, what will be the count? So it will say, okay, go to the next row and count. So can't place here, we can place here. Okay, go to the next row, can't place here, can't place here. Sorry, we can place here. Go to the next row, we can place here, go to the next row. So as soon as I go to the next row, it hits the base case, and that base case gives me a value of 1. So this queen knows there is one particular way. Okay, so what we do, we go to the next location. We cannot place a queen here, so the count for this row will be 0 plus 0 plus 1 plus 0, that is 1. So this count goes here, that is 1. So this queen is, so we try to place a queen here. Here we will get a count of 0. Here we will get a count of 0. We will get a count of 0. So count for this row will be 1. That will be returned back. And similarly, count for this row will be 1. That will be returned back. So this queen will know, okay, my sub problem is saying there is one way to solve this problem. So count will be incremented by 1. Similarly, when you place this queen at this point, you will get another configuration and will count will be incremented by 1. So this will give you a total count of 2. So are you guys getting it? How this count logic is working? Everyone says yes. Great, 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 guys. So let us just try to see if we are getting the right answer or not. Okay. So I'm saying, okay, this thing now. Okay. So let's try to run the code now. And this code is n queen print all. So dot slash n queen print all. If I give 4, answer should be 2. Okay. Yes. So I also need to remove the configurations from the base case. Let's just comment out this code. I'm not going to print the board. Instead, I'm just going to print the count. Okay, so the count is 2, and for n equal to 8, I should get an answer as 92, which is fine. So for n equal to 8, you have 92 such configurations, which means this code is fine. Now we will try to submit this code on a problem on HackerBlocks. The problem is n queen hard, and it says it's the same problem. So you have to output the number of solutions for given value of n. So let me try to submit this code, and I may get a TLE. Okay. So in the meanwhile, it's getting submitted. Let's have a look at the can place function. So can place function is actually pretty easy. So if you need to check if you can place a queen at this particular location, you just go through this particular column, and you also go through this particular right diagonal, and you also go through this particular left diagonal. Okay. And if you find any queen in one of these, you will return false. So we check the diagonal, and we also check the column. Okay, so this is the check for the column, and this is the check for the left diagonal, and this is the check for the right diagonal. Okay, so can you tell me the time complexity for can place function? Pavan, I'm coming to it. I'm coming to the bit set approach. I will also discuss the bit masking approach. Okay, order of n. Great. So it's going to take order of n time. And what is the overall complexity of n queen problem? How many possible configurations you are generating? Can you guys explain why it is n square or something like this? So I don't understand why it's n square. So effectively what you are doing is you are choosing one position out of n positions here, that is in 91 ways, here also 91 ways, here also 91 ways, here also 91 ways, and you're doing it 9 times. Okay, so it will be of this order, it will be exponential complexity. Okay, so it won't be a quadratic, it will be a exponential complexity, right? Total number of configurations, in every row you have 9 options, or you have n options, it will be n into n into n times, so it will be n raised to the power n. Is it fine? It will be n raised to the power n, right? But the actual running time will be little lesser because you're not trying all possible configurations. Okay, because if you place a queen here, you know you do not need to place a queen here, and hence all the uh, computations that you had to do for this particular configurations, they are avoided, so the running time will be actually lesser than n raised to the power n, but you can say n raised to the power n is a upper bound on this. Okay, so that's one way. So now let us try to reduce the complexity of can place function. Okay, so backtracking complexity we cannot reduce, although it's pretty bad, but all backtracking problems will have a bad complexity. But what you can do is you can slightly optimize the can place function. So we will look at 2-3 more optimizations that we can do to this function. Okay, so let's see first hacker blocks. Okay, it gave us a runtime error. So right, so runtime error because the board size is small, so maybe put it as 20, 20, and then I should try. Mm, okay, so one more change is this. Here also board size should be 20, and here also board size should be 20. Okay, so let me come to the next approach, that is a bit set approach. So what we can do is we can actually make the can place check in O1 time. We can check if we can place the queen in order 1 time. So in this approach, I'm just going to change this method of checking. Okay, I can just change the method of checking the queen, and sorry, it will be O1 time for each x comma y. So at each x comma y, I can just check this in order 1 time. Okay, now tell me, if I have a, a board like this and I have some cells in this 0 0, or let me just do it on this side. Okay, complexity mein I'm saying what you are actually doing is you are trying to pick a position for a queen in every row. So you will place one queen in each row, and that queen can be placed in NC1 ways in this row. For the next row also, that queen can be placed in NC1 ways. So next row also it can be placed in NC1 ways. So total it would be NC1 into NC1 into NC1 for n number of rows. So that means you have to multiply n times, and NC1 is nothing but n. So n is multiplied n times, it's going to be n raised to the power n. Okay, got it. Okay, so guys, let's see one better approach, and then we will discuss a more better approach. Let us say this is a 5 cross 5 grid. So the backtracking logic will remain same. I'm going to make optimizations only on the is save function. So let's say this cell is 0 0, 0 1, 0 2, 0 3, 0 4, 1 0, 1 1, 1 2, 1 3, 1 4, 2 0, 2 1, 2 2, 2 3, 2 4. 30, 31, 32, 33, 34, 40, 41, 42, 43, 44. Okay, so what we can do is we can say, okay, we will try to place a queen at any given location. Okay, now suppose if I want to check if this location is safe or not, what do? You iterate over the column and you also iterate over the diagonal, and that iteration actually takes order of n time. So we want to bring this complexity to order of 1. Okay, that's what we want to do. So what you can do is you can maintain a boolean array and you can just mark what all columns have the queens. Okay, so suppose if there is a queen in this particular column and if this particular column has a queen, if you have a boolean array 0 1 2 3 4 5, you can say, okay, these two columns are not available. So if I want to check, can I place a queen in the second column? So I can directly check, yes, this column is available. So I can place a queen in this column and I can say, okay, this queen column is now not available for the next row. Are you guys getting it? What we can do? Instead of iterating over the column, we can just keep an array to check if that column was used earlier or not. So this check can be done in O1 time. Do you guys agree? Manan says, can you explain that again? Okay. So Manan, I'm saying, okay, suppose you are filling this grid, you place a queen at this location. Let's say you have already placed two queens, let's say one at this particular location, and let's say you have placed one queen at this particular location. So you keep a boolean array from 0 to 4, 0 1 2 3 4. Let's say this is not required, and all the positions are available initially, but suppose you have already done filling in these two rows. Now you are at this particular row and you know there is a queen in the first column, so you mark this position as unavailable. There is a queen in the fourth column, you mark this position as unavailable, and now you are in the third row, that is I equal to 2. So here you can check, okay, if I want to place a queen in this column, if is this column safe, you can directly check from column of 0. So this column is safe. Got it? Right. So space complexity, it's going to be very less space. Okay, it's going to be order of n space, and also when you're doing backtracking, you are still using order of n space due to recursive call stack. Okay, so in a way, the complexity, space complexity is not increasing here. Okay, but we are reducing the time complexity. So we have maintained an extra array to make a check. Now the problem is with the diagonals. What we can do with diagonals? How do we check for diagonals? Are the diagonals for this position safe? Basically, I want to check if this diagonal is safe or not. If there is a queen in this diagonal or not. That's what I want to check. Anyone? Those who have done the algo course might have done this thing. Anyone? Right, Piyush is giving me something correct. Okay, so let's guys discuss one thing. So we have to actually observe one pattern that that is actually a property of diagonals. So if you
see along this diagonal, and if you try to find out sum of elements, sum of indices, okay, so if this location is I comma j, if you see what is I plus j along this diagonal, 0 plus 3 it's 3, 1 plus 2 it is 3, 2 plus 1 it is 3, 3 plus 0 it is 3. And what about this diagonal? Can you see what is the sum of elements? Sum of indices, okay, x comma y or I comma j. So 2 plus 0 is 2, 1 plus 1 is 2, 0 plus 2 is 2. So that means we can do some kind of hashing. We can just reduce that diagonal into a single integer. Are you guys getting it? If you look at this diagonal, the sum of elements is 1. If you look at this diagonal, sum of elements is 0. If you look at this diagonal, the sum of elements is 4. If you look at this diagonal, sum of elements is 5. If you look at this diagonal, sum of elements is 6. Here it is 7 and here it is 8. So that means each diagonal can be mapped with each diagonal of this form can be represented as a unique integer. Are you guys getting it? I plus jth index. Yes, R plus C. So I can say I will make another diagonal array, and I can mark the diagonal as true if there is a queen in that particular diagonal. Okay, suppose if you place a queen here, okay, so that means it's going to block the 0 plus 1 at the diagonal. That means one of this diagonal will be marked as false. Are you guys getting it now? So if you want to check for this queen, if this diagonal is safe or not, for what you will check in this array, the 0 plus 2th index, that is the 2th index, is this index safe or not? That's what you need to check. So basically for any given position r comma c, you will check for the index r plus c in the diagonal array, if that index is true or false. So that diagonal check can be done in order one time. Now we have one diagonal which is left, that is the other diagonal. Okay, so this particular diagonal, and so on. Okay, any doubts till now? Anyone? So yes, Shivam is saying R minus C. Yes, we will do something of that sort. So if you carefully look at along these diagonals, you will see the difference is constant. Okay, so let's try to see this diagonal. So if you do I minus j, that is 2 minus 0, that is same as 3 minus 1, that is same as 4 minus 2. So this diagonal can be represented by a unique number as 2. Okay, if you see this particular diagonal, the difference is again constant. It can be represented using 1 minus 0, that is 1. Okay, this diagonal, it is actually 0. What about this particular diagonal? It is 0 minus 1. For this diagonal, the difference is negative, minus 1. For this diagonal also, the difference is negative, that is minus 2. And for this diagonal, it's minus 3. So what you need to do is, if you see the unique values for this particular diagonal, they are in the range minus 3 to plus 3. So we can keep an array that actually maps these values from 0 to, okay, since we cannot keep a array with a negative index, we can keep an array with positive index, or you can make a hash map. So we will try to map minus 3 to 0, and we'll try to map 3 with 6. Okay, so what will happen is, now we keep another array for this particular diagonal. Okay, this for this diagonal, and you can see, okay, if a particular diagonal is used, I will just make that diagonal unavailable. So I cannot place any other queen in the same diagonal. Okay, so that's the whole idea here. Okay, so what we need to do, we need to move minus 3 to 0. So I need, say, for every element that I get r minus c, I need to add a value plus 3 to it. So how do I get 3? So 3 is nothing but n minus 1. So I will actually use this index in this array to mark that diagonal as available or unavailable. Are you guys getting it? Yes, so we will keep three arrays, one for the columns, one for the left diagonal, and one for the right diagonal. Yes, you can use a map also. That is also fine. Okay. Either you can use a map. If you use a map, then you do not need to add this particular value. So this is basically shifting. Shifting we have done due to negative values. Okay. You can keep a map, you can keep an array, and you can also keep a bit set. So bit set is also like an array. It's an array of bits. So it's a class in C++, and it is memory efficient. Okay. So if this is an array of 30 bits, the total memory it will occupy is 30 bits. Okay. But if you make an array of boolean, so one boolean is 8 bits, and if you need an array of 30, that will require 30 into 8 bits. So that's why we are just using a bit set here. Okay. Otherwise you can make a boolean array also. That's also fine. Okay. So what I do in the code now is, let's see, I have declared a global variable called answer. No, it's not global, it's in the main, and it's passed by reference. You can also make it as a global, but this one is a better way. So what I check, if I see if R denotes my current row. Okay. So R denotes in which row I am currently at. It starts from value 0 and denotes the total number of rows, and answer denotes me what is the total number of configurations possible. So every time I hit the base case, I increment my answer by 1. Okay. And since it is passed by reference, so there are no copies of answers in the stack. There is only one answer that is in the main, and every time we hit the base case, that answer is incremented. So what we do here, can anyone explain what I'm doing in this line number 10? Yes, so I'm traversing one complete row, and I'm trying to place queen at every column in the current row. Yes. So, and in line number 11, I'm checking if I pick this particular position, row comma C, that is R comma C, if this position is safe or not. So for that, I need to check if that column does not contain a queen, if that right diagonal does not contain a queen, and if that left diagonal does not contain a queen. Okay. Is this check clear? So we are checking from those three hash maps or those three arrays that we have done. Okay. So we are checking if there are no queens in that. Okay. If that position is particularly safe, so what we do, we try to place a queen in that particular diagonal. So if I say, okay, is this position safe? If these three checks are satisfied, okay, place a queen here. And if you place a queen here, you will mark that column and that diagonal as 1, which means these diagonals have been used, and you make a recursive call on the next row, and once you backtrack, means this call is over, you again unset that. Okay, so in the previous code we were doing this thing, board ij equal to 0, remember, here. So you were also doing backtracking, board of ij equal to 0, so that you want to try out the next configuration. So here also we don't have a board, but you want to try out the next configuration. That means you have to remove the queen for which you have already counted the ways. So this step is a backtracking step. Okay, so here you place the queen, and in this step you unplace the queen by making those positions as available. So 0 means available and 1 means booked. Are you guys getting this now? Everyone says yes. Great. Anyone having any doubts? You can also use mic to ask questions. Okay. What would be the new time complexity? Right. So the new time complexity will be 1 by n times of the previous complexity. That's it. Okay. 1 by n of previous complexity. Mic option is not How we will print the results? Good question. So for that, what you can do is, if you want to print the results, you will need to keep a board array, okay? And instead of using a isSave function, you can just make the check using the same criteria that I have just discussed, and also keep the same in the board array. Okay, so what you need to do is, you can put a board array here, int board of this 20, and you can say equal to board of r comma c equal to 1, and equal to board of r comma c equal to 0, and here you print the board array. In the base case, you print the board array. पवन, किसका डाउट था ये? Shivam, is it clear now? Shivam, this is what you need to do. If you have the board array, and the rest everything will remain same. Great. Yes, so that's what you need to do if you have the board. Okay, great. Now we will move on to the next approach that is actually little more efficient than this particular approach. And let's see. Okay, so the first code that I submit got me a time limit exceeded, because that was slightly inefficient. Now let us try with this particular code. I'm not sure, although this one is more efficient, but let's see if it passes all test cases or not. Okay, I need to remove this board array now. Okay, so this question has also passed all the test cases, but still we can optimize it further. Okay, so do you want to learn about more optimization, or you are done? It's not giving TLE, it's getting accepted. Okay, so using bitset it got accepted, and without it it was not getting accepted. Okay, so time is 1.91 second. We can try to reduce it this time further. So let's try to reduce this time now. So everyone says yes, we want to learn one more approach. Okay, so let me come to the next approach. So in this, we are going to solve nqueen using bit mask. I'm not going to use any board array. I'm just going to use these 4 or 5 lines of code, and I will explain you what we are doing here. And I've referred this code from the book CP3 by Stephen Alim. Okay, so let's see. Very elegant solution I found out from the book. So let's see, and I will try to explain you this one also. Okay. Okay guys, so let's see. This time, forget about the board array, forget about the 3 arrays we had made. But what we will do, we will keep 3 numbers. Okay, we will keep 3 integers. Okay, so 3 integers as uh, 3 integers to check whether that particular column is safe, row is safe, oh sorry, diagonal is safe. Okay, so one for the left diagonal, one for the right diagonal, and one is called a row mask. So let me explain you what I am doing. So what we can do is, if you have something like this, and suppose if you have placed a queen here, and if you have placed a queen here, So you can say I can maintain a number 1001 that will tell me, okay, there is a queen in this location and there is a queen in this location. So this number is what? This number is 9 actually. So I actually need an integer instead of an array. Okay, and an integer can have 32 bits, and in any case my constraints will be n less than equal to 32, because for very large values of n we cannot use backtracking solution. Okay, maximum for n equal to 20 or something. उससे ज़्यादा करेंगे तो it will lead give us a TLE. So are you guys getting what is row mask? So row mask is nothing but it denotes the columns in which we have already placed a queen. So if we have a queen like this, that means a row mask will have this particular notation. Okay, so this is what row mask will look like if all the columns are filled. Okay, and at any given point of time, I will make sure my constraints are not violated, that no queen cuts each other should still hold true. Okay, so what I'm doing is, I'm in the base case, I'm checking if row mask equal to done. So what is the value of done? It's 1 left shift n minus 1. So if n is 4, so what is 1 left shift n? 1 left shift 4 minus 1. So this number is 16 minus 1, that is 15. So this will actually give me a mask in which you have last 4 bits as set. So I'm checking if all the columns have been filled. That means my work has been done and I increment my answer by 1. Are you guys getting it? This step, base case. ओके, बेस केस समझ आ रहा है? बाकी लोग thumbs up. Great. So all right, not under. Okay, base case. So Pawan, I'm saying you start with a case like this, and you go to the next row, you make it like this. You go to the next row, you make it like this, something like this. Okay, and you go to the next row, you make it like this, 1 1 0. You go to the next row, you make it like this, and finally in the base case, when you have achieved this number, it means all the columns have at least one queen. That's what it means. So that means we have placed a queen in every column and our work is done. So we increment by answer our 1. So that's what we are going to do in every row. In every row, we are going to change the row mask. Pavan? Got it. Pavan says got it. Great. So that's what we are going to do. So we are going to do it for row mask, we are going to do it for left diagonal, and we are going to do it for right diagonal. Now we have 3 things. Initially all of them are 0. That means you have everything as 0 in the beginning. So row mask is 0, column mask is also 0, and left diagonal is left diagonal is 0 and right diagonal is 0. Okay, so row mask basically stores columns, and left diagonal basically is going to mark in which diagonals you have placed a queen. Okay, which diagonals are not safe. That's something like that. Okay, so now let us try to understand what we are going to do. So guys, it's slightly complex, so listen carefully. Okay, see carefully. So what I will do is, suppose I am in the first row, and suppose I have already tried out this particular position. Okay, so that would mean I will first generate a safe mask. I will generate a mask that will tell me what all uh, positions are safe in the current row. Okay, so I'm generating a safe mask, that is row mask or left diagonal or right diagonal. Suppose you have right. So suppose what you have done is you have placed a queen in the first row at this particular coordinate. So can you tell me what positions are not safe in the second row to place a queen according to the number. Can you tell me, if I place a queen at this location, what all positions are not safe in the second row? Okay, 0, 1 and 2. All of these positions are not safe. Right. Great. So what we will do is, if you place a queen at this location, this position is getting blocked, this position is getting blocked, this position is getting blocked. Okay. So for this particular queen, the row mask was 0, the left diagonal was also 0, the right diagonal was also 0. Okay, but when this queen is placed at this particular location, the row mask will become 1 like this, the left diagonal. Okay, okay, what we will do to the left diagonal is, due to this queen you are actually blocking this diagonal. Okay, this particular column, so this column is getting blocked. So what do, you say, okay, okay, let me take a number as p. Let's say p is a number like this, which means you have picked this position in the current row. So what changes you will have on the next row? Okay, so can you tell me what will be the value of row mask for this particular row when you come to this? That means this particular row is blocked. Can you tell me the row mask value for this particular row? Which means the first column is blocked. Okay, so carefully look at this. So I'm doing a or between row mask and p. So that means if row mask was 0 0 0, if I do an or, I will get a value of row mask like this, 0 1 0 0. Okay, this will be the value of row mask. What will be the value of left diagonal? So left diagonal will store what diagonals are blocked in the left. Okay, so that would mean if you do or between the left diagonal of the previous row with the position of current row, and you try to left shift it by 1, so that would give you this value. So left diagonal is 0 0 0 and p is 0 1 0 0, and you do a left shift, that will give you 1 0 0. So that means this particular diagonal is blocked. What about the right diagonal? So right diagonal, you will do or between the previous right diagonal, that is 0 0 0 0, with the position that is 0 1 0 0, and you right shift it by 1. So that will give you 0 0 1 0. So right diagonal will be 0 0 1 0. And if you want to check what all positions are safe, so you need to do an OR of all of them. So that will give you 1 1 1 0. Okay, so that means all the positions where you have a 1, those positions are blocked. Okay, and I'm taking a note here. Okay, I'm taking a note here because I want to say, okay, put 1 at those positions which are safe. So safe mask will contain this value 0 0 0 1. Are you guys getting it? What we are doing? So safe mask will have a value of 0 0 0 1. Okay, and I have done an and with the variable done. So done is like this. So just to make sure that so done, this can be a 32-bit number and it can have lot of more bits. Just to make sure that the remaining 28 bits are 0, I have done with the and with the value of done. Okay, so done is like this. You have 28 zeros followed by 4 ones. So if you do an and with this value done, so any bits that you might get here, they will be automatically discarded. Those bits we do not need because we just have a 4x4 board or a n x n board. So we are doing a and with done. So I think this instruction is clear. How do you compute the safe value? Okay, Great. Now we will discuss one very interesting approach to find out the set bits from a number. Okay, let's see. So let's talk about the optimization that we are doing here. So in the previous example, we said, okay, if we want to place queen in this row, we have to check for all columns, right? That's what we did. But in this problem, in this solution actually, we actually have a mask like this. We have a mask that is being generated in order one time for the entire row. Okay, and we do not need to iterate over all the bits of the mask because we know of a mechanism to find out the set bits from the mask directly without iterating over all the bits. Okay, so in bit masking there is a way to directly iterate over these two bits without going through bits which are zero. Are you guys getting the idea? So in earlier case, in the first case, you had to, in the first solution, you were iterating over all the n columns and each column took n time. So you took roughly n square time. Okay. Line 14 and 15, I'm coming to it. Wait. In the first approach. Then in the second approach, you went to all the columns and you solved for each column in order one time. So you still took order n time for each row. In the third approach that I'm discussing, I will only place the queen at those columns which are safe. So I will directly come to know which columns are safe, which are not safe. How? With the help of safe mask. Okay. So let me explain you how we can do it. Okay. Now suppose you are given a number like this, n equals to, let's say number is 9 le lete. Okay. And suppose I want to find out the positions which are safe. Okay, so in this you have two positions which are safe. So one position is 0001 and another position is 100. Are you guys getting it? So that would mean we just need two iterations of the loop to get the two positions. Okay, even if you have a number like 100000001 or 00101, you can just find out the positions in three iterations. Okay, how? So for that we will try to see this form. Okay, what we will do, let's say this number is n. So the logic to do it is like this. While the value of n is greater than 0, we can say position equals to n and minus n, and I can say n equal to n minus p. That will make sure the loop is going to run exactly two times and you're going to get these positions. Okay, so let us try to do it for dry run it for a value of n equal to 9. Okay, so if n is 9, so can you tell me what is n and minus n? So minus 9. So if you try to do this multiplication, so n is 1001, what is minus of 9? That would mean flip all the bits 0110 and you add a 1 here, that would be like 0111. Okay, and if you do an and now 0111, what you will get? You will get p. So p is n and minus n, so you get this number 0001. So you are getting the first number in first iteration and you do n equal to n minus p or safe equal to safe minus p. So if you subtract this p from 9, okay, so n is 1001. First time you get a p as 001, you do n equal to n minus p, the new value of n will be now 100. And what is minus n now? This is 8. 8 is like this. So what is minus of 8? Flip all the bits and add a 1 to it. So it will be again like this. Okay, so it is 1000. So you do an AND with 1000 and what you will see is you will get 1000 only. Okay, and if you do n equal to n minus p, you will actually subtract this from this, and your loop will become 0. So in the second iteration you are getting this number. that's that means this is the second safe position in the current row. So this, so instead of iterating over n places, you can just finish your work by iterating over 2 places. That's what I'm saying. So we say, okay, we find out the safe position. Once we know the safe position, for the next row, we update the row mask, we update the left diagonal, we update the right diagonal. That's what we do. And for every row, we again find out the safe mask using this formula. Uh, are you guys getting little bit? I know it's getting little difficult. We can go through one example if you say, okay. Kamal says all good. Recording, I will see, okay. Kamal says well explained, good. So let's say you, let's try to dry run it with the help of one more example. Let's say you place a queen here. So initially the row mask is 0 0 0. Left diagonal is also 0 0 0. Okay, and right diagonal is also 0 0 0. Okay, so this is in the first, before the first row. When you enter in the second row, since you have placed a queen here, your row mask will become 0 1 0 0. Left diagonal will become, you add the position. Okay, so position mask will be like this, 0 1 0 0. Now you might ask, how do we know this is the right position mask? Okay, so initially all positions are safe, so you will actually iterate over all the rows. Okay, but I'm just taking the case when you have your positioning at this particular point. Okay, so when you are finding out this position mask, you will get a mask with only one set bit, with one set bit, and that would be the last set bit. So actually this is a way, technique in bit masking I have also discussed in the bit masking webinar, that if you want to count the number of set bits, you can use this technique. So I'm just using that technique inside backtracking. Okay. So that would give you a position mask like this. Actually you will get this one, this one. Okay. Not this one. So firstly you will get this one, then you get this one, and then you come to this one. Okay. So let us assume we got this particular mask. For according to that, you will block the left diagonal, that's this. You will block the right diagonal, that is this. And you will have uh, left diagonal as this and right diagonal as this. Okay, and if I talk about the safe positions, that will be not of 1 1 1 0. So that means it will be 0 0 1. So that means only one position is safe in this, in the second row. So we just place a queen here. Now can you tell me what will be the values of row diagonal, left diagonal and the right diagonal in the third row? Can you tell me the bit masks for this? So this column will get blocked, okay, because if you find out P from here, P will be 0 0 0 1. Okay, so this will get blocked. So that means whatever is your old row mask, you will do an OR with P. So this is your old row mask. You do an OR with P, you will get 0 1 0 1. Okay. What about the left diagonal? So earlier, now due to this queen in this row, this particular cell is blocked, but it is out of bounds, so that will not get affected. But the right diagonal will also block this one. Okay, so what we will do is we will pick the old right diagonal, which is sorry, this one. This is row and this is right. We will pick the old right diagonal that is blocking this position in this row. We will also right shift it with 1. Okay, so what we do is this actually expands like this, right diagonal right shift 1 and do an OR with the new position right shift 1. So we have combined these two steps into one. So it's like right diagonal or P both right shift 1. Okay, so we have to propagate the effect of previous queens on the new rows as well. Okay, not just the previous row, but all previous rows will propagate an effect that will move one step right as you go in the next row. Are you guys getting it? Every time you go one step ahead in the next row, the effect of previous right diagonals will be propagated one step towards the right. Okay, so what I'm saying is this is your previous right diagonal. So if you do an OR with P, so what is P in this case? P is 0 0 0 1. So right diagonal is 0 0 1 0. P is 0 0 0 1. And if you just combine these two, that becomes 0 0 1 1. And if you do a right shift 1, that becomes 0 0 0 1. So this will be the right diagonal for this particular row. Okay. And what about the left diagonal? So this diagonal should get blocked. So what is my original left diagonal? That is 1 0 0. And according to it, I do an OR with P, this, and I just do a left shift 1. So it becomes 1 0 0 1, and doing a left shift 1 will give me 0 0 1 0. Okay. So this will be 0 0 1 0. So that would mean, finally, if I just check in this particular row, so I have the last three positions as blocked. So that means these positions are blocked and only this position is safe to place a queen. So this is my safe position. Okay. Come on, guys, you can ask questions if you want. Lavanpuri says, got it. Saurabh, got it. Kamal, Seema, Kamal says, got it. Time complexity and printing maze. So yes, printing maze, actually you can actually figure out from this value of P what is the index of the queen. Okay, so basically what you need to do is if you have let's say a number like this. Okay, P will be a number like this, and if you want to see in which place I have to put the queen, so this is the place in which you have to put the queen, and here also you can just find out without iterating what is the position of this set bit. So can you tell me the formula to find out the position of a set bit in a number which has only one set bit? So it will be log n or log n plus 1. So you can keep a board array, and on the log n plus 1 and 1th index, you can place the queen and you are done. Piyush, from the P, you can find out the position of board by saying the index will be log n. Okay. Yeah, how many set bits you have in a number? Log n bits hote hai na? So if I say, if I have this position 0 1 1 1 0, I want to see 0. What is this number? This number is 8. And what is this index? 0 1 2 3 4. Okay, you want to find out the third index is going to have a set bit from the right. Okay, so that means in the board, in the ith row, you keep a variable I here. Okay, and every time you go to the next row, you do I plus 1. That's fine. And in which column you will have, so column you can find out like this. You can say, okay, I'm putting a queen in this column, that is third column from the right. So log of 8 is to the base 2. So this is uh, 3. And if you want to find out the position from the left, so that would be like n minus log of p. That will be the index of the column. Okay, so this is the column, and you can put queen here like this. Okay, Got it? Lavanpuri says, got it. Okay, so guys, since the time was short, I could have written this code step by step and could have explained these things in more detail. But since this is a small class, so I won't be going in more details of this. Otherwise, we can do it in little more detail. Okay. So any other questions? If you have, you can ask me. And generally these type of things are good for competitive coding, and maybe you can use some of these methods in solving some other problems as well. But obviously an interviewer will not expect you to write such code, and this was just a brain exercise. Okay, if we had problem is crossword puzzle. All right, so there is a 10 cross 10 crossword which is given to you along with some set of words, ठीक है, which need to be filled in the grid, right? So अगर मैं इस example से आपको explain करूं, so there is a grid like this which has some plus and some minus in it. Two types of characters are there in the grid, right? So 10 cross 10 का grid है, and you have to fill characters जहां जहां पे minus आ रहे हैं. So where there is a minus, you can insert some strings, and these strings should be this. ठीक है? These strings should be there. So example, इसको अगर fill करते हैं, so this becomes something like this. यहाँ पे लंदन फिट हो रहा है, यहाँ पे दिल्ली फिट हो रहा है, यहाँ पे आइसलैंड फिट हो रहा है, एंड यू कैन सी कि कुछ करेक्टर्स ऐसे हैं जो रीयूज हो रहे हैं, राइट? देयर आर सम करेक्टर्स which are being getting reused. So sounds interesting. मतलब ब्रूट फोर्स का क्वेश्चन है, कंस्ट्रेंट छोटे हैं ना कंस्ट्रेंट्स 10, 2 की पावर 10 कितना होता है 1000, और हर सेल पे तुम डाल सकते हो 10 लेंथ हर रो में, ठीक है? कुछ नहीं है, जो रिकर्जन और बैकट्रैकिंग क्वेश्चन होते हैं ब्रूट फोर्स क्वेश्चन होते हैं, ठीक है? तो यहाँ पे बस ब्रूट फोर्स ही मारना तुम्हें. ब्रूट फोर्स सोचो कैसे कोड लिख सकते हैं ब्रूट फोर्स का, बस ये सोचना है. कोई सॉर्टिंग वॉटिंग कुछ नहीं चाहिए, सिर्फ ब्रूट फोर्स एल्गोरिथम लगेगा. इसका ना कोड नहीं डिस्कस कर रहा हूं मैं कोड गो थ्रू कर देता हूं और लॉजिक गो थ्रू कर देता हूं. ब्रूट फोर्स ये है, ऐसे कुछ सोचना नहीं है हटके इसमें, ठीक है? So what you have to do is you have to just, अगर पिक वन वर्ड, ठीक है? तो पहले तुम एक माइनस को सर्च करने का ट्राई करो, जहां पे माइनस मिलता है वहां से देखो कि आगे कितनी जगह खाली है. अगर आगे खाली नहीं है तो नीचे जाओ, नीचे चेक करो कितनी जगह खाली है. अगर ज्यादा जगह खाली और ये वर्ड फिट हो सकता है तो उसको फिट कर दो, लंदन फिट कर दो, ठीक है? फिर अगला वर्ड पकड़ो, ठीक है? और फिर ऐसा अगला ऐसा करेक्टर ढूंढो जैसे नॉन, यू हैव टू सर्च फॉर अ नॉन प्लस, राइट? मतलब प्लस नहीं होना चाहिए, प्लस को छोड़ के कुछ और हो, राइट? तो अगर तुमने यहां पे लंदन प्लेस कर दिया तो ओ पे जाओगे ना, ओ पे जाओगे, ढूंढोगे ओ, अब ओ से देखोगे आगे कुछ जगह है खाली नहीं है, नीचे कुछ खाली जगह है, नीचे नॉन प्लस तो है बट उसके जो करेक्टर्स हैं वो दिल्ली से मैच नहीं कर रहे हैं, तो यू विल स्किप दिस. ओ को भी छोड़ दोगे, एन पे आ जाओगे, फिर डी पे आ जाओगे. यहाँ पे चेक करोगे डी से आगे खाली जगह है और डी से मैच हो रहा है, तो दिल्ली को रख सकते हो सकता है यहाँ पे कोई और वर्ड होता है डेनमार्क, ठीक है? तो ऐसा हो सकता था कि यहाँ पे मैंने दिल्ली रखा और एक्चुअल में यहाँ पे डेनमार्क आना था। तो क्या होगा, हम आगे कॉल करेंगे, आगे से आएगा रिटर्न फॉल्स कि आगे का पजल सॉल्व नहीं हो पा रहा है। तो अगर फॉल्स आ रहा है तो हम दिल्ली की जगह यहाँ पे डेनमार्क रख के देख लेंगे। ठीक है, सो बेसिकली यू हैव टू ट्राई ऑल पॉसिबिलिटीज, हर एक वर्ड को हर एक माइनस पे हॉरिजॉन्टली और वर्टिकली दोनों दोनों तरह से प्लेस करके देखना है। अगर सोल्यूशन मिल जाते हैं बहुत बढ़िया, नहीं मिलता तो यू विल बैक ट्रैक। ठीक है, इसको तुम लोग ट्राई करना, मैं कोड गो थ्रू कर देता हूँ। मैंने लिख रखा है इसका कोड, जावा में भी लिख रखा है, सी प्लस प्लस में भी लिख रखा है। ठीक है, तो मैं दोनों में गो थ्रू कर देता हूँ। ठीक है, सो ये सी प्लस प्लस वाला कोड है। पहले मैं तुम्हें जावा में थोड़ा सा हमने मॉड्यूलर कोड लिखा है, वो गो थ्रू कर देता हूँ। ठीक है, तो ये देखो, एक यहाँ पे क्या है, दिस इज द मेन फंक्शन, बेसिकली कंप्लीट द पजल हेल्पर। इसको क्या मिल रहा है, एक पजल मिल रहा है। हैश सेट बेसिकली एक सेट ऑफ सिटीज है। ठीक है, जो जो सिटी तुमने ले लिया उसको सेट में से रिमूव करते जाओ। ठीक है, अब जैसे अगर मैं बोलूं कि मैंने पजल सॉल्व करते वक्त, मान लो यहां तक मैंने दिल्ली यूज कर लिया और इस रो तक मैंने लंदन यूज कर लिया। तो बेसिकली ये क्या कर रहा है, सेट में से दिल्ली और लंदन को हटा दे रहा है, डेनमार्क जो भी आगे सिटीज हैं। सो अगर इनको यूज कर लिया तो इनको हटा दे रहा है, बट ऐसा हो सकता है कि ये गलत जगह इंसर्ट हुए हों। ठीक है, तो जब हम बैक ट्रैक करेंगे तो वापस से इनको इंसर्ट कर लेंगे। अगर हम वापस लंदन पे आते हैं तो लंदन को डाल लेंगे सेट के अंदर, फिर से वो बैक ट्रैकिंग से अपने आप हो जाएगा। ठीक है, तो यहाँ पे क्या किया, सेट की कॉपी बनाई और उस कॉपी में से लंदन को रिमूव कर दिया। ठीक है, अभी मैं तुम्हें गो थ्रू कर देता हूँ यहाँ पे क्या किया है। ठीक है, सो देखो, अगर तुम्हें एक ऐसा कैरेक्टर मिलता है विच इज माइनस, माइनस का मतलब क्या है कि हम वर्ड को प्लेस कर सकते हैं। ठीक है, सो माइनस का मतलब ये है, अगर हमें कहीं पे माइनस मिल रहा है, लेट्स से यहाँ पे माइनस मिल रहा है, तो हमने एक फंक्शन बनाया गेट आर एच एस एम्प्टी सेल्स काउंट। इसके राइट में कितने ऐसे सेल्स हैं जो एम्प्टी हैं, वो मेरे को मिल गया, तो इसका अकाउंट आ जाएगा 3। ठीक है, और ये भी चेक कर लिया लेफ्ट में कितने एम्प्टी सेल्स हैं। मान लो यहाँ से अगर स्टार्ट किया, लेफ्ट में कितने एम्प्टी सेल्स हैं वो चेक कर लिया, राइट। तो अगर लेफ्ट में होंगे तो ठीक है, नहीं तो यही वाला होगा स्टार्टिंग वाला। ठीक है, फिर हमने चेक किया कि इसका साइज कितना है, व्हाट इज द साइज ऑफ माइनस। जैसे इसका साइज 2 है या इसका साइज 4 है। ठीक है, तो फॉर एवरी सिटी बिलोंगिंग टू द सेट, एस डिनोट कर रहा है सिटी, और मैं पहले क्या करने वाला हूँ, हॉरिजॉन्टली प्लेस करके देखने वाला हूँ। ठीक है, हॉरिजॉन्टली प्लेस कर रहा हूँ और फिर मैं वर्टिकली प्लेस करूंगा। तो मैंने चेक किया, अगर राइट साइज में जो भी माइनस है उनका साइज ग्रेटर देन 1 है तो मैं कोई सिटी प्लेस कर सकता हूँ। सिटी में उतनी लेंथ का प्लेस कर सकता हूँ जितने माइनस अवेलेबल है। तो हमने चेक किया कि क्या सिटी की लेंथ माइनस वाली विंडो के लेंथ के इक्वल है। ठीक है, और हमने चेक किया क्या हम राइट में फिट कर पा रहे हैं। राइट में फिट करने का मतलब ये है कि ऐसा भी हो सकता है ना कि यहाँ पे कोई वर्ड ऑलरेडी डला हो, लंदन टाइप्स, और हम यहाँ पे लेट से इंसर्ट कर रहे हैं इंडिया, तो कैन फिट का मतलब है कैन और एन मैच कर रहे हैं तभी हम इंसर्ट कर पाएंगे। ठीक है, तो काउंट बेसिकली क्या कर रहे हैं, माइनस और ऐसे वाले सेल्स को काउंट कर रहा है, नॉन प्लस वाले सेल्स को काउंट कर रहा है। राइट, सो कैन फिट ये बता रहे हैं। ठीक है, अगर कर पा रहे हैं तो हमने क्या किया, पजल में यहाँ पे मान लो इंडिया रख दिया और उस पजल की कॉपी बना ली। राइट, कॉपी क्यों बना ली, बिकॉज अगर एक्चुअल एरे में चेंज करेंगे तो बैक ट्रैक करते वक्त हमें ये रिस्टोर करना मुश्किल होगा। कॉपी बनाएंगे तो कॉपी में रिस्टोर अपने आप हो जाएगा। ठीक है, तो हमने पजल की कॉपी बना ली। अगर तुम C++ में कर रहे हो तो 2D एरे को वेक्टर ऑफ कैर ले लेना और बाय वैल्यू पास कर देना, तो तुम्हारा बैक ट्रैक अपने आप होगा। अगर सिंगल एरे में करोगे तो तुम्हें मैन्युअली चेंज करना पड़ेगा, हर जगह कैरेक्टर्स को रीराइट करना पड़ेगा, ठीक है। तो हमने क्या किया, अगर मैंने इंडिया को कंसीडर कर लिया तो इंडिया और एक सेट की भी कॉपी बना ली, राइट। अगर मैं अगली स्टेट पे जा रहा हूँ, इंडिया, लंदन, ठीक है। तो तुम एक काम करो, तुम एक हैश मैप रख लो यार, तुम एक हैश मैप रख लो, यहाँ पे सेट रखा है, तुम हैश मैप रख लो। तो जिन जिन सिटीज को तुमने ले लिया उनको ट्रू मार्क करते रहो, और जिनको नहीं लिया उनको फॉल्स मार्क करते रहो। सो यू विल पिक वन सिटी विच इज नॉट मार्क्ड ट्रू, तो फॉल्स वाले सिटी में से उठा लेना। तो यहाँ पे सेट रखने की जरूरत नहीं है, यू कैन सिंपली कीप अ हैश मैप ऑफ स्ट्रिंग एंड इंटीजर, स्ट्रिंग एंड बूल, कौन सा सिटी लिया कौन सा नहीं लिया, राइट। और उसको राइट में फिट करके देखो। तो जब तुमने इसको फिट कर दिया, राइट कैन फिट बता रहा है कि फिट कर सकते हैं, राइट फिट का मतलब है कि यहाँ पे इंडिया डाल दिया। तो हमने क्या किया, नेक्स्ट एम्प्टी सेल फाइंड आउट किया। लेट्स से यहाँ पे कहीं पे माइनस है, तो नेक्स्ट एम्प्टी सेल ये निकला, राइट। और अगर नेक्स्ट एम्प्टी सेल नहीं मिलता है तो इसका मतलब क्या, हमारी पजल सॉल्व हो गई है, उसको प्रिंट कर देंगे और काम खत्म। और अगर एम्प्टी सेल मिल जाता है तो हमने क्या किया, उस एम्प्टी सेल पे पजल भेजी, अपना हैश मैप भेजा, और वो एम्प्टी सेल के कोऑर्डिनेट्स भेजे, रो एंड कॉलम। सही है। ये केस था हॉरिजॉन्टली फिट करने का, ठीक है। इसका बिल्कुल सिमेट्रिक केस क्या होगा, वर्टिकली फिट करने का, बिल्कुल सेम है। वर्टिकली फिट करने में क्या होगा, हमने चेक किया कि डाउन में कितने एम्प्टी पोजीशंस हैं, राइट। फिर हमने देखा ऊपर ऊपर कुछ खाली पोजीशंस हैं तो उनको भी काउंट कर लिया, ठीक है। और फॉर ऑल द सिटीज जिनकी लेंथ मैच हो रही है और वो डाउन फिट हो सकते हैं, ठीक है, हमने क्या किया, पजल की कॉपी बनाई, सेट में से वो सिटी हटा दिया या फिर हैश मैप पे उसको ट्रू मार्क कर दिया, और वहां पे उसको फिट कर दिया। फिट करने से यहाँ पे वो वर्ड प्लेस हो जाएगा। अगला सेल ढूंढा जो नॉन एम्प्टी है, अगर वो सेल नहीं मिलता है तो उसको प्रिंट कर दिया, काम खत्म। अदरवाइज हमने क्या किया, हेल्पर को कॉल कर दिया और नेक्स्ट एम्प्टी सेल दे दिया जिस पे काम नहीं हुआ है। ये कंडीशन इसलिए ले रहे हैं ताकि जितने माइनस है एग्जैक्टली उतने उतने लेंथ का वर्ड हमें फिट करना है, ठीक है। अगर यहाँ पे 5 लेंथ का तो तुम इंडिया फिट करना पड़ेगा, तुम यहाँ पे DLI फिट नहीं कर सकते ऐसे, ये खाली नहीं रहने चाहिए, ठीक है। इसलिए ये कंडीशन चेक कर रहे हैं, और टाइम बचेगा ना यार, हम सारे वर्ड्स को फिट नहीं करेंगे, हम उन्हीं वर्ड्स को फिट करेंगे जिनकी लेंथ अवेलेबल विंडो से मैच हो रही है। यार C इक्वल टू नल का मतलब पता है क्या है, C इक्वल टू नल का मतलब ये है कि तुम्हारा पूरा काम खत्म हो गया, मतलब C डिनोट कर रहा है नेक्स्ट एम्प्टी सेल। अगर तुम्हें कोई नेक्स्ट एम्प्टी सेल नहीं मिलता, मतलब पूरे मैट्रिक्स में कोई माइनस मिला ही नहीं, इसका मतलब क्या है, काम खत्म, प्रिंट कर दिया पजल और काम खत्म। ये एक तरह का बेस केस है, ठीक है। इसको रन करके देख लेते हैं। ठीक है, तुम देखो एक काम कर रहा है, इसने बना दिया पूरा मैट्रिक्स वैसे ही। ठीक है, सो ऑल टेस्ट केसेस आर पास्ड। एक बार खुद से देख लेना यार, ठीक है। मल्टीपल आंसर है तो मल्टीपल एक्सेप्ट हो जाएंगे, ठीक है। और एक इसका एक C++ वाला भी है मेरे पास, तो सेम कोड C++ में भी लिखा हुआ है, तुम लोग देख सकते हो 3131। इसमें बस फंक्शंस नहीं बनाए हैं, थोड़ा बड़ा कोड है इसलिए मैं लिख नहीं रहा हूं उसको। 3131 ठीक है। तो अभी ये प्रॉब्लम है सैगिट द हॉर्स मिस्टर, राइट। सो बेसिकली क्या प्रॉब्लम है कि यहाँ पे एक मैट्रिक्स गिवन है तुम्हें, मतलब बेसिकली एक यूनिवर्सिटी है जिसके अंदर कुछ रूम्स हैं, ठीक है। तो एक हॉस्टल है जिसमें कुछ रूम्स हैं, यूनिवर्सिटी है, ठीक है। एंड एक मैट्रिक्स गिवन है n क्रॉस n की, जो डिनोट कर रही है, so basically this denotes the building, right? So this is your college building and there is a चौकीदार, ठीक है। यहाँ पे एक गेट कीपर है जिसको बोला गया कि बिल्डिंग की लाइट्स बंद करके आनी है, राइट। तो इसके बाद इसको बोला गया लाइट्स बंद करके आनी है बिल्डिंग की। एंड ये जो गेट कीपर है ये लेफ्ट से एंटर कर सकता है एंड देयर आर m रूम्स इन एवरी रो, ठीक है। एंड ये जो ये फर्स्ट और लास्ट कॉलम है ये स्टेयर्स है, ठीक है। तो बेसिकली सीढ़ी से वो ऊपर जा सकते हैं, यहाँ पे सीढ़ी लगी हुई है फर्स्ट इसके अंदर, और यहाँ पे भी सीढ़ी लगी हुई है, राइट। एंड इट इज गिवन उसको एक रूम से दूसरे रूम में जाने में 1 मिनट लगता है और उसको बेसिकली सारी लाइट्स बंद करनी है, ठीक है। ही हैज टू टर्न ऑफ ऑल द लाइट्स, बेसिकली जहां जहां पे वन है वो वाली लाइट ऑन है, उस रूम की लाइट ऑन है। तो सीढ़ियों में कोई लाइट नहीं है, जहां जहां पे वन है वहां वहां पे लाइट है, ठीक है। और स्टार्टिंग में वो लेफ्ट से एंटर कर सकता है, उसके बाद वो कैसे भी जा सकता है। उसके बाद वो मतलब वो यहाँ से गया, सीढ़ी चढ़ी, इधर से आया, हो सकता है वो यहाँ से ऐसे घूम के इधर से जाए, ये लाइट बंद करे फिर घूम के जाए, या फिर ऐसा हो सकता है वो डायरेक्टली ऊपर चढ़ जाए, राइट। क्वेश्चन समझ आ रहा है? सो हमें क्या बताना है, मिनिमम टाइम टेकन बाय चौकीदार टू स्विच ऑफ ऑल द लाइट्स। तो अगर वो इस तरह से जाए, यहाँ से वापस आ जाए, फिर ऊपर जाए, इधर जाए, इधर जाए, इधर जाए, और फ्लोर चेंज करने में भी उसको 1 मिनट लगता है, ठीक है। इस टेस्ट केस में कितना टाइम लगेगा उसको? हाँ यार, इसमें बिट मास्किंग लग सकती है, ठीक है। सो 1 मिनट उसको लगा यहाँ, 2 3 4 5 6 7 8 9 10 नहीं, 1 मिनट दोबारा देखते हैं। यहाँ तो वो खड़ा ही, आई थिंक 1 2 3 4 5, यहाँ पे 1 मिनट वेस्ट होगा ऊपर जाने में, बस 5 6, वापिस आने में 7, ऊपर जाने में 8 9 10, यहाँ पहुंच गया 11 12, 1 मिनट हमने ज्यादा ले लिया, राइट। देखते हैं, मतलब पास तो इसका यही है, शॉर्टेस्ट पाथ तो यही लग रहा है, ठीक है। बट ऐसा भी ये हो सकता है कि एक रो में मल्टीपल लाइट्स ऑन हो, तो हो सकता है वो ऐसे जाए, मतलब हमें पता नहीं है कैसे जाए। उसके पास हर एक रो के बाद 2 ऑप्शन है। ट्वेंटी 21 नहीं है यार, इसका आंसर 12 है। एक बार पढ़ लेते हैं। So next line and lines contain the building description. Each length contains a binary string of length m plus 2 representing a floor. 0 denotes light is off, 1 denotes light is on, right? Floors are listed from top to bottom, ठीक है। Last line represents the ground floor, ठीक है। And number of rows 15, number of columns 100 है, ठीक है। चलो एक बार यहीं पे मैं ट्राई करता हूँ। फर्स्ट केस को देखते हैं। कह रहे In the first case, it will go in the room 1 in the ground floor, then it will go in the room 2 in the second floor using left or the right stairs. एक सेकेंड, स्टेयर्स पे टाइम लग रहा है क्या? इट टेक्स नो टाइम टू स्विच द लाइट ऑफ इन द रूम इन, ठीक है, लाइट ऑफ करने में कोई टाइम नहीं लग रहा, ठीक है। स्टेयर्स में जाने के लिए, ऊपर जाने के लिए एक यूनिट टाइम लग रहा है, और नेबरिंग रूम में जाने के लिए भी 1 मिनट टाइम लग रहा है, ठीक है। तो एक बार बना लेते हैं, हो जाएगा ये। तो देखो यहाँ तो खड़े ही है, 1 मिनट, 2 मिनट, 3 मिनट, 4 मिनट, 5 मिनट, 6 मिनट, 7 मिनट, 8 मिनट, 9 मिनट, 10, अरे क्या हो गया, 1 मिनट यहाँ, 2, 3, 4, अब इधर से ऊपर आया, 5 मिनट में ऊपर पहुंच गया, फिर इधर 6 मिनट, 7 मिनट, 8 मिनट, 9, 10, 11, एक बार रीड ही कर लेते हैं, let us. In the second example, he will go to the 4th room, use the right stairs, go to the 4th room in the second floor, then go to the second room in the last floor, ठीक है। ठीक है, थर्ड एग्जाम्पल में कह रहा है he will alternate, थर्ड एग्जाम्पल में ऑल्टरनेटली मूव करेगा। चलो एक बार ट्राई करते हैं इसके लिए। यहाँ पे वो खड़ा है, लेट से यहाँ पे आने में 1 मिनट, 2, 3, 4, 5 मिनट में ऊपर, 6, 7, 8, 9 मिनट में ऊपर, 10, 11, 12, 13 मिनट में ऊपर, 14, 15, 16। चलो ट्राई करते हैं एक बार फिर से। इसको पास करके यहाँ पे आया 1 मिनट, इधर आया 2 मिनट्स, इधर आया 3 मिनट्स, इस रूम को क्रॉस करके इधर आया 4 मिनट्स। अब ऊपर चढ़ जाएगा, ठीक है, 5 मिनट्स, 6, 7, 8, इसको क्रॉस किया 9, ऊपर चढ़ गया 10, 11, 12, 13, 14, ऊपर चढ़ गया 15, 16, 17, 18। यस, यही करना है, ऊपर चढ़ने का टाइम लेना है हमें अलग से, ठीक है। 18 मिनट्स लग रहे हैं। यहाँ पे भी देख लेते हैं, 1, 2, 3, 4, 5, ऊपर चढ़ गया 6, 7, वापस आया 8, 9, 10, 11, 12। बस लास्ट लाइट तक पहुंचने का टाइम नोट करना है, एंड इट इज 12 मिनट्स। तो ये कैसे अप्रोच होगा क्वेश्चन? अच्छा मेरे को एक चीज ये बता दो, क्या मैं ये बोल सकता हूँ, क्या मैं यहाँ पे ग्रीडी लगा सकता हूँ कि अगर इस रो में लास्ट फ्लैट बिट यहाँ पे है, मतलब तो यहां से जाना बेटर ऑप्शन होगा। मतलब क्या मैं ये देख सकता हूं कि अगर अगली रो में जिस सीढ़ी के पास लास्ट रूम है उस सीढ़ी से चढ़ूं, क्या मैं ये बोल सकता हूं? इस लाइट से फर्क पड़ रहा है क्या? अगर मैं बोलूं ऊपर के रूम्स की लाइट इधर है सारी, तो बेटर है ना कि हो सकता है तुम्हें क्वाइट पॉसिबल कि ये वाला पाथ तुम्हें छोटा पड़े, बट ऐसा भी हो सकता है फिर ये वाला पाथ भी छोटा पड़े, या नहीं? तो देखो ये बात वैसे क्लियर है कि अगर इस रूम के अंदर, मैं ये बोल सकता हूं कि किधर से चढ़ना ये नहीं मेरे को पता, किधर से चढ़ना मेरे को ये नहीं पता, ठीक है, बट मैं ये बोल सकता हूं कि इफेक्टिवली अगर मैं प्री कंप्यूट कर लूं हर एक रो में लास्ट रूम की पोजीशन क्या है, फ्रॉम द लेफ्ट एंड फ्रॉम द राइट, ठीक है। तो मेरा एल्गोरिथम एफिशिएंट हो जाएगा। तो मैं क्या करने वाला हूँ, प्री कंप्यूट पोजीशन ऑफ या इंडेक्स ऑफ लास्ट रूम फ्रॉम लेफ्ट एंड द राइट फॉर एवरी रो। तो दो एरे बना लेना, एक बताएगा कि आयत रो में लास्ट रूम कहाँ पे है फ्रॉम द लेफ्ट, और एक बताएगा कि आयत रो में लास्ट रूम कहाँ पे फ्रॉम द राइट। उससे ये होगा कि तुम्हें बस करंट रो से अगली रो पे कॉल करना है, और तुम्हें दोनों ऑप्शन लेके देखना है कि अगर तुम लेफ्ट से चढ़े हो और तो तुम्हें लास्ट रूम बंद करने के लिए कितना टाइम स्पेंड करना पड़ेगा। लेट से एल ऑफ आई डिनोट कर रहा है आयत रो में लास्ट लाइट बंद करने का टाइम, यहां से अगर तुम एंटर करते हो, ठीक है, तो ऐसा कुछ हो जाएगा 2 × Li +-1 देख लेना जो भी आ रहा होगा, और अगले फ्लोर में तुम यहीं से चढ़ रहे हो ऐसा। या फिर ऐसा हो सकता है कि तुम राइट से एंटर किए हो, अगर राइट से एंटर किए हो तो टाइम कितना हो जाएगा, यहां से गए और यहां से वापस आ गए, तो वो कुछ हो जाएगा 2 × Ri टाइप्स। या फिर ऐसा हो सकता है कि तुम राइट से एंटर किए और लेफ्ट से ऊपर चढ़ गए, वो भी टाइम तुम निकाल सकते हो। या फिर तुम लेफ्ट से एंटर किए राइट से ऊपर चढ़ गए, ठीक है। तो फंक्शन जो तुम्हारा होगा उसमें तुम्हें करंट डायरेक्शन रखनी पड़ेगी, किस तरफ से तुम सीढ़ी चढ़े हो, लेफ्ट से आए हो या राइट से आए हो, ये रखना पड़ेगा, और कौन सी रो पे तुम जा रहे हो, कौन से फ्लोर पे तुम जा रहे हो, ठीक है। और यहां से तुम कॉल करोगे, कॉल कैसे करोगे, कॉल होगा कि तुम लेफ्ट से आए हो और लाइट बंद करके लेफ्ट से ऊपर चले गए, लाइट बंद करके राइट साइड से ऊपर चले गए, तो क्या आंसर होगा, इन दोनों का मिनिमम। या फिर अगर तुम करंटली राइट से आए हो, राइट साइड से एंटर किए हो और लेफ्ट से ऊपर चढ़ गए हो, या फिर राइट से ऊपर चढ़ गए हो, तो इन दोनों का मिनिमम। तो ये लेफ्ट लेना है या राइट लेना है वो डिपेंड करेगा करंट डायरेक्शन तुम्हारी लेफ्ट थी या राइट थी। क्योंकि ये ब्रूट फोर्स है तो दोनों ही केस लेके देखने हैं, फाइनली जो भी मिनिमम होगा वो तुम रिटर्न कर दोगे यहाँ पे। सिर्फ बेस केस को, ग्राउंड वाले रो को अलग से हैंडल करना है, बिकॉज इसमें तुम राइट से आ नहीं सकते, ठीक है। तो इफेक्टिवली जो तुम्हारा ग्रिड है, इतनी प्रॉब्लम तुम्हारी रिकर्जन सॉल्व करेगा, और ग्राउंड वाली रो के लिए तुम्हें मैन्युअली सॉल्व करना पड़ेगा, ठीक है, बिकॉज इसमें राइट से एंटर नहीं कर सकते, सिर्फ ये ट्विस्ट है इसके अंदर। ये बात समझ आ रही है? चारों केसेस समझ आ गए हैं? देयर आर 4 केसेस, और हर एक रो में कितना टाइम लगेगा वो तुम कंप्यूट कर ही सकते हो यार, कि तुम्हें पता है लास्ट रूम यहाँ पे है तो इतनी लाइट्स बंद करनी है, मतलब इस रूम तक जाने में इतना टाइम लगेगा, इसका जो इंडेक्स है, या फिर इधर से है तो इतना लगेगा। या फिर अगर तुमने पूरी रो ट्रेवर्स की है तो पूरी रो जितना टाइम लगेगा, या फिर पूरी रो तुमने लेफ्ट टू राइट ट्रेवर्स की है तो भी इतना टाइम लगेगा। लिख लोगे कोड? ठीक है, तो इसको तुम ट्राई करना। दिस प्रॉब्लम इज 812 B कोड फोर्सेस, 812 B कोड फोर्सेस।